this way in the video, since this generalizes to points in Rn, right? You can have n tuples, and this will work. Okay, so let's go ahead and try to figure out the proof. So proof. So I think we should be able to figure it out fairly easily. So I'm just going to go ahead and just try to do the proof all at once. Instead of just trying to figure it out first, let's go for it. So let epsilon be greater than 0. And then choose delta equals, and I'm going to pause here because I don't know what delta is. So at some point, we're going to come back and fill this in. Okay, so choose delta equals some magical number. Then for all pairs x, y in the plane with, I'm going to go ahead and write it like this. With this condition here, square root x minus, in this case it's 0 squared, right, plus y minus 0 squared less than delta, right? X naught and y naught are 0 in this problem. We have, and so now we have to look at the distance between f of x, y, and L. So f of x, y is this piece here, so it's x cubed over x squared plus y squared, and that's minus 0. And we want this to be less than epsilon. So this is equal to the absolute value of x cubed over x squared plus y squared. So we want to make this small. So one thing we can do here is we can say this is equal to the absolute value of x times the absolute value of x squared over x squared plus y squared. This is a reoccurring idea in these types of problems. So when I saw the x cubed, I thought, oh, I can borrow an x and do this, you know. And this number here is less than or equal to 1. So this is less than or equal to the absolute value of x times 1. Now, if you're not convinced by that, it's pretty easy to see that it's true. Just let me do it on here on the side. So if x is 0, then it's 0 and we're done because everything is less than epsilon. If x is not 0, then you can write this x squared over x squared plus y squared. You can drop the y squared, and so you just get x squared over x squared, and so it's less than or equal to 1. So in any case, it's less than or equal to 1. So what do we do next? Well, now there's a little trick, another little trick. So this is equal to the absolute value of x, and the absolute value of x, you can write this as the square root of x squared, right? And that's the same thing as saying the square root of x minus 0 squared, right, which is what we have here. And so this expression should be less than or equal to the square root of x minus 0 squared plus y minus 0 squared. And that's less than delta, right? So now we know what our delta has to be. It has to be epsilon, right? And so all of this is equal to epsilon. So I hope that made sense. I kind of rushed through it. That's it. So we're asked to show that a function is nowhere differentiable. So the natural thing to try first is to check the Cauchy-Riemann equations. If they do not hold, then we're done and the function is nowhere differentiable. So in this problem, we're going to set u of xy to 2y. And v of xy, this is actually negative x. You have to be careful here, negative x. So now we'll compute the partial derivatives and check the Cauchy-Riemann equations. So del u del x, that's equal to 0. Del u del y, that's equal to 2. Del v del y, that's equal to 0. So these are the same. So far so good. And let's see, negative del v del x. Well, negative del v del x is negative 1. But here you have another negative, so we're just going to get 1. So right away you see that these guys are not the same. So since del u del y is not equal to negative del v del x, the Cauchy-Riemann equations do not hold. And this is true for every complex number, so the Cauchy-Riemann equations never hold at any point. So the function is nowhere differentiable. So f is nowhere differentiable. You have to be really careful. Sometimes there's functions where the Cauchy-Riemann equations will hold at certain points or pieces of the complex plane. I hope that helps. Okay, so we have to prove that f of z, which is equal to the conjugate of z, is nowhere differentiable, so proof. So all we'll do is we'll show that f fails to satisfy the Cauchy-Riemann equations, and so it's not differentiable anywhere. First, let's rewrite f. So f of z is equal to the conjugate of z, and we can write z as, let's say, x plus iy conjugate. So we compute the conjugate, we just get x minus iy. All right, so now let's carefully identify u and v. So set u of xy equal to x, and v of xy, this is actually negative y. Gotta be careful. All right, so now we'll compute the partial derivatives. So del u del x, that's equal to 1. Del u del y, that's equal to 0. And then del v del y, that's equal to negative 1. And del v del x, negative del v del x, well, that's 0, and negative 0 is just 0, so 0. So these are equal, but for the Cauchy-Riemann equations to hold, these have to be the same, and these have to be the same. So it's not going to work here because these are not the same. So since del u del x is not equal to del v del y, the Cauchy-Riemann equations do not hold. So they completely fail. Equations do not hold. So therefore, f is nowhere differentiable, right? It never holds at any point. 1 is never equal to negative 1. So that's how you use the Cauchy-Riemann equations to show something is not differentiable. So we're going to prove that if we have a convergent series, then the limit of a sub n as n approaches infinity is equal to 0. So this is actually the nth term test from calculus. It may not look like it, but when we're done with the proof, I will go over why it actually is. So proof. So we'll start by assuming that we have a convergent series. So suppose that we have a series that converges to, say, L, where L is a real number. So all we have to do now is write down what it means for a series to converge. So this means that if we take the limit as n approaches infinity of the nth partial sum, we get L. So here, the nth partial sum is equal to a sub 1 plus a sub 2 plus dot 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 plus a sub n. So when we say a series converges and we write stuff like equals L, what we really mean is that the limit of these guys, s sub n, is equal to L. So convergence of a series is actually defined in terms of convergence of a sequence, right? So really important. Okay, back to the proof. So we have to show that this limit is equal to 0. So we have to show that an approaches 0, a sub n approaches 0 as n approaches infinity. Well, if you look here, we have a sub n. So the trick is to write a sub n in a clever way. So note, a sub n, well, we can write that as a sub n plus a sub n minus 1 plus dot 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 plus a sub 1. Now what we'll do is subtract away all of these guys. So minus a sub n minus 1 plus dot 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 plus a sub 1. So a sub n is really equal to, well, all of this is s sub n, and all of this is s sub n minus 1. So this is s sub n minus s sub n minus 1. So if we take the limit, so then if we take the limit as n approaches infinity of a sub n, that's equal to the limit as n approaches infinity of s sub n minus s sub n minus 1. And this is equal to, well, this converges to L, and this converges to L. So you just get L minus L, which is equal to 0. Now, this actually requires a proof. I mean, if you really want to get technical, you can prove that if this converges to L, then this also converges to L, because these are technically different, right? Here you have an n, and here you have an n minus 1. It's a straightforward application of the definition of convergence of a sequence. Very, very easy to do. Worth doing. Worth doing. So that's it. We're done with the proof. We showed that the limit of a sub n as n approaches infinity is equal to L. All right, so why is this the nth term test? Well, look at this statement here. It says that if this is true, then this is true. So it turns out that there's something called the contrapositive, which is equivalent to this statement. Let me write that down. So contrapositive. So we're going to write the contrapositive of what we just proved, which is logically equivalent. So our statement says if this is true, then this is true. So the contrapositive will say if this is not true, then this is not true. So what does it mean for this not to be true? Well, it means that the limit as n approaches infinity of a sub n is not equal to 0, or the limit as n approaches infinity of a sub n does not exist. So if this happens, then this does not happen. So it will be diverges. So a sub n diverges. So let's go over that again, because the contrapositive is an important idea in mathematics. So our statement said that, let me use a different color, if this was true, then this is true. The contrapositive says if this is not true, then this is not true. So what does it mean for this not to be true? It means this. What does it mean for this not to be true? It means diverges. So this is typically what you see in a calculus class. It's called the nth term test. And it is absolutely your best weapon when determining convergence and divergence. It's the first thing you should always try when you're being asked whether a series converges or diverges. I hope this helps. Hi YouTube. In this video we're going to prove that the function f of x equal to x over x minus 1 is uniformly continuous on the set 2 to infinity. Before we do the proof, let's recall what it means for a function to be uniformly continuous. So we say a function f is uniformly continuous in this case on the set bracket 2 to infinity if for every epsilon greater than 0 we can find some delta greater than 0 such that for all xy in this set, so x and y are in the set 2 to infinity, with the distance between x and y being smaller than delta, we have the distance between f of x and f of y being smaller than epsilon. So we have. All right. So before we do this proof, we have to actually figure it out. So I kind of did like a little sketch before making this video, so we should be able to do it. If not, we'll just delete the video. Let's try it. So scratch work. All right. So we know that we will have the distance between x and y less than delta. We have that to work with. And we have our epsilon, and it's greater than 0. And we know that x and y are in this set here, 2 to infinity. And we have to show that the distance between f of x and f of y is less than epsilon. So if we look at that distance, f of x is x over x minus 1. And then f of y is y over y minus 1. And this has to be less than epsilon. So the natural thing to do here is perform the subtraction. So the LCD here is x minus 1, y minus 1. And then to perform the subtraction, it's just x, and then here you're missing y minus 1, minus, and then y, and what's missing here, x minus 1. So just performing the subtraction here of the fractions. And then you distribute. So I'm going to come up here. So we get the absolute value. Let's see, we'd get xy minus x, right, distributing the x, minus yx, and then looks like it's plus y in this case. That's all over the LCD, so x minus 1, y minus 1. Okay. Does anything cancel here? Yeah, these cancel, so that's good. Okay. So we get the absolute value of y minus x over the absolute value of x minus 1, and then here we have y minus 1. All right, you can rewrite y minus x as x minus y. It's the same thing, right? The distance between y and x is the same as the distance between x and y. And then here on the bottom, we still have the absolute value of x minus 1. You know what? I'm not going to write it in absolute value. I mean, it doesn't matter. I'm going to go back to what I had before, right? This is just scratch work. We can just go back and forth. And we're almost stuck here, right? So at this point, we know that this is, we can say this is less than delta. And then we have this bottom piece here. We have the x minus 1, and then we have the y minus 1. And we're kind of stuck because we have this bottom term here. Like, how do we deal with this nonsense here? So you want this to be, less than epsilon, but we're stuck. So here's where you have to go back and think about this. X and y, let's just take x for instance, is in this set here, 2 to infinity, right? So the problem told us this. This is probably important, right? So that means that x is greater than or equal to 2. You say, okay, I have x greater than or equal to 2, and then down here I have an x minus 1, right? So how can you make this look like what we have down here? Well, what I was thinking is we can subtract 1 from both sides. So if you do x minus 1, then this becomes a 1 over here on the right-hand side, right? You just do minus 1 on both sides. Then you can divide by x minus 1 on both sides, and so you would get 1 greater than or equal to 1 over x minus 1. Aha! So you get 1 over x minus 1 less than or equal to 1. So you can do the same thing with y, right? So this should be less than or equal to, let me scroll down a little bit so you can see it. So this should be less than or equal to delta over 1 times 1, right? So if we make delta equal to epsilon, we got it, right? We will have it. So now we can do our proof, and we can repeat everything we just did in a more elegant way. So let's go ahead and do the proof. Let me scroll up a little bit more. A little bit more. There it is. Okay. So let's start the proof. So we'll start the proof by letting epsilon be greater than 0. And we're going to choose our delta to be equal to epsilon. So then for all x and y in this set with the distance between x and y smaller than delta, we're going to look at the distance between f of x and f of y. So f of x in this case is x over x minus 1, and f of y is y over y minus 1. Kind of a fun problem. The LCD is x minus 1, y minus 1, so this is going to be absolute value x, y minus 1, minus y, x minus 1, over x minus 1, y minus 1. This is something we did earlier, the subtraction, right? You could multiply this by y minus 1 over y minus 1, and this by x minus 1 over x minus 1, same thing. Let's go ahead and distribute here. So this will be the absolute value of xy minus x, right, distributing the x, and then minus yx, and looks like it's plus y, right, plus y. Easy to mess up here, right, because negative and negative is positive, and then we have x minus 1, y minus 1. These cancel. Okay, these cancel. Let's go ahead and rewrite this down here. So this is equal to So we have the absolute value of negative x plus y over x minus 1, y minus 1. Didn't mean to write it that way. Let's write it as like this. Let's write it as the absolute value of y minus x over the absolute value of x minus 1, y minus 1 absolute value. We know that the absolute value of y minus x is the same thing as the absolute value of x minus y, so I'll rewrite it one more time just for clarity. Then we still have this x minus 1 and the y minus 1 on the bottom here. And we know that x minus y is less than delta. So this is less than delta over all of this stuff down here. So we have x minus 1, y minus 1. And I'll mention it again, and I'll go through the thought process again. But we know that since x is bigger than 2, right, x minus 1 is greater than or equal to 1. So 1 over x minus 1 is less than or equal to 1, right? So we get this. So we can put a less than or equal to here and replace these with 1s. This is delta, 1 times 1. This is delta, and this is equal to epsilon. And this step here, this is, let me just mention it over here. This step here, this is since, just a little side note, just to make it really clear. Since x and y are in this set, right, just for emphasis, that means both x and y are greater than or equal to 2. That means x minus 1 is greater than or equal to 1. Therefore, that means 1 over x minus 1 is less than or equal to 1. Likewise, that means y minus 1 is greater than or equal to 1. So 1 over y minus 1 is less than or equal to 1, right? And therefore, the product is less than or equal to 1, right? And you might say, well, can you just multiply these? Yeah, these are all positive, right? Everything here is positive because x and y are bigger than 2. So you can multiply these, and the product is less than or equal to 1. So they're each less than or equal to 1 times 1, which is 1. So no problems. So that completes the proof. That completes the proof. I hope this video has been helpful. Thanks for visiting. That's it. Hey YouTube. In this video, we're going to prove that the sine function is continuous at every single real number. Recall that a function is continuous at x equals c. So let me just say f is continuous at x equals c if for every epsilon greater than 0, we can find some number delta greater than 0 such that for every real number x, so for all x and r, with the property that the distance between x and c is less than delta, we have that the distance between f of x and f of c is less than epsilon. So that's the delta epsilon definition of continuity. So we're going to use that to do the proof here. This proof is actually pretty simple and just basically relies on some trig identities and some other facts. So rather than just do the scratch work, I'm just going to show you the proof. So proof. It doesn't take some huge intuition to find the delta as it typically does in these problems. So we'll start by letting epsilon be greater than 0. And we're going to choose our delta to just be epsilon, believe it or not. It's that simple. Then, for any x, for any real number x, with the distance between x and c less than delta, and now we're going to look at the distance between sine x and sine of c, right? We're proving continuity at an arbitrary number c, and that will show it's continuous for every number c. So we look at the absolute value of sine x minus the absolute value of sine c. And now here's the trick. There's a trig identity, right? So this is equal to absolute value 2 cosine x plus c over 2 sine x minus c over 2. So you have an absolute value here around the cosine and sine. So you have a couple things you can do here. So you know that the absolute value of cosine and the absolute value of sine, they're both less than or equal to 1. But we also know that the absolute value of sine x is less than or equal to the absolute value of x. Right? So that's also useful. So what we'll do here is we'll use this one, the one that tells us that it's less than 1 for cosine, and we'll use this one for the sine function. So this is less than or equal to, you can pull the 2 out, 2 times 1 times the absolute value of x minus c over 2. The 2's here will cancel because you can pull it out of the absolute value, so you just get the absolute value of x minus c, and that's less than delta. We know that by assumption. But delta is equal to epsilon, and that completes the proof. So not a very difficult proof, but it does rely on this fact, and it does rely on the trig identities. I hope that made sense. Prove that if A is normal in G and B is normal in H, then the direct product of A with B is normal in the direct product of G with H. So first note that if A is a subgroup of G and B is a subgroup of H, then A cross B is a subgroup of G cross H. So we'll just focus on proving the normality in this problem. So suppose that A is a normal subgroup of G and B is a normal subgroup of H. And the claim is that A cross B is a normal subgroup of G cross H. So take any pair GH in G cross H and pair AB in A cross B. Then we have to look at the following element to prove normality. So GH, AB, and then the inverse of the pair GH. So this is equal to GH, AB, and the inverse of the pair G comma H is just G inverse H inverse. Now we'll use the definition of multiplication in the direct product. So this is GA, G inverse, HB, H inverse. And this element here, this is an A, and this is because A is normal in G, little g is in G, and little a is in A. Likewise, this element here is in B, and this is because B is normal in H, little h is in H, and little b is in capital B. So this pair is in A cross B. And so we're done with the proof. Thus, A cross B is a normal subgroup of G cross H. Not a hard proof, but the notation, it takes some getting used to. I hope this helps. In this video, we're going to prove that every Boolean ring is commutative. So recall, we say a ring R is Boolean if it contains the element 1, and for every element in our ring R, we have the property that x squared is equal to x. In other words, every element is what's called idempotent. Okay, let's go ahead and do the proof. So proof. So suppose we have a Boolean ring R, and we'll take x and y in our ring. And we have to show that the ring is commutative. So we'll start by looking at the element x plus y. That's an element in our ring, and our ring is a Boolean ring, so every element is idempotent. In particular, x plus y is idempotent, so this is the same as x plus y quantity squared. And this means x plus y times x plus y. Using the distributive property, we can write this as x times x plus y times x plus y. Using the distributive property once again, we have x squared plus xy plus yx plus y squared. And since every element is idempotent, this is equal to x plus xy plus yx plus y, right? Because x squared is equal to x and y squared is equal to y. If we subtract x and we subtract y from both sides of this equation, we end up with 0 is equal to xy plus yx. So this means that xy is equal to minus yx. Now, recall that in a previous video we proved that in a Boolean ring, the characteristic is 2. So in particular, y plus y is equal to 0. So this means that y is equal to negative y. So then, if we look at xy, well, that's minus yx. We can write that as minus y times x, and minus y is equal to y, so this is yx. So we've shown that xy is equal to yx for all xy in our ring R, so R is commutative. So pretty easy proof, but it does rely on the fact that a Boolean ring is of characteristic 2. I hope this helps. Prove every Boolean ring is of characteristic 2. So let's go ahead and do it. Proof. So before we start the proof, let me remind you what a Boolean ring means. So R is a Boolean ring if it contains 1, and every single element, so for all x in our ring R, every single element is idempotent. So x squared is equal to x for all x in R. And a ring is of characteristic 2 if x plus x is equal to 0 for all x in R. In general, the characteristic of a ring R is equal to n. This means that if you take x plus dot 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 plus x, this is equal to 0, and here we have n sum n's. And moreover, n is the smallest positive integer for which this is true, and this has to hold for all x in the ring. So that was kind of rushed. Let's go ahead and do the proof. So we have to prove it's of characteristic 2. So we have to prove that x plus x is equal to 0 for all x in our ring. So for all x in our ring, the natural thing to do is to start by looking at x plus x. Well, x plus x, well, that's an element in the ring, and every element is idempotent. So this is actually equal to x plus x, and then this is being squared. Well, what does this mean? This means x plus x times x plus x. Then we can use the distributive property to write this as x times x plus x times x plus x. And distributing again, we end up with x squared plus x squared plus x squared plus x squared. But every element is idempotent, so this is simply x plus x plus x plus x. So we have x plus x is equal to x plus x plus x plus x. Subtracting 2 of the x's, we end up with 0 equal to x plus x. It est, we have x plus x equal to 0, and that proves that every Boolean ring is of characteristic 2. Pretty easy proof. I hope that made sense. Suppose phi from G to K is a group homomorphism. We have to prove that if H is a subgroup, that's what this notation means, subgroup of G, then phi of H is a subgroup of K. So here phi of H is defined to be the set. This is called the direct image of H. And we have to prove that it is a subgroup of K. So proof. So we have to show three things. One, that it's non-empty. Two, that it is closed under the group operation. And three, that it is closed under inverses. So we'll start with one. We'll first show it's non-empty. So since H is a subgroup of G, the identity element in G is the identity element in H. It is in H. Thus, phi of the identity element in G, which is the same as the identity element in H, is in phi of capital H. So phi of capital H is not empty. This is actually really easy here, but it's easy to get confused. Remember, what does it mean for an element to be in phi of H? All of the elements look like this. They all look like phi of little h with H and H. So here our little h was the identity. Okay, 2. We have to prove it's closed under the group operation. So suppose we have two elements in phi of capital H. What does this mean? Well, this means there exists, let's say, H sub 1 and H sub 2 in capital H, such that x is equal to phi of H sub 1 and y is equal to phi of H sub 2. And we have to show that the product x times y is also an element of phi of capital H. So let's just go ahead and look at that product. So then xy is equal to phi of H sub 1 times phi of H sub 2. But phi is a group homomorphism, so this is just phi of H sub 1, H sub 2. And this is certainly an element of phi of capital H. And this is since H1, H2 is in H, because H is closed under the group operation. Right? It is a subgroup, so it is closed under the group operation. So we have phi of an element in H, and that's what it means to be in phi of capital H. 3, we have to show it is closed under inverses. So suppose again that we have some x in phi of capital H. Then there exists some little h in capital H, such that x is equal to phi of little h. We have to show that the inverse of x is also in phi of capital H. So then, let's look at the inverse. X inverse is phi of little h inverse, and this is phi of h inverse, and this is certainly an element in the direct image of h, phi of capital H. This is since the inverse of little h is in capital H, and this is because h is closed under inverses. So we've shown that the direct image is not empty. We've shown that the direct image is closed under the group operation. And we've shown that the direct image is closed under inverses. So we've shown the three things required to be a subgroup. So therefore, the direct image of H is a subgroup of K. I hope this helps. So suppose that phi from G to K is an epimorphism. That means it's a group homomorphism and it's onto. And H is a normal subgroup of G. We want to prove that phi of H is a normal subgroup of K. So what is phi of H? Well, here, phi of capital H, this is a set. It's called the direct image of H. It's the set of all the elements phi of little h such that H is in capital H. So this is called the direct image of H. Let's go ahead and prove that it's a normal subgroup of K. So we'll start by supposing that we have some K in capital K and some X in the direct image of H. And what do we need to show? Let me write it over here. We need to show that Kx K inverse is an element in the direct image of H. So if we show that, we're done. We've shown that it's a normal subgroup of K. Well, since phi is onto, there is some element which we'll call little g in capital G, such that phi of little g is equal to K, right? Because K is in capital K and phi is onto, we can find a little g such that phi of little g is equal to K. And since X is in the direct image of H, we can find some little h in capital H such that phi of little h is equal to X. So what we've done is we've created a relationship between K and X and phi, right? Because we somehow have to use the fact that H is normal in G. So we had to kind of go back and involve G somehow because we have H and that's a normal subgroup of G. So now we'll just look at Kx K inverse and see what happens. So then Kx K inverse, this is equal to, well, phi of G, phi of H, and then phi of G inverse, right? That's K inverse. And phi is a group homomorphism, so this is phi of GH G inverse. And this is certainly an element in the direct image of H, and this is because H is a normal subgroup of G, little g is in capital G, and little h is in capital H. And therefore, this element here is in capital H, so phi of that element is in the direct image. So Kx K inverse is in the direct image of H, thus the direct image of H is a normal subgroup of K. So I hope this helps. Suppose we have a sequence that converges to L. We want to prove that this limit is also equal to L. If you think of this here as a sequence, say C sub n, the terms of the sequence are called the Cesaro means or Cesaro averages. Before we prove this, let's talk about how to prove it, or in other words, how to come up with the proof. So in order to prove this, we want the difference between C sub n and L to be smaller than epsilon. So we want this here, and I'll go through this really quick. We want this minus L to be smaller than epsilon. Another way to write this is to maybe write it as a single fraction. So we want this to be smaller than epsilon. I'll go ahead and stop writing the smaller than epsilon part. So we have n copies of L, and we have n terms. So what we can do is we can group them together as follows. We can write this as a sub 1 minus L plus a sub 2 minus L plus ... plus a sub n minus L. Gotta be really careful here. Lots of nasty notation all over n. Now at some point in our proof, we're going to use the fact that our sequence converges to L. That's going to give rise to a natural number. I'll call it n sub 1. So what we can do is we can truncate this sum at n sub 1 as follows. This is a sub 1 minus L plus ... plus a sub capital N sub 1 minus L. And then we can continue it at plus the next term. The next term would be a sub n sub 1 plus 1 minus L plus ... plus a sub n minus L. Okay, and this is all being divided by n, so what we can do is we can write this over n, and then we can write this over n. Okay, and then we can use the triangle inequality a million times, and we can say that this is less than or equal to a sub 1 minus L plus dot 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 plus a sub n sub 1 minus L, all divided by little n. And we could do the same thing over here, plus a sub n sub 1 plus 1 minus L plus dot dot dot, and then plus absolute value a sub n minus L. Looks like a huge mess, but here's the idea. This first term here, if you look at the numerator, you can pretty much treat it as a constant, right? The numerator does not depend on n. So we can certainly choose little n to be bigger than some n so that this is smaller than epsilon over 2. So we got this piece, it's taken care of. And then what we'll do is we'll use the fact that our sequence converges to L to control all of these terms here, and it should work out. Let's go ahead and start the proof. And when we start the proof, a lot of what we write is going to be very similar to what I just wrote. So proof. We'll start with our hypothesis. So suppose we have a sequence that converges to L. Okay, and let epsilon be greater than 0. Since our sequence converges, that means there exists some positive integer, which again I'll call it n sub 1, such that for all little n bigger than n sub 1, the difference between a sub n and L is less than epsilon over 2. And say, why epsilon over 2? Well, if I would have kept playing with this, you would have seen that we could have taken it all the way down to epsilon, but I figured it was a bit much. Okay, so this condition here, should guarantee that this is controlled, right? That should be less than epsilon over 2 after some work. So now we have to control this. Okay, so then we can pick another positive integer. So in other words, there exists a positive integer n2, which is bigger than n sub 1. We can certainly find one via the Archimedean property, such that this term here is controlled. So in other words, it's bounded. So a sub 1 minus L plus dot 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 plus a sub n sub 1 minus L over little n is less than, and we want this to be less than epsilon over 2 for all little n bigger than capital N2. And then so then we should be set. So then for all little n bigger than capital N sub 2, what we'll do is we'll look at the terms of our sequence minus L. So we have a sub 1 plus dot 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 plus a sub n, all divided by little n. And we're going to do a lot of what we just did in the scratch work. So this is equal to, again, we can combine the fractions and write this as a sub 1 plus dot 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 plus a sub n minus, and then we can multiply this by n over n, so it's really nl, and it's all being divided by little n. And now we can group each of these little a's with an l, so we can write this as a sub 1 minus l, and I'll put it in parentheses for emphasis, plus dot 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 plus a sub n minus l. It's all being divided by little n. And now we want to involve n sub 1, big N sub 1. So I'm going to write this as follows. This is a sub 1 minus l plus dot 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 plus, and then we have a sub n sub 1 minus l, and then plus, and then here we have a sub n sub 1 plus 1 minus L, lots of notation, plus dot dot dot, plus, and then we have a sub n minus L. And all of this is being divided by little n. Now we can use the triangle inequality several times and write this as, so all of this is less than or equal to the absolute value of a sub 1 minus L plus dot dot dot, and then plus, then we have this piece. So the absolute value of a sub n sub 1, it's hard to say, minus L over n plus, we used it a whole bunch of times here, the absolute value of a sub n sub 1 plus 1 minus L plus dot dot dot, and then plus the absolute value of a sub n minus L, all divided by little n. And we know something about this term here. We know that because little n is bigger than capital N2, right, we said it here, it's less than epsilon over 2. So the first term is less than epsilon over 2. So this is less than epsilon over 2. What about this term here? Well, this is plus, and here, each of these guys is less than epsilon over 2. So how many terms do we have? Let's think about this. If you have b sub 1 to, say, b sub n, it's clear to anyone that we have n terms. A really nice way to figure out how many terms you have is to subtract. So you take the n and you subtract this one and you add 1. Watch this. N minus 1, and then what you do is you add 1. So we have n terms. Always works every single time. Say you have b sub 3 to b sub n. Well, how many terms do you have? Well, you do n minus 3, and then you add 1. So you have n minus 2 terms. Always works. So here, to figure out how many terms we have, we take the little n and we subtract n sub 1 plus 1. So we have n minus n sub 1 plus 1 terms. So we have n minus n sub 1 minus 1 plus 1 terms. Boom, these cancel. We have n minus n sub 1 terms. So this is going to be less than little n minus n sub 1 epsilon over 2's, all over n. Okay, here is the tricky part. So this is still here. We know that little n is bigger than, we said it was bigger than n sub 2. Yep, we said it was bigger than n sub 2, and n sub 2 is bigger than n sub 1. So little n is bigger than n sub 1. That's why we could do all this. But in particular, if little n is bigger than n sub 1, then little n minus n sub 1 is bigger than 0. It's a number bigger than 0. Okay? So it's this here is smaller than n. So this fraction is smaller than 1. So we have a number smaller than 1 times epsilon over 2, so that's less than epsilon over 2. Right? So we have a number smaller than 1, and it's positive. That's why we had to do this. It's a positive number smaller than 1, and it's being multiplied by epsilon over 2, so it's certainly smaller than epsilon over 2. And finally, let's not get stuck here. Epsilon over 2 plus epsilon over 2 is epsilon. And we have done it. We have proved the convergence of the Sorcerer sums, or the Sorcerer means. It's kind of a hard problem. I don't think this problem is easy. It took me a while to figure this out, maybe 20, 30 minutes. I hope that made sense.
It turns out that every cyclic group is abelian, no matter what. If it's cyclic, it's abelian. Let's actually prove this. It's really simple. So proof. Well, we need a cyclic group, so start by supposing that G is cyclic. Let's just go ahead and give it a generator at the same time. So it's generated by X is cyclic. Now we just need to show it's abelian. So we'll take two elements in G. So take any little a and little b in G. And we need to show that AB is equal to BA. Since G is cyclic, then we can write A as x to the n and B as x to the m for some little n, little m, which live inside the set of integers. Then AB is x to the n, x to the m. Well, this is just x to the n plus m. Addition is a commutative operation on the set of integers, so this is x to the m plus n. And again, we can write this as x to the m, x to the n. But wait a minute, x to the m, that's b, and x to the n, that's a. So we showed that AB is equal to BA. Thus, G is indeed an abelian group. And that completes the proof. It's very nice, almost immediate.
Okay, we're going to show that every analytic function in a domain D that is real valued is also constant. By a domain here, we mean an open connected set. All right, so proof. So we'll start by writing down, suppose f is analytic and f is real valued. So suppose, f is analytic and real valued in D. D is our domain. All right, let's rewrite f. We can always write f as u of xy plus I times v of xy. All right, now since f is real valued, it means it has no imaginary part. The imaginary part is 0, so v of xy is equal to 0. Okay. Now, since f is analytic, the Cauchy-Riemann equations hold. So the CR equations hold, everywhere in D. All right, so now let's compute the partial derivatives. Well, let's see. Well, del u, del x, since the Cauchy-Riemann equations hold, this is actually supposed to equal del v, del y. But del v, del y is 0 because v is 0, so this is equal to 0. Likewise, del u, del y, this should be equal to negative del v, del x. But v is 0, so this is also 0. So you have these partial derivatives, and they're all 0 in D at every point in D. So this implies that u and v are constant in D. And so the sum is constant. What is the sum? F is the sum. F is u plus v. So F is constant in D. Really easy proof, and it's kind of fun to do. Every finite integral domain is a field. Let's go ahead and prove this. So proof. So suppose R is a finite integral domain. So in order to show that R is a field, we have to show that every non-zero element of R is a unit. So take any little a in capital R, a not equal to 0. And we're going to consider the set of all non-zero elements of R. So set R star to be equal to the set of all non-zero elements of R. Now we're going to define a map. So define phi from R star into itself, so R star, by, let's see, phi of x is equal to ax. And the goal is to show that this is a surjection. In other words, it's onto. If we show it's onto, then since 1 is a non-zero element, that means that ax is equal to 1 for some x, and we have shown that a is a unit. Now, instead of actually showing it's surjective, since R star is a finite set, we're going to show it's injective. And since any injection from a finite set into itself is also a surjection, then we're set and the goal is accomplished. So we'll show it's injective. So claim phi is injective. So suppose phi of x is equal to phi of y for some xy in R star. What does this mean? Well, this means that ax is equal to ay. And then subtracting ay from both sides, we end up with ax minus ay equal to 0. Hence, we have a times x minus y is equal to 0. Now here is the key step in the proof. Since R is an integral domain, we have either a equals 0 or x minus y equals 0. Should be noted that a is in R star, which is also in R, and also x minus y, x is in R, y is in R, so the difference is also in R. Note, a is not 0, so x must be equal to y, right? We said a was non-zero at the beginning, so this shows phi is injective, or I'll just say 1 to 1. Now, since any injection from a finite set into a finite set must also be surjective, this means phi is also surjective. Hence, phi is also surjective. Now, since 1 is a non-zero element, it lives inside R star. And because phi is surjective, there exists an element which we can call x in R star such that phi of x is equal to 1. And what does it mean for phi of x is equal to 1? What does that mean? It means that ax is equal to 1. And this shows a is a unit. So therefore, R is a field. R is a field. So I hope this video made sense. In this video, we're going to prove that every convergent sequence is Cauchy. The proof is actually really easy. So before we do the proof, let's talk about why this should be true. So here's the idea. Let's say we have a sequence and it converges to, say, L. So what does this mean? This means that for all epsilon greater than 0, we can find a positive integer, which we can call capital N, such that for all little n bigger than capital N, the distance between a sub n and L can be made small. Well, how small? As small as we like, so smaller than epsilon. And I say as small as we like because this holds for all epsilon. So graphically, one way to look at this is to denote this axis by n, and this here can be L. And so the purple dots denote the terms. So this first dot here could be a sub 1, maybe this is a sub 2, a sub 3, a sub 4, a sub 5. And in the long run, the dots get closer and closer to L. That's what it means for a sequence to converge to L, that the terms of the sequence, a sub n, they get closer and closer to L. So what does it mean for a sequence to be Cauchy? Well, a sub n is Cauchy if, and the definition is very similar. It starts off with for all epsilon greater than 0, we can find some positive integer, which we'll call capital N, such that for all little n and little m bigger than capital N, the distance between the terms, say a sub n and a sub m, is smaller than epsilon. In other words, the terms can be made arbitrarily close. The terms get closer and closer together. How close? As close as we like, because this holds for all epsilon. So if you look at the picture here, you see that as the dots get closer and closer to L, at the same time, they get closer and closer to each other. So the terms do get closer and closer to each other. So if a sequence is convergent, then it must be Cauchy. Let's go ahead and do the proof. So proof. We'll start by assuming that we have a convergent sequence. So we'll say, suppose our sequence converges to L. Suppose A sub n converges to L. And to show it's Cauchy, we need to start by letting epsilon be greater than 0. So let epsilon be greater than 0. Now, since our sequence converges to L, so since A sub n converges to L, we can find a positive integer, capital N, such that for all little n greater than capital N, the distance between A sub n and L can be made small. Well, how small? Well, in this case, we're going to use epsilon over 2. The choice for epsilon over 2 will become clear in the next step. So we started with epsilon greater than 0, and we found a natural number such that for all little n bigger than that number, A sub n minus L is less than epsilon over 2. So now we need to look at this, A sub n minus A sub m. So then, for all little n and little m bigger than capital N, let's look at A sub n minus little a sub m. And we somehow need to rewrite this and incorporate this inequality. So the trick is to add and subtract L. So we can write this as A sub n minus L plus L minus A sub m. Right, all we did was add 0. Now we're going to use the triangle inequality on these two pieces here. So this is less than or equal to the absolute value of A sub n minus L plus the absolute value of L minus A sub m. And this is equal to, well, this piece is unchanged, it's good, A sub n minus L. And here we can rewrite this as A sub m minus L. Intuitively, we can do this because the distance between L and A sub m is the same as the distance between A sub m and L. Now we know something. We know little n is bigger than capital N. So this first term here is less than epsilon over 2. Right? Because we have this condition here. Likewise, little m is bigger than capital N. So this term here is less than epsilon over 2. And epsilon over 2 plus epsilon over 2 is equal to epsilon. So we started with some epsilon greater than 0. We found a positive integer, capital N, such that for all little n and little m bigger than capital N, the distance between A sub n and A sub m is smaller than epsilon. And so we prove that every convergent sequence is Cauchy. I hope this made sense. Let G be a group of order 5 or smaller. We're going to prove that G is actually abelian. So we're basically proving that every single group of order 5 or smaller is abelian. So let's take cases. So if the order of G is equal to 1, then G, well, its only element is the identity. So it's abelian. So 1 down, 4 to go. Now, if the order of G is a prime number smaller than or equal to 5, so if it's 2, 3, or 5, then G is cyclic by a previous argument, hence abelian. So done in that case. The only case left is when G is a group of order 4. So if the order of G is equal to 4. Let's take cases. So case 1, or rather subcases. Case 1, G has an element of order 4. So if G has an element of order 4, then G looks like this. It's the set containing E, X, X squared, and X cubed, and it's cyclic. So if it's cyclic, then it's abelian. So abelian. Case 2. Case 2 would be G does not have an element of order 4. So G does not have an element of order 4. So it does not have an element of order 4. Well, we know that the order of any element in our group G, we know that the order of any element has to divide the order of G. So it has to divide 4. So the choices are 1, 2, or 4. So we're saying that it doesn't have an element of order 4. That means that every element has order 1 and 2, 1 or 2. So then every element of G has order 1 or 2. Right? Every single element of G has order 1 or 2. Let me change colors. So this means that for all X in G, X squared is equal to E. Because if it has order 1, it's the identity, and the identity squared is E. If it has order 2, well then X squared is equal to E. So this means every element is its own inverse. Its own inverse. Hence, we can do the following. Hence, for all x, y, and g, we can look at the element xy, and we said that every element is its own inverse. So this is xy inverse. But this is y inverse x inverse. But every element is its own inverse, so this is yx. And this holds for all x, y, and g, so g is abelian. It really, really is a beautiful argument. So we've basically proven that every group of order 5 or smaller is abelian. So I think the tough case is when G has order 4, especially this case right here. G does not have an element of order 4. And again, just to go over this part again, if it doesn't have an element of order 4, then we know by a previous result that the order of x divides 4. So the choices are 1, 2, or 4, but it can't be 4, so it's 1 or 2. And that means this equation is true for every x in G. This means that every element is its own inverse, and it follows that G is abelian. So I hope this helps. In this video, we're going to prove that every Cauchy sequence is bounded. Before we start the proof, maybe let's recall what it means for a sequence to be Cauchy and what it means for a sequence to be bounded. So recall, sequence A sub n is said to be Cauchy if, for all epsilon greater than 0, we can find a positive integer, say capital N, such that for all little n and little m bigger than capital N, the terms get closer and closer together. In other words, the absolute value of a sub n minus a sub m is smaller than epsilon. And a sequence is bounded, so a sub n is bounded if we can find a positive number, say m, such that the absolute value of the terms is less than or equal to m for all positive integers, little n. Okay, so let's go ahead and start the proof. So proof. We'll start by assuming we have a Cauchy sequence. So suppose a sub n is Cauchy. And if it's Cauchy, we have this definition here. For all epsilon greater than 0, there is a positive integer such that all of this is true. So let's pick an epsilon. How about we pick 1? Well, why 1? It doesn't really matter, as you'll see when we finish the proof. So set epsilon equal to 1. Then by the definition of Cauchy, there exists a positive integer such that for all little n and little m bigger than capital N, the distance between a sub n and a sub m is less than 1. So we somehow need to show that the absolute value of a sub n is less than or equal to m. And all we have is this inequality, so we need a little bit more. So one way to do this is to fix a specific term as follows. So for example, set little m to be equal to n plus 1. Okay, and this is useful because this is bigger than n, right? And so we'll be able to use this condition here. So then, for all little n bigger than n, we have the absolute value of a sub n is equal to a sub n minus a sub little m plus a sub little m, right? And this is less than or equal to the absolute value of a sub little n minus a sub little m plus the absolute value of a sub little m. And m here is fixed. Little m is fixed. This is less than 1 plus the absolute value of little a sub m. If we like, we can write it as follows, maybe for clarity. Just to emphasize that it's fixed, this is a sub big N plus 1. So what we've done is we've found an upper bound. We've found a bound on the absolute value of a sub n when little n is bigger than capital N. That's why we needed to fix something or just set something down in stone so that we could bound this using this condition. Okay, so we have a bound. Let's write it again. So the absolute value of a sub n is less than 1 plus the absolute value of a sub big N plus 1. And this is true for all little n bigger than capital N. Now, for a sequence to be bounded, it has to be bounded for all natural numbers, right? So this is only true for little n bigger than n. So what we have to do is we have to bound the terms before these. So we're going to set big M equal to the maximum, and we can just take the absolute value of all of the terms of the sequence prior to the ones that we have bounded. So let's see, this works for little n bigger than capital N, so we can go to a sub big N. And then let's invoke or include this piece here. And so now we're set. So then, for all n, we have the absolute value of a sub n less than or equal to big M. And that completes the proof. Now, if this last step is unclear, it's because you do have to think about it. Let's actually clarify it if it's not clear. So if n is bigger than capital N, we know that the absolute value of a sub n, we know that's less than 1 plus the absolute value of a sub big N plus 1. And that's certainly less than or equal to big M, because big M is the max of all of this stuff. If n is less than or equal to n, Well, the absolute value of a sub n, that's less than or equal to the max of these guys. And that's certainly less than or equal to big M, because big M has an additional number. So in any case, the absolute value of a sub n is less than or equal to big sub M. Is this necessary to do in the proof? No, I don't think so. I think it's clear here, but it does require some thought. I hope this video made some sense. Let G be a group. Prove that every subgroup of the center of G is normal in G. Proof. Before we start the proof, let me just quickly recall what this is. What is the center of G? So the center of G, it's defined to be the set of all of the x's in G such that xg is equal to gx for all little g in capital G. In other words, the center is the set of all x's in G that commute with every element of G. And so what does normal mean in this case? Well, a subgroup H of G is said to be normal in G. We use this funny triangle. This is true if and only if for all little g in capital G and for all little h in capital H, we have GH, G inverse, also residing in capital H. So armed with this, we will go ahead and complete the proof. So we have to show that every subgroup of the center is normal in G. So we'll start by taking a subgroup of the center. So suppose that H is a subgroup of the center of G. So the inequality sign actually means subgroup. So now we have to show that H is normal in G. So we'll start by, let's see, we have to take a G in G and an H in H. So take any little g in capital G and little h in capital H. And now we have to show that GHG inverse is in capital H. So then, let's just write it down and see what happens. GH, G inverse. So we have to somehow show that this is in big H. But we know something. We know that little h is in capital H. But capital H is contained in the center of G. That means little h commutes with every element of G. In particular, it commutes with G inverse. So this is G, G inverse, H. And this step here is because H is in capital H, which is in the center of G. So H is actually in the center of G. So it commutes with every element of G. In particular, it commutes with this little guy here, G inverse. And then G inverse, that's the identity element, so we get EH. And E times H is just little h. And this is certainly in H. So we showed that for any little g in G and little h in H, that GH G inverse is actually also in H. And so this basically shows that H is normal in G. So this shows H is normal in G. So I hope that made sense. That's it. Let H be a subgroup of G such that the index of H in G is 2, and we have to prove that H is a normal subgroup of G. So this funny inequality sign here, this means subgroup. And the index of H in G, this is the number of cosets. So for us to say that it's equal to 2 means that there are 2 cosets of H in G. And we want to prove that H is normal in G. So recall that H is normal in G means that the right cosets are equal to the left cosets. So in other words, the set of right cosets is equal to the set of left cosets. Let's go ahead and start the proof. So proof. So we'll start with our assumption that the index of H and G is 2. So suppose that the index of H and G is equal to 2. Okay, this means that G has two right cosets. So let's write them down. So then the right cosets are, well, one of them is H. That's one of the cosets. You can also think of H as HE. So that's one of the cosets. And since the cosets partition G, their union has to be equal to G and it has to be disjoint. So the other coset is G set minus H, right? Because if you take the union of these two guys, you get G. So then the left cosets, are, well, as before, one of them is H. So that would be EH. And again, since the cosets actually partition G, that means that their union is G and the union is disjoint, the other left coset has to be G set minus H. Well, look at that. The right cosets are equal to the left cosets. So thus, the right cosets are equal to the left cosets, And intuitively, that's what it means for H to be normal in G. So therefore, H is normal in G. And so why are normal subgroups important? Whenever you have normality, the set of cosets, which is G mod H, actually turns into a group. So its elements are actually cosets, which is kind of cool. I hope that made sense. Every non-zero prime ideal in a PID is maximal. Let's go ahead and prove this. So proof. Recall a PID stands for principal ideal domain. A principal ideal domain is simply an integral domain where every ideal is principal. So suppose that R is a PID and I is a non-zero prime ideal. And the claim here is that I is maximal. So claim I is maximal. So we're going to let J be an ideal such that I is contained in J, which is contained in R. And the goal is to show that J is equal to I or J is equal to R. That's precisely what it means for I to be maximal. So now we're going to use the fact that R is a PID. So since R is a PID, we can write I equal to A and J equal to B for some AB in R. In other words, I is the ideal generated by A and J is the ideal generated by B. So note that A is equal to 1 times A, which is in A, which is equal to I, which is contained in J, which is equal to the ideal generated by little b. In other words, little a is in the ideal generated by b. So there exists some r in capital R such that little a is equal to RB. And just to slow down here for a minute, in case you've never seen principal ideals before, the ideal generated by A is equal to the set of all elements of the form RA such that R is in capital R. Likewise for the ideal generated by B. So that's what a principal ideal is. So note, I guess I'll stick with this color. Note, A, which is equal to RB, it's an I, which is the ideal generated by A. And this ideal is prime. Hence, what does that mean? That means that R is in the ideal generated by A, which I'll go back to now. I'll go back to calling it I, right? This is I. So R is an I, or B is an I. Okay, one of the two is going to happen. Okay. So let's take cases. If R is an I, then we can write R as equal to, say, SA for some little s in capital R. And now we should be able to rewrite A in a clever way. So then A, well, that's equal to RB, which is equal to SAB, because R is SA. And everything here is commutative, right? We're in a domain. So this is a SB. The multiplication is associative, so we can write this as A SB. Hence, A minus A SB is equal to 0. Right, equal to 0. Using the distributive property, we're simply factoring out the A. We end up with A, parentheses 1 minus SB, is equal to 0. Since R is a domain, we have A equal to 0 or 1 minus SB equal to 0. But A is not 0, because if it were, then I would be the 0 ideal. We said it was a non-zero ideal. So A is not equal to 0. Hence, 1 minus SB is equal to 0. So 1 is equal to SB. So what does that mean? Well, that means that B is a unit. So thus, B is a unit. Right? B is a unit. And so if B is a unit, we can do the following. So then 1 can be written as B inverse because it exists, because B is a unit, times B. This is an element of R, and this is B, so it's in the ideal generated by B, which is equal to J. So J contains 1, hence for all R in R can be written as R times 1. This is an element in R. This is an element in J. Therefore, because J is an ideal, this is also in J. And so R is a subset of J, but J is a subset of R, hence J is equal to R. And I'm showing a lot of detail here on purpose. A lot of this is pretty trivial, perhaps, but hopefully it's helping. So we've taken the first case if R is in I. Let me switch colors. Now let's take the case if B is in I. I believe this case should be shorter. I actually haven't done this in a while. Let's see. So if B is an I, here's what we're going to do. So we have to show J is equal to I. So let's show J is a subset of I. So take any X in J. Then we can write X as RB for some R in R. Okay, for some R in R. Then X is equal to RB. Now R is in our ring R. B is an I. Because I is an ideal, that means X is an I. So we took an X and J, and we showed that X was an I. So J is a subset of I, but we showed at the beginning, we assumed that I was a subset of J. Hence, J is equal to I. So in any case, we either have J equal to R or J equal to I. This shows I is maximal. And so that's how you prove that every non-zero prime ideal of a PID is maximal. I hope that video made sense. If G is abelian, then every subgroup of G is normal in G. This is a pretty easy proof. Let's go ahead and do it. So suppose G is abelian, and let's take a subgroup, let's call it H, and let H be a subgroup of G. And the claim is that H is normal in G. So claim that H is normal in G. Well then, for all G in G, and for all little h in capital H, we just have to look at GH inverse and show that this element is in H. Well, GH and G inverse are all elements of G, right? H is a subgroup of G, so little h is also in G. G is abelian, so these commute. And GG inverse, that's E. And EH, that's just H. So this is certainly in H. And that's it. So this shows that H is a normal subgroup of G. Really, really easy proof. In this video, we're going to prove that every P group has non-trivial center. Recall that a P group is a group whose order is a power of a prime. So proof. We'll start by assuming that we have a P group. So suppose G is a P group. Say that it has order P to the n, where P is prime, and n is greater than 0. To prove this, we're going to use the class equation. So by the class equation, we can write G, the order of G rather, is equal to the order of the center plus, then we have the order of G divided by the order of the centralizer of A sub 1 plus plus the order of G divided by the order of the centralizer of A sub k. All right, let's pause a moment and talk about what these guys are. So recall that we can write the order of G that's equal to the index of the centralizer of A sub I in G times the order of the centralizer of A sub I. And so if we divide both sides by the order of the centralizer, we get that the order of G divided by the order of the centralizer is equal to the index of the centralizer of A sub I in G. And what is this? This is the order of the conjugacy class of A sub I. And in particular, this conjugacy class has order greater than 1. So this is the order of the conjugacy class of A sub I. And this is a number bigger than 1, right, by the class equation. So this equation here tells us that the index is a divisor of G, which is P to the n. This knowledge here from the class equation tells us that the index is a number greater than 1. So this is a number, it's bigger than 1, and it divides P to the n. So this is a power of a prime, right? So this is a power of a prime. So we can write what we have over here as P to the n equals the order of the center of G plus, and these are all powers of primes. So this is P to the R1 plus ... plus P to the RK. So now we're done, right? P divides this little guy, P divides this, it divides everything in between, therefore P must divide the order of the center. So we have a prime number, and it's dividing the order of the center of our group. So that means that the order of the center of our group is not equal to 1. In particular, it's bigger than 1. So the center is non-trivial, right? And that's it. That's how you prove that every P group has non-trivial center. But you do have to know that this is a number bigger than 1, and that follows from the fact that it's the order of the conjugacy class of A sub I. And in the class equation, we specifically mention that these are the conjugacy classes with size bigger than 1. So it's a number bigger than 1. It divides P to the n. So it must be a power of a prime. So these are all powers of primes. So P divides all of these guys. It divides this. Therefore, it must divide the order of the center. And that's it. I hope that made sense. Let G be a group, little g in G, and n a natural number. We have to prove that if G to the n is equal to the identity element, then the order of G divides n. So proof. First, let me say that to show that the order of G divides n, this is the same thing as saying, so we need to show that n is a multiple of the order of G. So if we show that n is a multiple of the order of G, that means that the order of G divides n. They are exactly the same thing. So we'll start by supposing that G to the n is equal to E. Well, that means that G has finite order. So G has finite order. Let's give it a name, say M. So M will be equal to the order of G. So we just need to show that n is a multiple of m. So if we show that, we are done. So by the division algorithm, by the division algorithm, there exists unique integers r and q such that we can write n as mq plus r, with r being strictly less than m and greater than or equal to 0. So now, or note, E is equal to G to the n. But n is mq plus r, so this is G to the mq plus r. And this can be written as G to the mq times G to the r. We can write the first factor as G to the m to the q, and the second factor we'll leave it as G to the r. Well, m is the order of G, so this is e to the q, G to the r. E to the q is e, so we get e, G to the r, and e is the identity, so we just get G to the r. So G to the r is equal to e. But m is the smallest positive integer such that G to the m is equal to e. And we know that r is smaller than m. So this forces r to be equal to 0. Right? And r can be 0 because it's greater than or equal to 0. So we basically use the minimality of m to force r to be equal to 0. So if r is 0, that means that n is equal to mq plus 0. So n is equal to mq. So n is a multiple of m. So m divides n. So the order of G divides n. And that is the proof. I hope this helps. It's a nice proof. We have a group G, and we have to prove that the center of G is a subgroup of G. Before we do the proof, let me just recall what the center is. So recall, the center of G is the set. It's all the x's in G that commute with every other element of G, or commute with every element of G. So not just every other, it commutes with itself as well. So xg is equal to gx for all G and G. That's what it means to be in the center. So if you have an element and it's in the center, it commutes with everything in your group. Okay, so to prove that this is a subgroup, that's what this symbol means, subgroup, we have to show three things. We have to show that the center is non-empty, we have to show that the center is closed under the group operation, and we have to show that the center is closed under inverses. So the first thing we'll do is show that the center is non-empty. So note, for all little g in capital G, the identity element commutes with every single element, right? It commutes with little g. So EG is GE. That's precisely what it means for little e to be inside the center. Hence, the center is not empty, right? Because the identity element commutes with every element of G, and so it's in the center, so the center is not empty. Now we have to show that the center is closed under the group operation. So we'll take two elements in the center. So suppose x and y are in the center. And that means that x commutes with every element of G, and it means that y commutes with every element of G. Now we have to show that the product xy is in the center. That means the product commutes with every element of G. So then, for all little g and g, we have to show that xy commutes with little g. So xy times little g. Now we're going to start being a little bit abusive here. I won't write all the reasons down. It just becomes way too tedious. We can use associativity here. This is x, yg. And now we can commute. These commute. You know, y and g commute. Why does that happen? Well, because y is in the center, right? So that's a key step. So y commutes with every little element, with every little g, because y is in the center. It commutes with everything inside G. Now we'll use associativity again. So we have xg, y. I didn't write down y, but that was associativity. Okay. And then x is in the center, so x can commute with little g. So this will be little g times x times y. And this is because x is in the center. Right? It's also in the center. We can use associativity one more time. So we have g, x, y. That was associativity. And look, we have xy times little g is equal to little g times xy. For all g and g, that's precisely what it means for the product xy to be inside the center. So we're done with this step of the proof. We have shown that it is closed under the group operation. Let's go ahead and show it's closed under inverses, and then we are done. So suppose x is in the center of G. This means that x commutes with every element of G. So then, for all little g and g, we want to show that the inverse of x, which is in G, right? G is a group. We want to show that the inverse of x commutes with little g. So let's see how we can do this. We somehow need to involve x in this. So maybe we can do something like this. X inverse, g, how about x inverse? We can do that, right? And I'll put this in parentheses here. Okay, so we're skipping a lot of steps here. A lot of associativity was used there, right? And this is okay, right? Because this over here, this is E, right? So we really didn't do anything. All right, now we can use the fact that x is in the center. So this is x, little g, x inverse. And this step here is because x is in the center of G. Okay, x is in the center of G. And now over here, this is going to give us E. So we're going to get E, G, x inverse. Right, being really abusive here with the associativity. Very, very abusive stuff. And then E times little g, well, that's just going to be little g, x inverse. And look, we showed that if we take x inverse times little g, we get little g times x inverse. And this holds for all g and little g. This is exactly what it means for the inverse of x to be in the center. So we showed that the center was not empty. How? Because it contains the identity. We showed that the center was closed under the group operation, and we showed that the center was closed under inverses. So therefore the center is a subgroup of G. Beautiful, beautiful proof. I hope this helps someone out there who's messing around with the center of a group. Okay, we're going to show if G is a group and we have two elements in G and we take their product, that the inverse of the product, xy, is y inverse x inverse. So proof. So suppose G is a group. We'll try to be really careful here. Suppose G is a group and x and y are in G. Now, in order to prove this, we somehow need to justify writing down x inverse and y inverse. So since G is a group and x and y are in G, the inverses also live inside G. So let me just say then x inverse and y inverse are in G, right? Because it is a group, it is closed under inverses, so everything is nice there. Okay, now we'll focus on proving our statement. So then, what we'll do is we'll take xy, and we have to show that if we take xy and we multiply it on the left by this, we get e, and if we multiply it on the right by this, we also get e. So we'll start by multiplying this on the right. So y inverse, x inverse. Now we'll very carefully use associativity. So here we have this term, and this term. We're going to use associativity on these three terms. So it's x, parentheses y, parentheses y inverse, x inverse, parentheses, parentheses. The step was by associativity. Now we'll do it again, but we'll use it on these three terms. So really careful stuff here. Very delicate. This is x, y inverse, parentheses, x inverse, parentheses, parentheses. Again, by associativity. Later on, we can start to be sloppy, and we will, but for now, in these more basic proofs, we'll stick to being really precise. This next step, this is equal to the identity, right? So this is E x inverse. And this step, it's kind of silly, but I'll write it. Why is this the identity? Well, this is because y inverse is the inverse of y. E times x inverse, well, E is the identity. So this is x inverse. And this step is because E is the identity. And the last step, well, this is equal to E, and this is because x inverse is the inverse of x. Let's reflect on what we just did. So we used associativity not once, but twice, right? And very, very carefully. And we also used the fact that y inverse was the inverse of y, and that x inverse was the inverse of x. And we also used the fact that E was the identity. So there is a lot going on here. So it's important to understand why every single step works. And later on at some point, we'll stop writing all these reasons. They just become obvious. All right, now let's go the other way. So likewise, and we'll continue to be careful. So likewise, if we take y inverse, x inverse times xy, we can use associativity. We'll use it on this term, and this term. So it'll be y inverse, x inverse, sorry, this term, and then xy. Right, so this term, and this term. So this is by associativity. Then we'll do it again, except now we're going to look at this term, and this term. So it'll be y inverse, x inverse x, y, and then don't forget these parentheses out here. Very tedious stuff. By associativity. And let's keep going. This is y inverse, e, y. And this step here, this is because x inverse is the inverse of x, and this is equal to y inverse y, and this is because E is the identity, and finally this is equal to E, and this is because y inverse is the inverse of y. A lot of writing in such a easy proof. If you don't show any of the steps and you don't use associativity or justify anything, it just takes a couple seconds. But when you actually go through it and you think about every little step, you really have to be careful. So again, we used associativity twice. We used the fact that x inverse was the inverse of x and that y inverse was the inverse of y, and we used the fact that E was the identity. So we showed that if we multiply y inverse x inverse on either side of xy, we get the identity. So we showed that it is the identity. So therefore, the inverse of xy is y inverse x inverse. So I hope this helps someone out there. Prove that the function defined by f of x equals 1 over 1 plus x squared is uniformly continuous. Before we do this proof, let's recall what it means for a function to be uniformly continuous. So recall f from, say, a to r is uniformly continuous. Uniformly continuous, I'll just put cont, if for all epsilon greater than 0, we can find some positive number delta greater than 0, such that for all x and y in A, with the distance between x and y being less than delta, we have the distance between f of x and f of y being smaller than epsilon. Okay, that's what it means for a function to be uniformly continuous. Went through that really quick, but hopefully it's just a quick refresher. So proof. So in order to start the proof, we have to use this definition. So we have to start by letting epsilon be greater than 0. So let epsilon be greater than 0. And then we have to find a delta. So this is the part you usually figure out on your own on the side. Let's choose delta equal to epsilon over 2. I figured this out beforehand because I've done this problem before, but you'll see as we go through it, as we go through the proof, we're kind of going to figure it out as we go through it. So then, for all x, y, and r, with the distance between x and y less than delta, what we'll do is we'll look at the difference of f of x and f of y, and we'll show it's smaller than epsilon. So then we have f of x, which is 1 over 1 plus x squared, minus f of y, which is 1 over 1 plus y squared. And the obvious thing to do here is to combine the fractions. So we can do that by finding an LCD. So I'll skip some steps here, but this is 1 plus y squared minus 1 plus x squared over, and then here we have 1 plus x squared, 1 plus y squared. And then some stuff here should cancel in the numerator. Looks like the 1's cancel, and so we're left with y squared minus x squared over 1 plus x squared, parentheses, and then parentheses 1 plus y squared. And in all of this, we still have the absolute value. So this can be written as follows. This is really the absolute value of y squared minus x squared. And you can put these guys in the bottom in absolute values too. I'll go ahead and do that. So 1 plus x squared. And then here we have the 1 plus y squared. Lots of absolute values and 1. So that's an absolute value line. That's a 1. Okay, I don't like y squared minus x squared, so you can rewrite this as the absolute value of x squared minus y squared. You don't have to do that. For me, it just makes more sense. So you have 1 plus x squared. I'll write these smaller. And then 1 plus y squared. Okay, this is the difference of squares. So far we've done nothing tricky. This is the natural thing to do. In fact, this is how I figured out the problem. I just started writing stuff down and then seeing what happens. So the difference of squares, you can write this as x plus y with absolute value, and then x minus y. And this is all being divided by 1 plus x squared times, and then here we have 1 plus y squared. And just to make the point, we have x minus y here, x minus y less than delta. So this part here is kind of taken care of. So I'm going to write this as the absolute value of x plus y over, and then here we have 1 plus x squared, and then here we have 1 plus y squared. And then I'm going to put this on the outside over here. So if we can show that this first term here, this first factor is bounded, in other words, it's less than some number, we are set because we know that this is less than delta. So what we'll do is we'll use the triangle inequality in the numerator. So this is less than or equal to, so this piece is going to hang out, so I'm going to put parentheses here, the absolute value of x over 1 plus x squared times, and then 1 plus y squared. That's a y. Plus the absolute value of y over, and then here we have 1 plus x squared times, and then here we have 1 plus y squared. And all of this is being multiplied by the absolute value of x minus y. So we need to make this smaller than a number. One thing we can do is we can drop the y squared. So this is less than or equal to, so we'll drop the y squared here. We just want x's here, so it's less than or equal to the absolute value of 1 plus x squared. And then over here we'll drop the x squared, so this is plus y over 1 plus y squared. And then we still have the absolute value of x minus y. And this is the part that took me longer to do, I think. This whole fraction here is less than 1. And this whole fraction here is also less than 1. And we'll prove that at the end of this video. So we have 1 plus 1 times the absolute value of x minus y. So this is equal to 2 times the absolute value of x minus y. And we know that the absolute value of x minus y is less than delta. So this is less than 2 delta. And we said delta was equal to epsilon over 2. So this is 2 times epsilon over 2, which is equal to epsilon. And that completes the proof. So this is really, the proof is actually how I figured it out. The natural thing to do when you get here, though, is to use the triangle inequality. So after you do a couple of these, you'll notice it's a reoccurring idea. Let's go ahead and prove why this step was true really, really quickly. So we're going to prove, so claim, that if you have the absolute value of a over the absolute value of 1 plus a squared, the claim is that this is less than or equal to 1. And this is just like a proof sketch. So if a is less than or equal to 1, then the absolute value of a over the absolute value of 1 plus a squared, well, the absolute value of a is less than or equal to 1. So this is less than or equal to 1 over the absolute value of 1 plus a squared. And then we can just simply drop the a squared. This is 1 over 1, which is equal to 1. So it's less than or equal to 1. If a is bigger than 1, then we have the absolute value of a over the absolute value of 1 plus a squared. And this is less than or equal to the absolute value of a over the absolute value of a squared by dropping the 1. And this is equal to the absolute value of a over the absolute value of a squared, which is 1 over the absolute value of a. Notice that in all of this, a is not 0 because it's bigger than 1. And a is bigger than 1, so it's positive, so this is just 1 over a. And since a is bigger than 1, if we divide this inequality by a, we get 1 over a less than 1. So this is less than 1. Boom. So in any case, it's less than or equal to 1. And that's how we were able to do this very, very, very key step. I just didn't want to have to do all of this in the middle of the proof. So hopefully that video was helpful, and hopefully it made sense. That's it. Prove that if phi from G to K is an onto homomorphism, then K is isomorphic to G mod the kernel of phi. So what is the kernel of phi? Well, it's the set of all elements in G such that phi takes little g and sends it to the identity element in K. So it's all the g's that phi maps to the identity element. Okay, so to prove this, we have to come up with a homomorphism that is one-to-one and onto. And then we're done, right? Because we've come up with an isomorphism. So first we have to come up with something. For notation, so I don't have to keep writing cur phi, set h equal to the kernel of phi. And now we're going to define our function. So define psi, and we'll go from g mod h, so g mod the kernel, into k, by, well, psi takes a right coset, which we'll call hx, and sends it to phi of x. So we actually have to show 4 things. We have to show 1, that phi is well defined, 2, it's a homomorphism, 3, it's 1-to-1, and 4, it's onto. We don't necessarily have to do them in that order, but we certainly should show that it's well defined first. So 1, claim psi is well defined. What does that mean? It est if we have 2 cosets, hx and hy, and they're the same, then we should have the same result. We should have that phi of x is equal to phi of y. That's what we have to show. So let's show that. Let me use a different color. So suppose hx is equal to hy. So this means that x, y inverse is in h. That's what it means for hx to be equal to hy. Right, that's exactly what it means. Now h is special. H is the kernel of phi. So maybe let's look at phi of this element and see what happens. So then phi of x, y inverse, well, this is equal to the identity element in k, because x, y inverse is in the kernel. Remember, h is the kernel of phi, which is the set of all g's in G, such that phi of G is equal to the identity element in K. So if this element is in H, then phi of this element is the identity element in K. We can rewrite the left-hand side of this. So phi of X, phi of Y inverse. We can do that because phi is a group homomorphism. And then we can rewrite this as follows. Phi of x equal to, multiplying both sides on the right by phi of y, we get phi of x equals phi of y. And we started with hx equal to hy, and we showed that phi of x is equal to phi of y. So we're done here. So psi is well defined. Well defined. Let's go ahead and show that it's a group homomorphism. That should be pretty easy. So 2, let me go back to my original color. So for any 2 right cosets, let's say hx and hy in the quotient group G mod h, let's look at psi of hx times hy. Well, this is just psi of hxy. That's how you multiply cosets. And this is phi of xy. But phi is a group homomorphism, so this is phi of x, phi of y. Phi of x is psi of hx. And phi of y is psi of hy. So we showed that for any 2 cosets, psi of hx times hy is equal to psi of hx times psi of hy. So psi is a group homomorphism. 2 down, 2 to go. We still have to show it's onto and that it's 1-to-1. Let's go ahead and show it's onto. So suppose we have some k in capital K. And since you can't see it anymore, let me go ahead and write down psi again. So psi took g mod h into k, and it was defined as psi of hx equals phi of x. So we took some k in capital K, and we have to produce a coset that psi takes back to k. So suppose k is in k. Now since phi is onto, there exists some x in g. Keep in mind in all of this, phi went from g to k. So it's onto, k is in capital K, and so there is some little x in g such that phi of little x is equal to k. So then psi of the coset hx, well, by definition of psi, that's just phi of x, and so that's equal to k. So this shows that psi is onto. It's so easy to mess up the words psi and phi. I hope when I'm done with this video and I listen to it before uploading it, I didn't mess up. So easy to mess up. 4. We have to show it's 1-to-1. So suppose psi of hx is equal to psi of hy for some right cosets hx, hy in the quotient group g mod h. Well, this means that psi of x is equal to, phi of x is equal to phi of y. Now, we don't know anything about, whether phi is 1-to-1. We just know it's onto, so we need to do something else here. One thing you can do is rewrite this. So then, this is actually phi of x, phi of y inverse, right? Just multiplying on the right by phi of y inverse. And this is equal to the identity element in K. Now, phi is a group homomorphism, so we can rewrite this. So this becomes phi of x y inverse equal to the identity element in K. So this means that x y inverse is in the kernel of phi, which is h, right? We said that the kernel of phi is h. So x y inverse is in h. That's precisely what it means for the right cosets hx and hy to be the same. So we started with psi of hx equal to psi of hy, and we showed that hx is equal to hy. So this shows that psi is 1-to-1. So we've shown that, let's go back up, we showed that psi was well defined, took care of that. We showed that psi was in fact a group homomorphism. We showed that psi was onto, so we did that right here. And we showed that psi was 1-to-1. So we've basically shown that psi is an isomorphism. So therefore, psi from g mod h to k is an isomorphism hence g mod h is isomorphic to k. Well, h, we said that was the kernel of phi, so g mod the kernel of phi is isomorphic to k. And that is the first isomorphism theorem. Let me put it in a box from abstract algebra. So I hope this helps. Hey YouTube, in this video we're going to prove that the square root function is continuous everywhere it's defined. So this function is defined on the set bracket 0, infinity. So first we'll prove it's continuous at 0, and then we'll give a proof to show it's continuous at every positive number. Therefore, it will be continuous everywhere in its domain. Before we do the proof, recall the definition of what it means for a function to be continuous at a number. So we say f is continuous at x equals c if, for all epsilon greater than 0, we can find some delta bigger than 0 such that for every real number x with the property that the distance between x and c is less than delta, we have the distance between f of x and f of c less than epsilon. So that's the definition we're going to use to do both proofs in this video. Okay, so first let's do the proof for 0. Okay, so proof. I'm going to go a little bit fast because it's 2 proofs in one video. So before we do this proof, we have to figure it out. So I haven't actually figured it out yet, so let's go over here and figure out how to do it. And then we'll write the proof over here. So we know we have an epsilon greater than 0, and we're going to need delta. Okay, we need delta. So we know that the distance between x and c is less than delta. So c is 0, so we know that x minus 0 is less than delta. And we want this to imply f of x minus f of c less than epsilon. Well, f of x is the square root of x. F of c is f of 0, so it's just the square root of 0. We want this to be less than epsilon. So we have the absolute value of x less than delta, and we want this to tell us that the absolute value of the square root of x is less than epsilon. Well, we can drop the absolute value here, so we just get square root of x less than epsilon. And then you can square both sides, we get x less than epsilon squared. Okay, so what we can do is we can choose delta to be epsilon squared in our proof. Okay, now let's go back and formalize our proof. So we'll start the proof by letting epsilon be greater than 0. Now we're going to choose our delta, so choose delta equal to epsilon squared. Then for any x, and x here is in this interval here, with the distance between x and 0 less than delta, we have, and now we have f of x, so f of x is the square root of x minus the square root of 0. Okay, so that's equal to the square root of x, or we can drop that, and we know x is less than delta, right? So this is less than the square root of delta, but delta is equal to epsilon squared, so this is the square root of epsilon squared, and that's just epsilon, right? It's actually the absolute value of epsilon, but epsilon's positive, so we're good. Good stuff. So this proves that f is continuous at x equals 0, right? So we started with an epsilon greater than 0, we chose our delta, and then for any x in this interval where the distance between x and 0 is less than delta, we showed that the distance between f of x and f of 0 was less than epsilon. So that's the first proof. All right, the second proof. Now we have to prove that it's continuous at all positive numbers c. Okay, so I'm going to scroll down a little bit. I think this one's going to be harder. So let's see, scratch. So again, we have our epsilon greater than 0, and we need to find a delta greater than 0 such that whenever the distance between x and c is less than delta, that needs to tell us that the distance between the square root of x and the square root of c, right, f of x minus f of c, that needs to be less than epsilon. So this is going to take some trickery. So my thinking here is that here we have x minus c, and here we have the square root of x minus the square root of c, right? So what I'm thinking is maybe we can multiply this by the square root of x plus the square root of c over the square root of x plus the square root of c. We're basically rationalizing the numerator. And I think this might work. Let's see. This is a minus b, a plus b. So that's a squared minus b squared, right? Difference of squares. So this is going to be x minus c. All of this is an absolute value. And then here we have the square root of x plus the square root of c, right? So then the numerator is less than delta, right? So this is less than delta. Then we still have the stuff on the bottom, the square root of x plus the square root of c. Now this piece here, this square root of x, it's a positive number or it's 0. In any case, this fraction is less than or equal to delta over the square root of c. And this is good because c is not 0, right? C is not 0. And so now we want this to be less than epsilon. So I think if we choose delta to be epsilon times the square root of c, that's exactly what's going to happen. So let's try it. Let's go ahead and formally prove it. So we'll start by letting epsilon be greater than 0. And we're going to choose our delta to be epsilon times the square root of c. And this is a positive number because c is a positive number. Okay. Then, for any x in 0 infinity with the distance between x and c less than delta, we have, and so now we look at the distance between f of x and f of c. So that's this here, square root of x minus square root of c. So square root of x minus square root of c. And we can rationalize this, and when we do that, we did it here, so I won't do it again. You end up with the absolute value of x minus c over the absolute value of the square root of x plus square root of c. You don't really need the absolute value on the bottom, but I'll go ahead and put it, right, because the bottom is going to be positive. Okay, and this is less than delta, right, because this is less than delta, over, and then here I'll do it in steps, square root of x plus square root of c. Now we'll drop that square root of x, right, because this fraction on the left is smaller, right, because the bottom is bigger. So you can drop that square root of x. That's key. So here you have square root of c, and delta is equal to epsilon square root of c over square root of c, and these cancel, and so you get epsilon. And that completes the proof. I'm really happy that this worked out. I kind of like doodled it on the side before I made the video. I thought, oh, I think it'll work. Let me just try to make the video, and if it doesn't work, I'll just delete the video. But it worked out, so good stuff. I hope this video has been helpful, and that's it. Hi everyone, in this video we're going to prove that this piecewise function is differentiable for every real number x. So for all x in the set of real numbers. Let's go ahead and go through it, so proof. So the easy part is to mention that it's differentiable if x is not equal to 0. So note that if x is not equal to 0, then using the definition of the piecewise function, then in this case f of x is equal to x squared times the sine of 1 over x. And this is differentiable because it is a product of differentiable functions. So is differentiable, because it is the product of differentiable functions. So it's kind of just an observation, but an important one because it is the product of differentiable functions. And we're really not expected to prove that each factor in this product is differentiable. It's kind of assumed, so it's not really the main goal of this problem. So it's a product of differentiable functions, hence it's also differentiable. The important part of this problem is to prove that it's differentiable at x equals 0. So to do that, we'll use the definition of the derivative. So I'm going to write that up here on the top left corner. So recall that f is differentiable at c, and we write that as f prime of c, if the following limit exists. So we take the limit as x approaches c of f of x minus f of c, all divided by x minus c. So if this limit exists, then we say the function is differentiable, and we call the result of this limit the derivative of the function, right? That's the definition of the derivative. You can also use the alternate definition with the x plus h, but let's go ahead and use this one in this problem. So in this problem, we have to show that this limit exists when c is equal to 0, right? Because we want to show it's differentiable at 0. So let's consider this limit. So consider the limit as x approaches 0 of f of x minus, and then it's f of 0 because our c is 0, and on the bottom we have x minus 0. Okay, let's keep going. This is equal to the limit as x approaches 0. So f of x, well, when you're taking a limit, x as x approaches 0, x is not equal to 0. I don't know if you remember the definition of a limit. The if part had something like this: x minus c less than delta, and the actual definition of a limit. And you'll notice that x can't be equal to c here, because if it is, you would get 0 less than 0. So x is not equal to c. In this case, x is not equal to 0. So that's important because that tells us that we use this piece here for f of x. So it's x squared sine of 1 over x. So that's the reason that we use that piece, because in the definition of a limit, x is not actually equal to the number you're approaching, right? It's just really, really close to it, but not equal to it. Minus f of 0, well, that's just 0, again, by definition, right? When x is equal to 0, our function is equal to 0. And on the bottom, we have x minus 0. So this is equal to the limit as x approaches 0 of x squared times the sine of 1 over x all over x. Okay, and then we can cancel one of the x's. So this is equal to the limit as x approaches 0 of x times the sine of 1 over x. And now we just have to show that this limit exists. And it does, and it's equal to 0. So, and it's very easy to prove, and we'll do it with the squeeze theorem. So note, if we just look at the sine of 1 over x, I'll do it in pieces. We know sine is bounded by 1. That means it's less than or equal to 1 and greater than or equal to negative 1. Now here we have x times the sine of 1 over x. So multiplying everything by x, we have minus x less than or equal to x sine of 1 over x less than or equal to x. And now we can use the squeeze theorem. So since we take the limit, or let me just say note again, if you take the limit of the left-hand side, so this piece here, well, you can just plug in 0, so you get negative 0, so it's 0. And if you take the limit of the right-hand piece of the inequality, you also get 0. So we have the following three conditions. We have that this function here is bounded by x. We have that this piece here goes to 0, this piece here goes to 0, so this goes to 0, this goes to 0. Therefore, by the squeeze theorem, what's trapped in the middle, that also goes to 0. So to say it formally, I'll just say thus: by the squeeze theorem, squeeze THM, our limit is equal to 0. So this means, so what did we show? This means that the limit as x approaches 0 of f of x minus f of 0, let's reiterate what we did, over x minus 0, we said that this is 0. So this means that f is differentiable, right? Because the limit exists. It's equal to a number, so the limit exists. That means that f is differentiable at x equals 0. And furthermore, f prime of 0 is actually equal to 0. So we've shown that f is differentiable for every single real number, and that completes the proof. So I hope this video has helped someone out there who's learning how to write proofs. If it's helped, leave a comment, subscribe, like, all of that good stuff. Thanks for watching. Take care. Hi YouTube. In this video we have a sequence of functions, and we're going to prove that it converges to 0 pointwise on the interval 0, 1. So first, let's recall what it means for a sequence of functions to converge pointwise. So in this problem, we have a sequence, f sub n, and it's defined on the interval 0, 1, that's the domain, into the set of real numbers r, that's the codomain. And we'll say that a sequence of functions, f sub n, converges to f pointwise on 0, 1 if for every epsilon greater than 0 and for every x in our set 0, 1, we can find some positive integer n. Notice that it could depend on both epsilon and x, such that for all little n bigger than capital N, the distance between f sub n of x and f of x is less than epsilon. So let's go ahead and prove this. So proof. Actually, before we prove it, we have to figure out the proof. So let's do the scratch work over here. So scratch work. All right, so we start the proof by picking an epsilon greater than 0 and taking a number x in 0, 1. So the easiest case is if x is equal to 0. So if x is equal to 0, then f sub n of 0, that's just going to be 0 because you get n times 0 up here, and then so the whole thing is 0. In this case, we can choose any n, and then we look at the difference between f sub n of 0 and 0, which is the limit. So we get 0 minus 0, which is 0, and that's less than epsilon. So if x is 0, we can choose any n, and the proof is complete. If x is not equal to 0, right, if x is not equal to 0, then we look at the difference f sub n of x and 0, and we want this to be less than epsilon. This can be rewritten as the absolute value of nx e to the negative nx, and we want that to be less than epsilon. X is in 0, 1, so we can drop the absolute value because x is positive, right, because x is not 0. So this can be written as nx, and furthermore, you can bring down the exponential function, e to the nx, and you want this to be less than epsilon. So if you were trying to figure this out for the first time, this is probably where you would have the most difficulty, right? So my thinking here is that we can use the Maclaurin series for e to the x. Recall that e to the x is equal to 1 plus x squared over 2 factorial plus dot, dot, dot. And the thinking for this is that here you have an exponential function, and here you have a polynomial function. And so you have to get rid of the exponential function. So you have to compare the exponential to a polynomial. Well, this is one easy way to do it. So let's write the Maclaurin for e to the nx. We can do that by replacing all of the x's with nx. So it'll be nx quantity squared over 2 factorial plus dot, dot, dot. And which one do we compare it to? Well, it's up to us, but I think it might be more beneficial to compare it to something greater than degree 1, because we have a degree 1 polynomial in the numerator. So let's compare it to this one. So this infinite sum is certainly greater than nx quantity squared over 2 factorial. And now in our inequality up here, we have e to the nx in the bottom. So let's solve this for 1 over e to the nx. We can do that in one move by multiplying by the reciprocal of the right-hand side and dividing by e to the nx. So we have 2 over the quantity nx squared greater than 1 over e to the nx. I'm going to write that again as 1 over e to the nx less than 2 over nx quantity squared. All right, let's rewrite this jumbled mess up here. So we have, let me change color here. So this is nx e to the nx. You can write this as nx times 1 over e to the nx. So this is less than, right? This piece here is the same as this piece here. So this nx here hangs out, and you can replace that circled piece with 2 over nx quantity squared. And this is 2 over nx. And we want this to be less than epsilon, right? Our goal is to find a positive integer n. So now we can solve for little n, right? We can multiply both sides by little n. So we get 2 over x less than n epsilon. Divide by epsilon. That gives us 2 over epsilon x less than n. So n is bigger than 2 over epsilon x. So then in the proof, we can choose our capital N to be greater than 2 over epsilon x, right? Epsilon is greater than 0. X is not equal to 0, so this number makes sense, right? This is a real number. So via the property of Archimedes, the Archimedean property, we can choose a natural number that is bigger than this one. So given any real number, you can find a natural number that is bigger. It's called the Archimedean property, and that's how we're able to choose our capital N. So let's go ahead and carefully write the proof. So we'll start the proof by letting epsilon be greater than 0 and choosing an x in 0, 1. So let's do that. So we'll let we'll let epsilon be greater than 0, and we'll let x be in 0, 1. Okay, let's take cases. Let's take cases. So if x is equal to 0, well, if x is equal to 0, we did it here. We can choose any n, right? So choose any n. Choose any positive integer n. It doesn't matter, right? It does not matter. Then for all little n bigger than capital N, right? So for all little n bigger than capital N, we look at the difference f sub n of 0 and 0. And we know that's 0 minus 0, which is equal to 0, which is less than epsilon. And so the proof is done if x is equal to 0, right? So it's trivial. But notice we formalized it pretty well here, right? If x is 0, we chose our n. Then for all little n bigger than n, we look at this difference. So it's been proven for x equals 0. If x is not equal to 0, right, if x is not equal to 0, we're going to choose, I believe we said n greater than 2 over epsilon x. Let me just go down there and look. Scroll down and look. Yes. See, we had to use a different n, right? We had to use a different n whenever x is not equal to 0, right? We're showing pointwise convergence, so n can depend on x. So it's a different n. When x is 0, we can use any n. In this case, we have to choose n bigger than this. So I can't write this down if x is 0, right? So there's an issue, right? There's an issue. So choose n greater than 2 over epsilon x. Then for all little n bigger than capital N, we have to look at the difference. So f sub n of x minus 0. And we know that's nx e to the negative nx minus 0, so just that. And we know we can drop the absolute value and write it like this, nx over e to the nx. And we know we can write this as nx times 1 over e to the nx. And we can use this inequality here as we did before. So this is less than nx times 2 over nx quantity squared, which is equal to 2 over nx. So let's be a little more formal here. After this, in our scratch work, we did some backwards thinking to find n, right? We solved for n. So let's go back and do that a little more formally. So since little n is bigger than capital N, which is bigger than 2 over epsilon x, right? Let's go ahead and solve this for 1 over n so we can make it less than epsilon. So this means that little n is bigger than 2 over epsilon x. Right, so we're going to solve this for 1 over n because the n's on the bottom. Okay, so I'm going to multiply by the reciprocal here. So we get epsilon x over 2 times n bigger than 1. Then divide by n. So we get epsilon x over 2 greater than 1 over n. So 1 over n is less than epsilon x over 2. So what we're doing here is we're formalizing the proof, right? We're making sure we carefully show that this quantity is less than epsilon. To do that, you look at the n, it's on the bottom, so you solve for 1 over n, right? So now let's go back and restate what we did. So thus, I'm going to rewrite this piece. So the difference between f sub n of x minus 0, it's important to let the reader know what you did. So go back, restate what you did. This is equal to, we said it was nx over e to the nx. Just skip some steps and got there. And it's less than 2 over nx. It's not necessary to go through all of this again. We just did it. And we can write this as 1 over n times 1 over x. And 1 over n is less than epsilon x over 2. So this is less than epsilon x over 2 times 1 over x. Right? Did I do that right? I think I did that right. Oh, and I forgot my 2 here. I knew there was something off. So here's my 2. So here's my 2. And then these cancel, and so you get epsilon. And the proof is complete. Right? So again, we have 2 over nx. We wrote that as 1 over n times 2 over x. And then 1 over n is less than this. So we replace it. The 2's cancel, the x's cancel, and we get epsilon. And so we've shown that the sequence of functions converges pointwise to 0. So just to reiterate, when you're writing the proof, you take cases, right? You start with your epsilon greater than 0. You pick your x. If x is 0, we can choose any n. It doesn't matter. Just choose any one you want. Then for all little n bigger than n, it's done. If x is not 0, we have to choose this specific one, right? This specific one that's bigger than this number. So we can't write this in the first case because x is 0. So it does need to be separated, right? So big N does depend on x in this problem. And that's why we have pointwise convergence instead of what's called uniform convergence. It turns out that this sequence of functions does not converge uniformly to 0 on this interval. Maybe I'll make a video for that another day. So I hope this video has been helpful. That's it. Hey, what's up? In this video, we're going to do a simple proof to show that a subset is a subgroup of a group. So here H is equal to 2z. H is all of the multiples of 2. So every element in H looks like 2 times n, where n is an integer. And then our G here is going to be the set of integers. And the operation here is just addition. So plus equals addition. So a subgroup of a group is a subset that's also a group under the same operation. However, there is a theorem that we can use in these proofs. So we say H, I'm going to use subgroup notation. So H is a subgroup of G. It's an inequality. Sometimes this means subgroup. If, and there's 3 conditions. The first condition is that H is not empty. The second condition is that H is closed under the group operation. So H is closed under the group operation. Group operation. So what does that mean? That means that for all, let's say, x and y in H, we have x plus y also in H. Now I'm using plus here because the operation in this example is plus. If you're using just regular group multiplication, you would do x, y in H. So it depends on the notation. Typically, we use the plus sign if we know the operation is commutative. Otherwise, we just use times. 3, H is closed under inverses. So H is closed under inverses. And so what does that mean? That means that for every x in H, we have the inverse of x, so negative x also in H. And again, if you were using multiplicative notation, it would be x to the negative 1 in h. So whenever we have a question that requires us to show something as a subgroup of a group, all we have to do is meet these three conditions. Let's go ahead and prove this one. And again, this one is purposely relatively straightforward. So proof. So first we have to explain why it's non-empty. So we have to think of a simple number that resides in h. Well, you can just pick any integer you want and then just show it's there. Let's use 0. So note 0 is equal to 2 times 0 is in h. And this is because 0 is in z. And when I say 0, I'm talking about this one, right? That's the n, right? That's your little n there. So this shows that h is not empty. So the first condition is satisfied. So now we have to show h is closed under the group operation. So we'll take any x and y in h. So take any x, y, and h. And then what you typically do in these proofs is you just write down what it means for elements to be in your set. So this means that x and y are multiples of 2. So this means that x is equal to 2n and y is equal to, say, 2m for some integers n and m in z. And so now we have to show that x plus y is in h. So the natural thing to do is to write it down. So then x plus y. And then we know what x is, so we can replace it with 2n. Likewise, we know what y is, so we can replace it with 2m. And we want to write this in a form that will tell us that this element lives inside h. So all of the elements in h are 2 times an integer. So what we can do is we can factor out a 2. Then we have n plus m. And then this here is in 2z. And this is because n plus m is in z. And why is that? That's because z is a group and it is closed under its group operation, right? So n and m are in z. Z is a group. So therefore, n plus m is also in z. So again, you could say all that in words or you could write it down a little more formally. So this is because this guy is an integer. And the reason it is because this is actually a group. So this shows that h is closed under the group operation. So this shows h is closed under the group operation, under the group operation. And that's key, right? H is closed under the group operation because G is, right? N and M are in G, and it's a group. Therefore, the sum is also in G. So it's kind of nice how that happens. Now we have to show that it's closed under inverses. I'll take a new x. So take any x. Could have used the same one, but take any x in 2z. So that means that x is equal to 2n for n in z. Now n is in z, and z is a group. So since z itself is closed under inverses, so this means negative n is in z. And again, this is because z itself is closed under inverses, right? N is in z, z is a group, it's closed under inverses, so negative n is also in z. I'll say it here because z is closed under inverses. So that means that, let's call it y equals 2 times negative n is also in 2z, right? Because negative n is in z, so 2 times negative n must be in 2z. Now we just have to show it's the inverse. So then we'll look at x plus y. So x is 2n. Y is 2 times negative n. As before, we can pull out a 2, so we get n plus negative n. n plus negative n is 0, right, because they're inverses, so you get 2 times 0, so you just get 0. And if we look at y plus x, we get 2 times negative n plus 2n. So this is 2 times and then negative n plus n, going kind of fast. This is 2 times 0, which is 0. So we have x plus y equals 0, y plus x equals 0, 0 is the identity. So this means that y is the inverse of x. So y is the inverse of x. And in particular, it's in 2z, so given any x in 2z, we have that negative x is also in 2z. So note here, if it's not clear, note that y is 2 times negative n, which is negative 2n, which is actually literally negative x. So we showed all 3 conditions, that it is non-empty, closed under the group operation, and closed under inverses. So this shows that it's a subgroup of G. So this shows, it's a big T, this shows that H is a subgroup of G. And that's it. I hope this video has been helpful. Hi YouTube. In this video we're going to prove that the sine function is uniformly continuous on the set of real numbers. Recall what it means for a function to be uniformly continuous. So f is uniformly continuous. Uniformly continuous on the set of real numbers R if for every epsilon greater than 0 we can find some delta greater than 0 such that for all real numbers x and y where the distance between x and y is small, so how small? Well, less than delta, then the distance between f of x and f of y is less than epsilon. So that's the definition of what it means for a function to be uniformly continuous on the set of real numbers. So in this problem we're going to prove that the sine function is uniformly continuous. So let's go ahead and work through the proof. So proof. So let's just do the proof, and as I do the proof you'll see why I'm just doing it instead of showing you how to figure it out. So let epsilon be greater than 0. And it turns out that in this proof our delta is simply going to be epsilon. So we'll choose delta to be epsilon. Okay. So then for all x, y, and r, so then for all x, y in the set of real numbers with the distance between x and y less than delta, we have, so now we're going to look at the distance between f of x and f of y. That's going to be sine x minus sine of y. And this is probably the part where if you were trying to do this on your own, you'd probably get stuck if you got stuck. So how do you do this part? Well, when you see something like this, you should think, hey, isn't there a trig identity or something I can use here? And there is, right? There is. This is equal to 2 cosine x plus y over 2, parentheses, and then sine x minus y over 2. So that's one of the main key steps in this proof, is just recognizing that, hey, there is a trig identity. So we now have to show that this is less than epsilon, right? So we need to somehow involve x minus y. So recall there is an identity, or not identity, but an inequality that says that the sine of x is less than or equal to the absolute value of x. Also, we know that the absolute value of cosine of x is less than or equal to 1. So here, what we're going to do is, let me show an extra step. So I can bring the 2 out of the absolute value, and let me just separate these into 2 separate absolute values so you see it clearly. So we have that first absolute value times that second absolute value. Beautiful stuff. And now you'll see that this is less than or equal to 2, so this one will replace with 1. And this one we will replace with the absolute value of what's inside using this inequality. So this is times the absolute value of x minus y over 2. Now you can write this as 2 times the absolute value of x minus y over 2. And the 2's cancel, so you get the absolute value of x minus y. We know that's less than delta. And delta is equal to epsilon, and that completes the proof. I hope this video has been helpful. Thanks for visiting my channel. That's it. Hi YouTube. In this video we're going to prove that the cosine function is uniformly continuous on the set of real numbers. So before we do the proof, recall what it means for a function to be uniformly continuous. We say that f is uniformly continuous on the set of real numbers, so on R, if for every epsilon greater than 0, we can find a delta greater than 0, such that for all xy in the set of real numbers, where the distance between x and y is less than delta, we have that the distance between f of x and f of y is less than epsilon. And the key difference between continuity and uniform continuity is that in uniform continuity, delta is only allowed to depend on epsilon. It's not allowed to depend on anything else. Okay, let's go ahead and go through the proof. Normally when I do a proof like this, I show you how to figure it out. However, the proof in this case is pretty simple as long as you have the right trig identity. So let's just do it. So we'll start by letting epsilon be greater than 0. And then we have to choose our delta. So you would have to do some scratch work to figure out the delta. I've already done this problem, so I'm going to go ahead and show you that delta is just going to be epsilon. And when you see the proof, you'll see why I didn't go through the scratch work. Then, for all xy in the set of real numbers with the distance between x and y less than delta, we have to look at the distance between f of x and f of y. So we have, and so let's look at that distance, the distance between f of x and f of y. So the absolute value of f of x minus the absolute value of f of y. So that's equal to, well, f of x is simply cosine x. Okay, cosine x. And f of y is simply cosine y. Okay, cosine y. And so now we're kind of stuck. So the trick is to use a trig identity. So this is equal to the absolute value of negative 2 sine, okay, sine of x plus y over 2 times sine of x minus y over 2. So this is the key in the proof, just knowing this trig identity or being able to reference it in some way. So when you see cosine x minus cosine y, always think, hey, wait a minute, isn't there a trig identity that relates these somehow? And so yeah, there is, and this is the identity. So now we need to continue the proof. So how do we do that? Well, we're going to use two things. So one, recall that the absolute value of sine x is less than or equal to 1. At the same time, the absolute value of sine x is less than or equal to the absolute value of x. So we're going to use these two facts to finish the proof. So the negative 2 here doesn't matter because when we take the absolute value of it, it's going to go away. In fact, let me just go ahead and show an extra step. So the absolute value of negative 2 is 2. Then we have times the absolute value of the sine of x plus y over 2 times the absolute value of the sine, put a dot here for times, of x minus y over 2. Okay, good stuff. So now we get to use these little inequalities here that have been written. Let me change the color. So this is less than or equal to 2. So which one do we use for which piece? Well, we know that the absolute value of x minus y is less than delta. So we want to probably use this one for this piece here. Okay, that way we have an x minus y. So this one will be less than or equal to 1, so times 1. So we'll use the first one for the first piece here. And then this one will be less than or equal to the absolute value of x minus y over 2. You can bring the 2 out of the absolute value and cancel it, so it's no issue. So this is equal to the absolute value of x minus y. And we know that the absolute value of x minus y is less than delta, and we said that delta was equal to epsilon. And that completes the proof. And that's why in this problem I decided not to show you how to find delta. I figured let me just show you the proof and you'll get it. A lot of times in these problems the delta is really obscure and it's like you really can't figure it out unless you know how to find delta. But now you kind of see how to prove it and how to figure it out, right? So whenever you encounter something like this, just always think, isn't there a trig identity that somehow relates cosine x and cosine y? So I hope this video has been helpful. Thanks for watching. Hi YouTube. In this video we're going to prove that this sequence is a Cauchy sequence. So before we do the proof, let me recall what it means for a sequence to be Cauchy. So we say that a sequence is a Cauchy sequence, I'll just say is Cauchy, if for every epsilon greater than 0 we can find some positive integer n. So there exists an n in the set of positive integers such that basically the terms get closer and closer together. So for all little n and little m bigger than capital N, the distance between two terms, a sub n and a sub m, can be made arbitrarily small. Okay, so you can make the distance between the points closer and closer together. So for example, if you were to maybe graph a Cauchy sequence, it would look something like this maybe. So all the terms get closer and closer together. Okay, the dots are the terms. All right, so before we do the proof, we actually have to figure it out. So I'll write proof over here, and then over here on the right, we'll go through the scratch work of how to come up with the proof. So we know that we need a sub n minus a sub m. We need that to be less than epsilon. That's our goal. That's our goal. And again, this is the scratch work. This is the scratch. So let's go ahead and write down a sub n. A sub n is n squared over n squared plus 1. And then a sub m is m squared over m squared plus 1. Good stuff. So I'm thinking maybe perform the subtraction, so let's do that. So the LCD will be n squared plus 1, m squared plus 1. So we can write this as n squared, and then what's missing here to get the LCD is m squared plus 1, minus, and then here we're missing n squared plus 1, so it'd be n squared plus 1 times m squared, all being divided by the LCD, which is n squared plus 1, m squared plus 1. And again, we want this somehow to be less than epsilon. So the next thing to naturally do is maybe just distribute. So you get n squared m squared. So n squared m squared. And then n squared times 1 is just n squared. Then distribute this m squared, so it's minus m squared, n squared, and then minus m squared. On the bottom, we still have all of this stuff here. This n squared plus 1, and then m squared plus 1. And it looks like we have some cancellation. That's always good. So that cancels there. So we're left with the absolute value of n squared minus m squared over all of the stuff here. So n squared plus 1, m squared plus 1. So one idea is to notice that n squared minus m squared is the difference of squares. However, I don't think it's going to help us because we would just get n minus m times n plus m. So another idea I have maybe is to break this up. This is really n squared over all of this. Let me write it like this. N squared over all of our stuff here. So n squared plus 1, m squared plus 1. Okay. And then minus, so minus m squared over then all of the stuff down here. N squared plus 1, m squared plus 1. And the reason I'm doing this is because I'm thinking about the triangle inequality, right? If we change this to a plus and put a negative here, we can use the triangle inequality. Recall the triangle inequality says if you have the absolute value of a plus b, that's less than or equal to the absolute value of a plus the absolute value of b. So let's try to use that here. So that would give us the absolute value of n squared over n squared plus 1, m squared plus 1, absolute value, and then plus. Now when you take the absolute value of this piece here, that negative is going to go away, so there's no issues there. So absolute value m squared, it's going to get rid of it. So n squared plus 1, m squared plus 1. And again, the goal is that we want this to be less than epsilon. So my thinking on this is maybe we can make this first piece here less than epsilon over 2, and this first piece here less than epsilon over 2, and then the sum will be less than epsilon, right? Because epsilon over 2 plus epsilon over 2 is epsilon. So we need to somehow reduce these denominators here. So let's see. So it'd be really nice to get rid of this n squared up top, right? So we can make the bottom here smaller by dropping the 1. And let me show you which one I'm thinking of dropping. We're going to drop this one in yellow, because watch. Then it's n squared over n squared m squared plus 1. And we can do that because this fraction is smaller than this fraction, because the bottom here is bigger than the bottom here, right? And I dropped the 1 precisely so we can cancel the n squareds. We're going to do something similar here, use a different color, except now we're going to drop this 1. That way we're left with m squared over, then here we have n squared plus 1, m squared. And it's strategic. It's so that this cancels and so that this cancels. So now we're left with 1 over m squared plus 1 plus 1 over n squared plus 1. And again, now we can drop the 1's, and this is a less than in this case. M squared plus 1 over n squared. Beautiful stuff. Now we're going to figure out how to make this less than epsilon over 2. I'm going to come over here because our proof is not going to go this low. So we want this to be less than epsilon over 2. So 1 over m squared to be less than epsilon over 2. We can cross multiply, so we get 2 less than epsilon times m squared. That means that m squared is greater than, reading it backwards, greater than 2 over epsilon. Taking the square root, we can say m is bigger than the square root of 2 over epsilon. And we can do the same thing with the n. So what we'll do in our proof in a few minutes is we'll choose a natural number n greater than the square root of 2 over epsilon. And we can do that via the Archimedean property, right? It says given any real number, you can always find a natural number that's bigger. This is a real number, and so we can use the power of Archimedes to find a natural number that is bigger. Okay, so that's going to be our n. We're going to choose an n bigger than that in our proof. Let's go back and knock this proof out. Let's do it. All right, so proof. So we'll start our proof by saying let epsilon be greater than 0. And by the Archimedean property, we can choose a natural number n that is greater than the square root of 2 over epsilon. So I didn't write that down by the Archimedean property. I didn't say natural number. I'm saying it in words. So remember, if you're doing stuff like this for like a class or something, you usually have to write more. So choose n bigger than this. Then, for all little n and little m bigger than capital N, we're going to look at the distance between a sub n and a sub n. So I'll skip some steps here in the proof. So this is going to be equal to n squared over n squared plus 1 minus m squared over m squared plus 1. Okay, and we did a bunch of algebra earlier, and we deduced that this was equal to, so via all of our scratch work, just pretend we're doing it again, we got to absolute value, let's go to this step here, n squared minus m squared, n squared plus 1, and then m squared plus 1. Right, because stuff canceled, and we got to that. Okay, that's, a lot of math gets us there. And then we broke this up and we used the triangle inequality. So I'll skip some steps and go to our piece down over here. So let me go further. Let's go down to this piece. So pretend we're doing all of the stuff we just did, right? Just all of it again, and that can put us here. So let me change this to less than, just to make this video shorter. So less than 1 over m squared plus 1 over n squared. Again, we just did all of this stuff. So let me put in the missing steps. So missing steps. Just reproduce them from the scratch work. And now we know that, let's just say little n, for instance, is bigger than capital N, which is bigger than the square root of 2 over epsilon. So this is something that we haven't quite shown, right? These missing steps, they're easy to reproduce from the scratch work, but this, let's go through it again. Right? That would mean that little n is greater than the square root of 2 over epsilon. So that means that n squared is greater than 2 over epsilon. So dividing by n squared and dividing by 2 over epsilon, that means that 1 over n squared is less than epsilon over 2. You can do the same thing for little m. So this is less than epsilon over 2 plus epsilon over 2. And again, this is since little n and little m are bigger than n, which is bigger than the square root of epsilon over 2. And this is equal to epsilon. And that completes the proof. So I'm glad I skipped the missing steps. Otherwise, I just realized this is an 11-minute video. So I thought it would take like 2 minutes. I was very, very wrong. I hope this video has been helpful. That's it. In this video, we're going to prove that this set, which is the set of all real numbers except 1, with this binary operation form a group. So we have to show 3 things. So let me write them over here. We need to show, 1, that the binary operation star is associative. So we have to show that for all little a, little b, little c in our set, if we compute a star b and then star the result with c, that's the same thing as computing b star c and then starring the result with a. So that's called associativity. That's the first thing we'll prove. 2, we need to show there exists an element E in our set such that for all A in our set, if we take A and we star it with E, that's the same thing as taking E and starring it with A, and that's equal to A. That's called the existence of an identity element. So E is called the identity. And 3, we have to show that for all A in our set, we can find some element B in our set such that A star B is the same thing as B star A, and that's equal to the identity element. So B is called the inverse of A. So the first condition is called associativity. The second one is the existence of an identity element. And the third one is that every element has what's called an inverse element. So let's go ahead and go through this proof really, really carefully. So proof. Just so I don't have to keep calling it this, I'm going to let G be equal to this set here. All right, we'll start with the first one. So 1. So we claim that our set is associative. So for all A, B, and C, in our set G, let's look at A star B star C. So we first work out what's in the parentheses. Now before we go further, let's try to make sense of this binary operation so that we're not just using the formula, instead we're kind of thinking about how it works. So if you have A star B, what does that mean? That means that you add A and B and you subtract the product. So you add these guys and subtract the product. So if we're doing A star B, we add A and B and we subtract the product. And then we still have the star and the C. And then we do it again. We add this guy to the C, so A plus B minus AB plus C, and we subtract the product, A plus B minus AB times C. At this point, we can't do much except maybe rewrite this and distribute the C. So this is equal to A plus B minus AB plus C minus, let's be really careful here, so minus AC minus BC, and then we have a negative and a negative, so we get plus ABC. There's not much more we can do here. So now what we'll do is we'll compute this. And this should be equal to what we have here already written down. Let's try it. So now we have A star, B star C. So we first compute what's in parentheses. So B star C, well, we still have the A. Okay, so B star C, that means we add B and C, and we subtract the product. And then we do it again. We add A to this and subtract the product. So that's A plus B plus C minus BC, and then we subtract the product. So A, B plus C minus BC. And now we can distribute the A. So this is A plus B plus C minus BC minus, and then distributing the A very, very carefully, we have AB minus AC plus ABC. Now what we have here should be equal to what we have up here as well. Let's use a different color and carefully check. Let's see, we have A here, we have A here. Boom, one down. B, B, boom, there it is. Negative AB, do we have that? We do. Plus C, do we have that? We do. Success. Minus AC, do we have that? We do. Minus BC, do we have it? We got it. And then the last one is ABC, and we have ABC. So we've shown that star is an associative binary operation. So this shows star is associative. Now we have to find E. Once we find E, we can carefully write down this equation with this quantifier to show that we have an identity. But first we have to find E. So let me go to the side here and let's find E. So how do you find E? Well, you kind of write this down and work it out. So let's write down A star E. And again, this is not part of the proof. What we're doing here is not part of the proof. That's why I'm doing it on the side. So A star E, that means you add them, so A plus E, and you subtract the product, so minus AE. And we set this equal to A, because we want it to be the identity. You can subtract the A's, and so you end up with E minus AE equals 0. Factoring out an E, you get E 1 minus A. And here, multiplication is commutative, so there's nothing funky going on, right? Really, it would have been better if it was written this way, right? And then factoring is a little more clear. Anyways, this is equal to 0. These are real numbers. That means that E is equal to 0, or 1 minus A is equal to 0, in which case A is equal to 1. But that's impossible, because A is in the set of all real numbers not containing 1. So that means E must be equal to 0. So now we will carefully show that 0 is the identity. Okay, so 2. And for reference, let me go ahead and write the binary operation down again over here. So we have A star B, and star tells us to add the elements and subtract the product. All right, so then, for all A and G, which is the set of all elements not containing 1, all the real numbers except 1, we're going to look at a star e, or a star 0. So a star 0, well, that means a plus 0 minus a times 0, which is just a. Likewise, we'll look at 0 star a. What does that mean? That means we add 0 and a, and we subtract the product. That's also a. So this shows the identity element, that the identity element is e, which is equal to 0. And that's certainly in our set G because it's not equal to 1. So we've shown the existence of an identity. Finally, the last piece of the proof is to prove that we have an inverse. So as before, we have to find the inverse, like on our own on the side, before we prove that we have one. So we want an element B such that a star B is equal to the identity. So what does a star B mean? That means you add a and b and you subtract the product. And that should be equal to e. So what we'll do here is we'll solve for b because we have to find b, right? B is what we're looking for. We're looking for the inverse. So subtract here the b, e is 0. So let's fix that first. And then subtract the a. So we get b minus ab equals negative a. Factor out the b. And solving for b, kind of rushing this video is turning kind of long, there is our b. And note that this is actually in G since a is not equal to 1, so it's well defined, right? Because if a was 1, this wouldn't make any sense. So that's going to be the inverse of an element a. So now we go back to the proof and we prove it. So for all a and G, the element, let's call it b, negative a over 1 minus a. This is also a real number, and it's certainly in G. Right? A is not 1, so it's okay. And now we have to take a and star it with this guy. So a star b is equal to a star, and let's write down what b is, negative a over 1 minus a. Get some more room here. This is going to get a little bit messy. So this is equal to, well, the formula says you add these. So it's a plus, then it's negative 1 over 1 minus a, and then you subtract the product. So a, negative a over 1 minus a. So this is equal to, we're going to multiply this a by 1 minus a over 1 minus a. So it's going to be a, 1 minus a, over 1 minus a. The reason I did that is because the LCD is 1 minus a. Minus a over 1 minus a. And then here, minus and minus is plus. So plus a squared over 1 minus a. So this is equal to, all of this is being divided by 1 minus a. Here we get a times 1 is a times negative a is negative a squared. Here we get a minus a and then plus a squared. Boom, all of this cancels. We get 0 over 1 minus a, which is equal to 0. Now we have to prove it the other way. Let's go ahead and finish it. We're almost there. Now if we look at b star a, this is the same thing as, well, b is negative a over 1 minus a and then star a. What does star mean? Star means you add these and subtract the product. So negative a over 1 minus a plus a minus the product. Negative a over 1 minus a times a. This is equal to negative a over 1 minus a plus a, 1 minus a, 1 minus a. Playing the same game here, multiplying by 1 minus a over 1 minus a. Negative and negative again is positive. And again, rewriting this, this is all over 1 minus a. So we end up with negative a, and then here we get a, and then minus a squared, and then over here we get plus a squared. And boom, these guys go away. You end up with 0 over 1 minus a, which is 0. So we showed that a star b is equal to 0, which is the identity element. Yes. And we showed that b star a is equal to 0, which is the identity element. Success. So we've shown all three conditions. So thus, I'll make it a comma, G together with star is a group. So not the easiest example, but I hope this video helps. And the point is that this here is not the proof, right? This is how you figure it out. This is how you prove it. So it's really important to structure your work carefully. Also notice this little subtle point here. We did have to justify why this element was in our set G. So I hope that video made some sense. In this video, we're going to prove what's called the squeeze theorem, or pinching theorem, or sometimes even the sandwich theorem. I prefer squeeze. It basically says if we have three sequences, a sub n, b sub n, and c sub n, and c sub n is trapped between the other guys here, a sub n and b sub n, and if a sub n converges to L and b sub n converges to L, then whatever is trapped in the middle also must converge to L. So it's pretty clear intuitively, we just have to come up with a proof. So proof. We'll start by writing down our hypothesis, which is basically all of this stuff up here. So suppose we have three sequences, a sub n, b sub n, and c sub n, and they are such that, well, c sub n is trapped in the middle, so a sub n is less than or equal to c sub n, which is less than or equal to b sub n, for all positive integers n. And by the way, you can relax this condition. As long as this inequality is true for all little n greater than some capital N, everything's okay. In other words, as long as this is true from some point on, then the squeeze theorem still works. Okay, and we also have to assume that the limit as n approaches infinity of a sub n is equal to L. So I'll write it this way. A sub n converges to L. And we also want this to hold, so I'll write that as b sub n converges to L. So we've written down all our hypotheses. Now we just have to figure out how to prove this. So this is what we're trying to show. So using the definition, we're trying to show that for all epsilon greater than 0, there exists a positive integer, which we'll denote by capital N, such that for all little n greater than capital N, the distance between c sub n and L is smaller than epsilon. So if the distance between c sub n and L is smaller than epsilon, that means that c sub n minus L is smaller than epsilon and greater than negative epsilon, right? It's trapped, right? Its distance is smaller than epsilon, so it's trapped between negative epsilon and epsilon. We can add L to all three sides, and we get this inequality. So this is equivalent to this. So if we can come up with this in the proof, we're basically done. All right, so to start using this definition, we have to start by assuming that we have an epsilon greater than 0. So we'll start by saying, let epsilon be greater than 0. And then we somehow have to find our capital N such that this condition is true. So first, let's use this condition. Since a sub n converges to L, there exists a positive integer. Now, we have two sequences converging to L, so it's a good idea generally to maybe call this n sub 1, such that for all little n greater than n sub 1, the distance between a sub n and L is smaller than epsilon. But we know we can play the same game we did with c sub n and write this id est. We can write this as a sub n less than L plus epsilon and greater than L minus epsilon. And this is true for all little n greater than capital N sub 1. All right, now let's use the fact that B sub n converges to L. So since B sub n converges to L, there exists a positive integer, perhaps another, so let's call it n sub 2, such that for all little n greater than n sub 2, the distance between B sub n and L is smaller than epsilon. And as before, it est, this is equivalent to saying that B sub n is less than L plus epsilon and greater than L minus epsilon. So we have a couple conditions here. I'm going to circle them. We have this one here. We have this one here. And we have this one here. And with all three things, we should be able to finish the proof. I'm going to finish the proof over here on the side. So we're going to continue up here. So first, we need to find a capital N, right? We have let epsilon be greater than 0, and we need to find a positive integer n. Well, we want both conditions to hold. So the natural thing to do is to set capital N to be equal to the maximum of n sub 1, n sub 2. So it's the biggest one. Okay, then for all little n greater than capital N. Okay, so if little n is bigger than capital N, it's certainly bigger than the biggest of these guys. So it's bigger than the smaller one. So it's bigger than both, right? So we have this condition holding and this condition holding. And then let's see if we can create this inequality. Well, we know, let's see, L minus epsilon. So let's write that down, L minus epsilon. And now we have to use this. So L minus epsilon is less than a sub n. This is less than a sub n. And this inequality is true because little n is bigger than capital N, which is bigger than n sub 1. And that's the condition required for this to be true. All right, then we can use this box again. So this is less than or equal to C sub n, which is less than or equal to B sub n, again by the same box. And now we need to show that this is less than L plus epsilon. Well, we can use this condition here because little b sub n is less than L plus epsilon. Why? Because little n is bigger than capital N, which is bigger than n sub 2 because capital N is the maximum, right? So this condition holds, and so b sub n is less than L plus epsilon. So this is less than L plus epsilon. It est, C sub n is less than L plus epsilon and greater than L minus epsilon, right? Less than L plus epsilon and greater than L minus epsilon. And now what we can do is we can subtract epsilon from all three sides. So we end up with C sub n minus L less than epsilon. And this is the same as saying that the absolute value of C sub n minus L is less than epsilon. Beautiful stuff, right? So we started with an epsilon greater than 0. We found a positive integer n, so this is certainly an integer, such that for all little n greater than capital N, the distance between C sub n and L is smaller than epsilon. So this shows that the limit as n approaches infinity of C sub n is equal to L. And we have proved the squeeze theorem. I hope that made sense. Hey YouTube, thanks for visiting my channel. In this problem we're going to prove that the sequence of functions converges pointwise on the interval 0, 1. Before we do the proof, let's recall what it means for a sequence of functions to converge pointwise. I'll squeeze it in up here at the top. So we will say that f sub n converges to f pointwise if for every epsilon greater than 0 and for every x in our domain, in this case the domain of the functions is 0, 1, we can find some positive integer such that for all little n bigger than big N, the distance between f sub n of x and f of x can be made small. How small? Less than epsilon. So that's what it means for a sequence of functions to converge pointwise on an interval. So in this problem, we're going to prove it for this case. So before we do the proof, we actually have to figure out the proof. So that's the scratch work. So let's go ahead and figure out the proof. So the sequence has to converge in this set, okay? So let's consider different cases. So like if x is 0, let's think about what happens to our functions. We look at f sub n of 0. Right, you just plug in 0 to your sequence. And so you get 0 to the n, and that's just going to be 0. So this should converge to 0 as n approaches infinity. And in the proof, what's going to happen is we're going to have f sub n of 0 minus, and we're saying it converges to 0, so minus 0. Well, we know f sub n of 0 is 0, so we'll just get 0 minus 0, which is 0. And that will be less than epsilon in the proof, right? So it should work out really, really easily. If x equals 1, we look at f sub n of 1, and that's 1 to the n, which is 1. And as n approaches infinity, right, this will approach 1. So in our proof, we'll have f sub n of 1, and our limit should be 1, so minus 1. So this is 1 minus 1, which is 0, which will be less than epsilon. So both of these cases will be very easy to deal with when we actually go to our proof. The difficult case, or the more challenging case, is the case when x is strictly between 0 and 1. So if this is the case, then f sub n of x is simply x to the n. And whenever you have a number that's strictly between 0 and 1, and you're raising it to a power, that number gets smaller and smaller and smaller the bigger the power gets. So eventually that number gets really, really close to 0. So as n approaches infinity, this should approach 0. So our limit in this case is going to be 0 again. So in our proof, we'll have f sub n of x minus 0, which is x to the n minus 0, which is the absolute value of x to the n. And we somehow have to show that this is less than epsilon. Okay, so this is where it gets a little bit tricky. So we can drop the absolute value, and the reason is x is between 0 and 1. Okay, so it's already positive, so this is x to the n. And we want this to be less than epsilon. So if you look back, let me scroll up so you see it. If you look here, we need to find a natural number n. In these first two cases, I don't even think I mentioned it, but this will work independent of n, both of these cases, x equals 0 and x equals 1. So this is super easy, and we'll just mention it in the proof. But in this case, we'll actually have to find an n. So to do that, let's go ahead and solve this inequality for little n. So n is in the exponent. So the natural way to do that is maybe take the natural log of both sides. So ln x to the n less than ln epsilon. Then you can use the power rule for logs to bring down the n. So you get n ln x less than ln epsilon. And then we can solve for little n by dividing by the natural log of x. And when you divide by the natural log of x, we'll first notice a couple things. One, it makes sense because x is not 1, so you're not dividing by 0. The other thing that's worth noting is that the graph of the natural log is special, right? It's got a vertical asymptote at 0, and it passes through 1, and it looks like this. So our x is, use a different color so you can see, our x is in this green region here on the graph. So x is between 0 and 1. So the natural log of x is negative, it's less than 0. So when we divide by the natural log of x, we actually have to reverse the inequality. So this will become n greater than the natural log of epsilon over the natural log of x. Now, we have to find a positive integer greater than this. We can do that using something called the Archimedean property. It's usually studied at the beginning of like an advanced calculus course. It says that whenever you have a real number, you can always find a natural number that's bigger. So we'll choose big N to be bigger than the natural log of epsilon over the natural log of x, right? We can use the Archimedean property to do that in the proof. Okay, let's go ahead and go through the proof carefully. So proof. So let me scroll back up to the definition so you see it. So you always start the proof by taking an epsilon greater than 0 and an x in your interval. So we will say let epsilon be greater than 0 and take an x in the interval. So let's take cases. So let's say if x is 0. Well, if x is 0, we know that fn of 0 is 0. So take any n. Take any positive integer. Doesn't matter which one, right? Because we have to show the existence of capital N, right? You have to show that there is a capital N such that this condition is true. So in this case, it doesn't really matter. So we'll just take any capital N. Then for any little n, it doesn't matter what our big N is. So for any little n bigger than big N, if we look at fn of 0, we're claiming in this case that the limit is 0, so minus 0. We just get 0 minus 0. That's equal to 0, and that's less than epsilon. And the proof is done in the case when x is equal to 0. If x is equal to 1, in this case, f sub n of 1, well, that's 1 to the n, which is 1. And so as before, we claimed our limit was 1. So this whole process here is going to repeat itself. So again, we can take any positive integer. So take any n in the set of positive integers. Then for any little n bigger than capital N, we look at the difference between f sub n of 1 and 1, which is our limit. Well, we know f sub n of 1 is 1, so we get 1 minus 1. So that's 0, and that's less than epsilon, so the proof is done in the case when x is 1. Now the fun part. If x is between 0 and 1, this is the part that's kind of exciting, we're going to choose a natural number n that is larger than the natural log of epsilon over the natural log of x. Right? You can use the Archimedean property to do that. Okay. Then, for any little n bigger than capital N, we're going to look at the difference, right? The difference between f sub n of x and 0, because our limit is going to be 0 in this case. So we look at f sub n of x minus 0. Well, that's x to the n minus 0. That's the absolute value of x to the n. And we know we can drop the absolute value because x is between 0 and 1, so that's just x to the n. Now we're totally going to formalize this. So since little n is bigger than capital N, which is bigger than ln epsilon over ln x, that means we just restate it, we have little n bigger than ln epsilon over ln x. And let's solve for x so we can really make the proof concrete. So if you multiply both sides by the natural log of x, you reverse the inequality sign. Again, the natural log of x is negative in this case, because recall this green region, that's where x resides, so the natural log is a negative number. So we get n natural log of x. Then we flip the sign, so that's less than natural log of epsilon. And we're solving for x, so now we'll divide by n. So we have ln x less than ln epsilon over n. And now to solve for x here, we can use the fact that ln x and e to the x are inverse functions, or you can take a more algebraic approach and you can exponentiate both sides so that these actually cancel. So you get that x is less than e to the natural log of epsilon over n. All right, let's finish our proof. So thus, let's restate this. the difference between f sub n of x and 0. We said that was equal to x to the n. Right, that's equal to x to the n. And this is less than, well, x is less than this guy here. So I'm just going to replace x with that. So it's e to the natural log of epsilon over n, and the whole thing is to the nth power, right? Just replacing x with what's in parentheses using this. And then what you do here is use properties of exponents, right? The n's will cancel. So you'll get e to the natural log of epsilon. And then these cancel, e and the natural log of x, because they're inverse functions, and so you get epsilon. And that completes the proof. So a bit of work. Wow, this video is almost 12 minutes long. Oh my God. All right. So long problem. I hope this helped. Just to finish really quickly. So in general, we had, just to recap, we had our sequence was this. And we showed it converged pointwise. And the function it converged to was, let's see, don't want to mess up now after 12 minutes. So it converges to 0 if x is 0 or if it's less than 1. And it converges to 1 if x is, if x is 1. Yeah, if x is 1. Converges to 1 if x is 1. I got a little lost there. And so this is the pointwise limit of this sequence of functions. The convergence is not uniform, right? Because this is a sequence of continuous functions. If the convergence was uniform, then the limit should also be continuous. But it's clear this function is not continuous, right? It's got to jump. So again, whenever you have a sequence of continuous functions and the convergence is uniform, the limit is also continuous. And this just did not work in this case. So it's only pointwise convergence on this interval. So that's it. Proof that the limit of 3x plus 5 as x approaches 2 is equal to 11. We're going to use the delta epsilon definition of a limit to do this. So let's recall that before we get started. So recall the limit of f of x as x approaches a is equal to L. This is equivalent to the statement for all epsilon greater than 0, we can find some number delta greater than 0, such that for all real numbers x, with the distance between x and a smaller than delta, we have the distance between f of x and L smaller than epsilon. So we're going to use this definition to prove that the limit is 11. So before we do the proof, we're going to figure out the proof, and then we're actually going to write the proof. So it really is a separate process. So this will be the scratch work. So here we're allowed to be sloppy. So we need to show that whenever the distance between x and 2, because 2 is our a, is smaller than delta, that the distance between f of x and L is smaller than epsilon. So this here is our f of x, 3x plus 5. And our L in this problem is 11, so minus 11. And we want this to be smaller than epsilon. So this is the same as 3x minus 6, smaller than epsilon. This is the same as 3 times x minus 2, smaller than epsilon. Then we can divide by 3, so we end up with x minus 2 smaller than epsilon over 3. So that is going to be our delta in the proof. Right, so now when we write our proof, we know exactly what our delta is, and it'll seem like magic to the person who didn't see the scratch work. So let's go ahead and do the proof. So proof. So we'll start by letting epsilon be greater than 0. So let epsilon be greater than 0. Then we have to find a delta, which we already found in the scratch work. So choose delta equal to epsilon over 3. Then for all real numbers x with the distance between x and 2 smaller than delta, we have, and now we're basically just going to mimic what we have here, but in a more elegant way. So we have f of x, which was 3x plus 5, minus L, which is 11, and this is equal to 3x minus 6. Notice we didn't write less than epsilon. We're not allowed to do that. That's what we have to prove. That's why it's good to separate the scratch work from the proof. Here, again, we're just mimicking what we did here, so we're going to factor out a 3. And we know something about x minus 2. X minus 2 is less than delta. So 3 times x minus 2 is less than 3 delta. And what's delta? Well, delta was chosen by us to be epsilon over 3. So this is equal to 3 times epsilon over 3. Beautiful. And the 3's cancel, and this is equal to epsilon. Boom, there it is. And that is the delta epsilon proof. This is the easiest delta epsilon proof you can do, but it's really good to master it. You should know how to figure it out via the scratch work, and you should also know how to write it formally via a formal mathematical proof. So I hope this video made sense. Hey YouTube, in this video we're going to prove that this limit is equal to 0 using the delta epsilon definition of a limit for a function of 2 variables. So first let me go ahead and write down the definition. So in what follows, L is a real number. So when we write limit as xy approaches, say, x naught, y naught of f of xy, when we say that this is equal to L, this means that for every epsilon greater than 0, there exists a delta greater than 0, such that for every pair of real numbers x and y, so we could say that a couple ways. I'll say it as follows. So for every pair xy in the plane with, I'll write it down here, with the distance between xy and x naught y naught less than delta. This here does have this little symbol here as well. So what is this? This is called the Euclidean distance. We'll come back to it in a minute. We have the distance between f of xy and L less than epsilon. And this is just the regular absolute value. These are real numbers, so we can just use the absolute value. These are ordered pairs, though, and we have to measure the distance between ordered pairs. How this works is you can rewrite this as follows. You can write this, you can subtract the x coordinates, so you would get x minus x naught, and then subtract the y coordinates, okay, and then you get this. And then the definition of this is that you take the square root and you just square the components. So it'd be x minus x naught squared plus y minus y naught squared less than delta. So some books write the definition like this. They use this, like I have a calculus book here, and this is how they write the definition. I decided to use the Euclidean norm just to show you what it was. Okay, so first let's figure the proof out, and then we'll prove it. So I'll write proof over here, and then we'll come over here to the right, and we'll try to figure out the proof. So scratch work. So we know we'll have an epsilon greater than 0. We'll have that. And our goal is to find delta. So we're going to need delta. And we get to assume this piece here. We'll get to assume this. So we'll have this. We'll have that this distance is less than delta. So that we get for free. And then we have to look at the distance between f of x, y, and L. So in this problem, f of x, y is this right here. and L is the 0. So I'm going to go ahead and write that down. So you have absolute value x cubed y over x squared plus y to the 4th. Then we have minus 0. Let's go ahead and perform subtraction. So we'll get absolute value x cubed y over x squared plus y to the 4th. And we somehow need to show that this is less than our epsilon. So how do we do it? Well, there's a reoccurring idea in these problems. Whenever you have a fraction, you can drop terms from the numerator, right? Now I see this y to the 4th here, and it seems really problematic. Like I don't want that to stay there. So we're probably going to end up dropping that. Before we do though, let's reason this. Maybe we can take this y and write it out here, just to make it look better. And let's just write it like this, just so we can clarify our thinking as to what will happen if we drop the y to the 4th. So let's think about that again. So if we drop the y to the 4th, what's going to happen? We're going to end up with x cubed over x squared, which is just the absolute value of x. So I think that might be the way to go. So if x is not 0, so this is only valid if x is not 0, we can drop the y to the 4th, and we'll get the absolute value of y times, then here we'll have x cubed over x squared. Then here we'll have the absolute value of y times the absolute value of x. Now you might say, well, what if x is 0? Well, if x is 0, the whole thing is 0, and this is going to be less than epsilon, and we're done with the proof. So at some point in the proof, we'll clarify this thinking one more time. We'll mention it again, and so we'll be able to do the proof, no worries there. So you might look at this and say, well, wait a minute, we're in a pretty bad position here. Well, I forgot to mention that here x naught is 0 and y naught is 0. I just totally forgot to do that. So glad this is not the proof, it's the scratch work. So we have the absolute value of y times the absolute value of x. We want this to be less than epsilon. Well, check this out. The absolute value of x is equal to the square root of x squared. And that's equal to the square root of x minus 0 squared. And that's certainly smaller than less than or equal to the square root of x minus 0 squared plus y minus 0 squared, right? Because there's more stuff here in the square root, so this could be bigger or equal, and that's less than delta. So how do I know how to do that? Well, again, it's a reoccurring idea. I think I did this somewhere else at some other point in life. And so when I saw the x and y, I thought, well, we can control those terms, right? You could do the same thing with the y, right? So likewise, this guy is less than delta, right? So then you can say that this here is less than delta times delta, which is equal to delta squared. So we just got to make delta squared equal to epsilon, and we're good. So we're going to choose delta to be equal to the square root of epsilon. Beautiful stuff. All right, let's prove this thing. So now we'll go back to our proof. And we'll start formally. We'll let epsilon be greater than 0. And we will choose our delta. Our delta is going to be the square root of epsilon. So then, let me scroll up so you can see the definition. We have to rephrase the definition, right? So we let epsilon be greater than 0. We chose our delta. Right? It certainly exists. Epsilon exists, so the square root of epsilon exists because epsilon's a positive number. Then for all ordered pairs in the plane, so for all xy in the plane with, well, the distance between xy and 0, 0 being less than delta. So with, I'm going to go ahead and write this down. So with 0 less than square root x minus 0 squared plus y minus 0 squared less than delta, we have, and so now we'll look at the distance between f of x, y, and L, which is what's written here, right? So I'll write it again. So x cubed y over x squared y to the 4th, right? Minus 0, so I didn't write the 0 because it's equal to this. And I'm going to go ahead and write it like I did before, so absolute value of y times x cubed over x squared plus y to the 4th. Now, if x is 0, we're done. Right? I'll just say done. Why? Because this whole thing is 0 and it's less than epsilon and piece of cake. So assume x is not 0. Then, write it again, just for clarity. X cubed y, x squared plus y to the fourth. We said this was equal to the absolute value of y times the absolute value of x cubed over x squared plus y to the fourth. Again, if x is 0, this whole thing here is 0 if it wasn't clear. And so it's less than epsilon and the proof is done, right? Independent of delta, right? So we don't even need the delta. So assume it's not 0, so we can do this. Then we can drop this evil y to the fourth term. This is less than or equal to the absolute value of y times the absolute value of x cubed over x squared. See, now it's not 0 over 0, so we're okay. This is equal to the absolute value of y times the absolute value of x. And each of these are less than delta. So delta times delta, which is delta squared. But we said delta was the square root of epsilon. So it's the square root of epsilon squared. And that, my friends, is equal to epsilon. And that completes the proof. I hope this video has made sense. Thank you for visiting my channel. That's it. Suppose R is a commutative ring with identity and I is a proper ideal. We're going to prove that I is prime if and only if the quotient ring R mod I is an integral domain. So proof. Let's start by assuming that the quotient ring is an integral domain. So suppose the quotient ring is an integral domain. That means if we take any two elements in this ring and we multiply them and we get 0, then at least one of them is 0. So that's the definition of integral domain that we'll be using. And the claim here is that I is a prime ideal. So suppose that AB is in I for some AB in our ring. And we have to show that A is an I or B is an I. And that will prove that I is a prime ideal. Now then, the fact that AB is an I means that the coset I plus AB is equal to I plus 0, where I plus 0 is the identity element of the additive subgroup, or of the additive group of the quotient ring. So this is the 0 element in the quotient ring. So I plus A times I plus B is equal to I plus 0. So this is the 0 element in the quotient ring, and the quotient ring is an integral domain, so that means that I plus A is equal to I plus 0, or I plus B is equal to I plus 0. This means that A is an I, or B is an I. And so we're done. This means that I is prime. So thus, I is a prime ideal. So one direction down and one to go. Now let's start by supposing it is actually a prime ideal. So suppose I is a prime ideal. And now we'll prove that the quotient ring is an integral domain. So we'll assume that we have some product and it's equal to 0. So suppose that we have, say, I plus A times I plus B equal to I plus 0 for some I plus A, I plus B in our quotient ring R mod I. So then we can rewrite the above as follows. Then I plus AB is equal to I plus 0. And this is precisely what it means. for AB to be in I. Since I is prime, this means that A is an I or B is an I. In other words, I plus A is equal to I plus 0, so I plus A is equal to I plus 0, or I plus B is equal to I plus 0. So we started with the product equal to 0, and we showed that at least one of them must be 0. So we've shown that R mod I is an integral domain. So thus, the quotient ring is an integral domain. And that's it. The only idempotent elements in an integral domain are 0 and 1. This is a pretty easy proof. Let's go ahead and do it. So suppose R is an integral domain. So integral domain. And let's take some x in R, which is idempotent. Idempotent. So now we'll simply use what it means for an element to be idempotent. So then, this means that x squared is equal to x. So what we can do is subtract x from both sides. So we end up with x squared minus x equals 0. And using the distributive property, we have x minus 1 equals 0. Now since R is an integral domain, this means that x is equal to 0 or x minus 1 is equal to 0. So x is equal to 0 or x is equal to 1. And we've shown that the only idempotent elements in an integral domain are 0 or 1. I hope this video made sense. In this video, we have to prove that if x is a real number, then there exists a positive integer n such that x is between negative n and n. So let's go ahead and try to work it out. So proof. So before we write the proof, we have to figure out the proof. So let's go ahead and try to do that. So this will be our scratch work. So to do this proof, we have to use something called the Archimedean property or Archimedean principle. It basically says that given any number, you can find the number that's bigger. So let's start by using x. If we have x, then we can find a number that's bigger than x. So we can find the natural number n that's bigger than x by the Archimedean principle. So if you write this backwards, this means that x is less than n. So that takes care of the first condition. Now we somehow need to involve negative n. In particular, maybe we can start by trying to involve a negative sign. So one way to do that is to look at negative x. So if we look at negative x, again, by the Archimedean principle, this says that there is an integer, maybe let's call it m, that's bigger than negative x. Right? We can't use the same n, right? The Archimedean principle just guarantees the existence of a number. It doesn't specify what the number is. So using the Archimedean principle once, we have n bigger than x. And rewriting it, we got this. Using it again on negative x, we get m bigger than negative x. Now, when you multiply by negative 1, what you get is negative m, and then you switch the inequality, less than x. So now we have this. So putting both of these conditions together, we have x less than n bigger than negative m. If you're curious as to why I used negative x, it was pure luck. I was thinking that because there's a negative here, well, maybe not luck, but because there's a negative here, I figured we somehow have to involve it. So let's try to use negative x. We're almost done, right? We're almost done with our scratch work. These numbers need to be the same. So let's look at a picture here. Let's say this is x, and this is n, and this is negative m. This is one possible scenario, right? So we want x to be between these numbers. So what we could do is we could take the maximum distance, right, between these. So we would take this bigger distance here. So if we were, that's m in this case, right? This distance here is m. So if we put m over here, that would work. X would be between negative m and m. So we just have to take the biggest distance. So we're going to set, let's call it big N, to be equal to the maximum of n and m. And that's what we're going to use in the proof, okay? If we use this, we should get everything to work. Let's try it. Let's go back to the proof now. So it says if x is a real number, so we'll start by assuming that. So suppose x is a real number. And now it'll all come to clarity, hopefully, after we do this. And we have to show the existence of a positive integer such that this is true. Right? We decided that if we take the bigger of these two, it will work. So first, we have to go through this whole procedure again. So since x is a real number, so x is in the set of real numbers, by the Archimedean principle, there exists a natural number, which I'm going to give it a different name. Okay, I'm going to call it n1. I want to save n for my final answer. So n sub 1 in the set of natural numbers such that n is bigger than x. Now let's do it again with negative x. So since negative x is a real number by the Archimedean principle, so AP, there exists a natural number, possibly another one, which I'll call n sub 2 in the set of natural numbers, such that, and this time we have that n sub 2 is bigger than negative x. So that would mean that negative n sub 2 is less than x. And then taking this condition and reading it backwards, x is less than n sub 1. Okay, and let me just explain this step again. So here's n2, here's negative n2, here's x, here's n1. So if we take the biggest distance between the two and we call that our n, x will be between those numbers. And we'll also show it mathematically, as you'll see in a moment. So take n to be equal to the maximum of n2 and 1. Then, okay, let's carefully show it. So then let's do the easy case first. So then x is less than n1, we know that already, which is less than or equal to n, because n is the maximum of the two, right? It's the maximum of the two. So now we have to show that x is bigger than negative n2, right? We have to show that x is bigger than negative n2. So let me come back over here. So if we want to show that x is bigger than negative n2, right, it might be worth showing, well, I guess we have to involve n2 with n somehow, right? So let's think here. So note, let's just see what happens. Let's try it. n2 is less than or equal to n, right? So now we need to involve negative numbers. So this would mean that negative n2 is greater than or equal to negative n, right? So rewriting this, this would mean that negative n is less than or equal to negative n2, which is less than, look up here, less than x, which is less than, well, it worked out perfectly, and 1, which is less than or equal to n. So in particular, this means that negative n is less than x, which is less than n. And that completes the proof. Got a little bit freaky there at the end. When I got here, I wasn't, after this, I wanted to involve a negative, and I tried to involve x, but then I realized, wait a minute, n is the maximum of n2 and 1. So let's just focus on that. n2 is less than or equal to n. And then you want to involve negative n2. So you multiply by negative n2. And then just write this down and read it backwards, right? So negative n is less than or equal to negative n2, which is less than x, which is less than n1, which is less than or equal to n. And so you get this condition here. So kind of figured it out on the spot. But hopefully that helps, because when you're doing these on your own, that's what you have to do, right? You have to figure them out. So maybe if you see how I figure it out, maybe that will help you learn how to figure it out for yourself. So I hope this video has been helpful. That's it. Let H be a subgroup of G. We have to prove that if G is cyclic, then so is the quotient group G mod H. So proof. It's probably worth noting that the quotient group is actually a group in this problem. H is a subgroup, so we have that part. And G is cyclic, therefore G is abelian. And H is a subgroup, and so it's also abelian. Because it's abelian, it's normal. So H is actually normal in G, and so the quotient group actually makes sense. So this is a group because H is normal in G. So all we have to do is show it is cyclic. So we'll start by assuming that G is cyclic. So suppose G is cyclic with generator little g. So that means we can write G as the cyclic group generated by little g. And the claim is that the quotient group is also cyclic. So we need to come up with a generator for the quotient group. So the natural choice is to look at the cyclic group generated by the right coset Hg. So take any right coset, say Hx, in the quotient group. Then x is an element of G, which is generated by little g because it's cyclic. So there exists some integer, let's call it m, such that we can write x as little g to the m. So then we should be able to write hx as a power of hg. Let's try it. So then hx is equal to h little g to the m. And by definition of the multiplication in the quotient group, this is actually h little g times h little g times dot 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 times h little g, where we have m copies of this right coset. So this is actually hg to the mth power. It's hard to say it. And this is certainly in the cyclic group generated by hg. So we showed that if we took an element in the quotient group, it was also in this cyclic group. So that means that the quotient group is contained in this cyclic group. And the other inclusion is obvious. So the quotient group is equal to the cyclic group generated by hg. So G mod H is cyclic. And that's it. Prove that if x is a positive real number, then there exists a positive integer n such that 1 over n is less than x, which is less than n. Proof. Before we do this problem, we have to actually figure it out. So let's go to the side I can't spell scratch work. Let's go to the side and do the scratch work, or whatever that is. So to do this problem, we have to use something called the Archimedean principle. It basically says that given a number, we can find a positive integer which is bigger. Okay, so we need to create this inequality. So the natural thing to do is to start with x. So because x is an element in the set of real numbers, by the Archimedean principle, we should come up with a natural number n which is bigger than x. So we can do that. And if you write this backwards, if you read it right to left, it says x less than n. So that takes care of the first condition. Now we need to come up with 1 over n less than x. Okay, so I'm using the same n here. We won't be able to do that in the proof, but let's solve this for n. So if you multiply both sides by n, we get 1 less than xn. And then dividing by x, right? X is positive, so the inequality sign won't switch. We have 1 over x less than n. Okay, or reading it backwards, n bigger than 1 over x. So we need to use the Archimedean property on 1 over x. So 1 over x is a real number. So by the Archimedean property, there exists a positive integer which we can call, say, m, which is bigger than 1 over x. And again, doing the same thing we just did, that would give us, let's see, multiplying by x and dividing by m would give us x bigger than 1 over m. And so we have 1 over m is less than x, which is less than n. So we have this here. So what we'll do now is we need to get the same number here. So what we'll do is we'll take the maximum of these two numbers, and things should work out. Why the maximum? I'll explain in the proof why the maximum should work. Let's go ahead and start writing our proof, and we have to do this all over again in the proof anyways. So it says, prove that if x is a positive real number. So that's our hypothesis. So we start by writing down, suppose x is a positive real number. So positive real number. Okay, and the goal is to create this inequality over here. All right, so now we can use the Archimedean property on x. So since x is a real number, so since x is an element in the set of real numbers, by the Archimedean property, or Archimedean principle, I'll say by the AP, there exists, so I'll use a backwards E for there exists, and I don't want to use N or M. I'm going to use a different letter because I want N to be my final letter, so I'm going to use N1. N1 in the set of natural numbers such that N1 is bigger than X. So this means that x is less than n1. And as we figured out in our scratch work, in order to come up with this, which is not the final answer, but it's close to it, we need to use 1 over x. So note, x is positive, so 1 over x makes sense, right? It's a real number. It est 1 over x is in the set of real numbers. So by the Archimedean principle, so by the AP, there exists a natural number, possibly a different one. We cannot guarantee it's the same one, so therefore we must use a different symbol. So n sub 2 in the set of natural numbers such that n sub 2 is greater than the number 1 over x. And again, multiplying by x and dividing by n2, this would imply that x is bigger than 1 over n2, or rather 1 over n2 is less than x, right? Reading it backwards, which is less than n1. So we're here. This is where we were in the scratch work, and I said I would explain what to do now. So the idea is to take the maximum of these two. So we're going to set lowercase n to be equal to the maximum of n2 and n1. And let me explain why this will work. So first of all, if n1, you come over here, this is scratch, this is not part of the proof. So scratch. So n1 is going to be less than or equal to capital N. So I guess I can mention that in the proof. So note, x is less than n1, which is less than or equal to lowercase n, because n is the maximum of n1, n2. Okay, so why did we use the maximum even though we have 1 over n2? That's the confusing part. Let me write this backwards. X is bigger than 1 over n2. Right? This is a fraction. So if x is bigger than 1 over n2, it's going to be bigger than 1 over any number, anything bigger than n2. Right? So like, let's say x is bigger than 1/2. Well, if it's bigger than 1/2, it's certainly bigger than 1 over 99. And 99 is bigger than 2. So that's why taking any number bigger than n2 also works. But that's not enough. Let's justify it in the problem. So note, n is also less than or equal to, or greater than or equal to, rather, n2, right? Because n is the maximum of these two. So that means that 1 over n2 is greater than or equal to 1 over n. Right? Writing this backwards, this says that 1 over n is less than or equal to, right, reading it backwards, 1 over n2, which is less than x, which is less than n1, which is less than or equal to n. That, my friends, is beautiful. So this means that 1 over n, take the strongest inequality, take the strong one, less than x, which is less than n. And that, and that completes the proof, right? So we have 1 over n less than x, which is less than n. Let me write it again so it's a little more clear. 1 over n less than x less than n. And that finishes the proof. So I kind of figured it out a little bit on the spot, so it wasn't maybe the cleanest argument or the cleanest explanation, but it was a correct one, and hopefully by doing it this way, by not having it like all prepared out and showing you how I figure it out, hopefully you can learn how to write proofs as well. It's hard, and the thought process is difficult. So I hope this video has been helpful. That's it.
If G is a group such that x squared equals e for all x in G, then G is abelian. Let's prove this. So proof. The first thing to notice is this right here. This pretty much tells you that every element in the group is its own inverse. It's obvious. If it's not, take x and G and notice that x equals e. This is pretty much the definition of inverse. If you have xy equals yx equals e, then y is the inverse of x. Well, we have xx equals xx equals e. So x is x inverse. If you prefer a more formulaic approach, you can multiply both sides by the inverse and show that x is its own inverse. In any case, let's show it's abelian. So suppose x and y are elements of G, and we need to show that x times y is equal to y times x. So then, and this is a really, really cool proof, x times y, well, every element is its own inverse. So this is actually equal to xy inverse. And there's a formula for this. This is y inverse, x inverse. But again, every element is its own inverse, so you get yx. That's it. So G is abelian.
Suppose R is a commutative ring with identity and I is a proper ideal. We want to prove that I is a maximal ideal if and only if the quotient ring is a field. So we'll start by assuming that I is a maximal ideal. So suppose I is a maximal ideal. And the claim here is that the quotient ring is a field. So suppose that we have some, say, I plus A in the quotient ring, such that I plus A is non-zero. So it's not equal to the zero element. Okay. Note what this means. This means that A is not an I. So that's going to be quite useful. Okay, now we somehow need to produce a unit, right? We need to produce a unit, a non-zero element in the quotient ring, such that when we multiply it by I plus A, we get the identity in the quotient ring. So in order to use maximality, in order to use the fact that I is maximal, we need to create a larger ideal, an ideal that's larger than I. So consider the following ideal, which we'll call, I'll call it J. So we'll set J equal to I plus the ideal generated by A. So this is so it'd be A times 0 plus 0 times D, just regular matrix multiplication. This is the second row first column, so we use the second row first column. That'll be 0 times C plus B times 0. And the last one, I'll just go quickly, be 0 times 0 plus B times D. All right, there's a lot to verify in this video, so feel free to fast forward because it's a long proof. So this is equal to AC 0, 0, BD. And this is an S, and it's important to say why. This is an S because AC is not 0, and that's true since A is not 0 and C is not 0. So that needs to be said, right? So AC is non-zero because the individual elements are not 0. Likewise, BD is not 0 since B is not 0 and D is not 0. So there needs to be an AND here. And, right? So everything has to be justified in proofs like this, right? You want to justify every single step. Leave nothing to the imagination. Right? Show all the work. All right, so this shows that star is a binary operation on S, right? We took two matrices in S, and we showed the product was an S. Thus, star is a binary, I'll just say bin op, on S. That proves that. Now we just have to go through the conditions. I think the most tedious will be associativity, so we'll do that one first. So now let's go ahead and show associativity. So I'll put a 1 here, and let me switch colors, and I'll just say associativity. So this is what we're showing in this step. So we have to show, let me write it again over here, that for any, let's say for any x, y, z, in G, this is the general statement of associativity, x star y star z is equal to x star y star z. It's funny, I just realized something. Up here, when we were talking about the criteria for a group, I used A, B, C for associativity, then I just switched to x and y later on. No big deal. No cats were killed. So that's the associativity criteria. So we need to take 3 matrices this time. So take any. So we need 3 of these guys. Let's say let's use A again. A 0, 0 B. Then we have C 0, 0 D. And then we have let's see, I guess the next letter would be E 0, 0 F, and S. So we no longer have to go through all of this stuff for this step. We just have to show that this is true, right? Without the operation symbols written, it's x, y, z equals x, y, z. That's what we have to show, right? That's what we have to show. So the easiest way to do it is just to compute one side, then compute the other side, and then just observe they're equal. So then, Let's start with the left-hand side. So let's look at parentheses A0, 0B, parentheses C0, 0D. I'm going to try to go slow because I do not want to mess up. It's a very long problem. Parentheses E0, 0F. Okay, so we take the product of these first two, and we already did it up here. So I'm going to go ahead and cheat and show that. By the way, when you're multiplying these, you notice you just multiply the corresponding entries, right? Look, it's AC, BD. That will always work when you're multiplying diagonal matrices. So we can take that shortcut in our work. So this is equal to AC 0, 0, BD. You can always do that to multiply diagonal matrices. Then we have E0, 0F. And using our little trick, that's ACE, AC times E. Right? And then this is in parentheses if we really want to be picky. Right? And then 0, 0, and then this is BD, F. And associativity of real numbers says we can drop the parentheses, right? So because A, B, C, D, E, F are real numbers, they are. Multiplication is associative. I'll just say ASS. So we can drop the parentheses. You could be a little more elegant and rearrange it and work backwards, but I'm not going to do that. So we have this, and we can drop the parentheses. There's no ambiguity because multiplication of real numbers is associative. Now let's work out the other side. So the other side also, let me say also, we switch colors. This time it's going to be A0, 0B times, and then here we have C0, 0D, and then E0, 0F. Okay, so now we work out this product here on the right first. So this is A0, 0B, and this here, you just multiply the entries, right? So CE, 0, 0, and then DF. Going kind of fast, you do it one more time, and you get A times CE, if you want to be picky, 0, 0, B times DF, again, if you want to be picky. And then again, same reason here, because the multiplication of real numbers is associative, you can drop the parentheses, right? The notation is non-ambiguous, so you have 0 BDF. So the left-hand side is equal to the right-hand side, so this is equal to this, right? Because they're both the same thing. And so star is associative, so thus star is associative. And really, you'll notice that associativity of star follows because associativity of real numbers. So that's key. That's key. All right, two more conditions. We're already past 11 minutes. Sorry. But it's good to go through it. So it's good to, hopefully someone out there is watching this and you have an example where every step is carefully shown. Again, feel free to fast forward. The next condition is the existence of inverses, right? So, identity. We have to show that there exists an identity element. So remember, the condition says there exists E in G such that for all x in G, xe equals x and ex equals x. So you first have to show existence of the identity element. So our identity element is just going to be the identity element we know from regular matrix work. So regular matrix multiplication. So this element here is a diagonal matrix, and this is an S, and that's because 1 is not equal to 0, right? Remember, S is the set of all elements A, 0, 0, B, where A and B are not equal to 0. So this element is certainly an S. And the claim is that this is the identity. So we have to show that for every element X and G, xe is equal to x and ex is equal to e. So take any matrix. So take any element. So take any element. So A, 0, 0, B, and S. This is like our x. Then we just have to show that when we multiply our element by our proposed identity, we get back our element on both sides. So A, 0, 0, B times 1, 0, 0, 1. And we know that this is a times 1 using our multiplication trick, 0, 0 times 0, which is 0, b times 1. And 1 is the identity in the set of real numbers, right? So in terms of multiplication, this is a0, 0b. So that checks. Going the other way, we should get exactly the same thing, right? We have 1, 0, 0, 1, a0, 0b. And this is equal to 1 times a, going really fast, 0, 0, 1 times b. Running out of time. And this is equal to a, 0, 0b. So this shows that our little matrix is indeed the identity element. So this shows 1, 0, 0, 1 is our identity element. Okay. So notice how we first had to specify that was an S, and then you do the condition, because the existential quantifier comes first. The very last step is to show the existence of inverses. So inverses. And then we're done. We've shown this set is a group. So inverses. So given any element, here's the criteria. So for all x in G, we have to show there exists a y in G such that x times y is equal to E and y times x is equal to E. Later on, if you study more group theory, you'll learn that if you have a one-sided inverse, you have a two-sided inverse, as long as you have all the other conditions as well. All right, so we have to take any x in G. So we'll start by taking a matrix. So take any A0, 0B in S. So then A is not equal to 0, and B is not equal to 0. So note, now we have to show the existence of y. So our inverse matrix is going to be 1 over A, 0, 0, 1 over B. How did I know that? I just know stuff from algebra, from linear algebra, right? So if you have a diagonal matrix, the inverse is going to look like this. And note that this is an S, so we have to show there exists a y in G. G is S right here, right? And this is because 1 over A is not 0, and 1 over B is not 0. And this is since A and B are not 0. Right, so these guys are all good because A and B are not 0. So this is an element of S. So we took an x and G, we showed the existence of y. Now we have to verify that this is indeed the inverse. So we have to take the multiplication on the left and on the right. So let's do it. So then A0, 0B time. And the structure is important, right? It's really key to do everything in the correct order. You have to do this first, then you have to do this, and then you do this, right? It's a proof. It's beautiful. So it's A times 1 over A, 0, and then 0 times 0 is 0, and then B times 1 over B. And that's equal to our identity element. And then we do it the other way, 1A. And it's obvious, but sometimes, well, not sometimes, when you're proving things, again, when you're first learning, nothing is obvious, especially when you're proving something like this. 1 times A, 1 over A times A, 0, 0, 1 over B times B. And so this is 1, 0, 0, 1. So this shows that we have an inverse. So thus, 1A, 0, 0, 1B is the inverse. I mean, you're supposed to say is an inverse, right? You can prove the inverse is unique later, but let's be a little bit abusive. Is the inverse of A0, 0B. Yeah, I mean, we haven't necessarily proved that inverses are unique yet if we're just starting the theory of groups, but inverses are unique, so you can say the inverse instead of A inverse. That's it. So thus S star is a group. Wow, 17 minutes. I believe I have another video showing another set is a group. It's a little bit harder, actually a lot harder than this one. I'm not sure why this one took so long, but that's it. I hope this has been helpful to someone out there in the world. In this video, we're going to look at a very specific binary operation and then prove that it is indeed an associative binary operation. So here's the setup. So capital X will be a set. So this is a set. And we're going to look at a set which is called the power set of capital X. this is equal to the set of all subsets of capital X. And what we're going to do is define a new binary operation, one that's different from union and intersection and set difference. It's called the symmetric difference. So the notation we'll use is a triangle. The triangle will denote the symmetric difference operation. So for two sets, for say capital A and capital B, in the power set of capital X, in other words, they are subsets of capital X, we'll take A and we'll take the symmetric difference of A with B. And we'll define this to be all of the elements in A, but not in B, or, so union, all of the elements in B, but not in A. Let me write this down in English right below. This is the set of all elements that are in either A or B, but not in both. Okay, but not in both. That means if you write the symmetric difference of A with B in set builder notation, this is the set of all X, such that X is in exactly one of AB. Okay, very, very useful to think of it this way. So X is in exactly one of AB. So if you have an element X that is not in your symmetric difference, okay, this is equivalent to saying that X is in either 0 or 2 of AB. So if it's in the symmetric difference, it's in exactly one of AB. So if it's not, it can't be in exactly one of AB. It's either in none of them or in both of them, right? So very, very useful. And so it turns out that the triangle, so used to using star for binary operations, that the symmetric difference is a binary operation. So it is indeed a binary operation on the power set of capital X. Okay, so it's a binary operation. It's also a commutative. So let me squeeze this in here. So it's commutative. It's a commutative binary operation on the power set. So in this video, we're going to focus on the proof of associativity. So let's carefully do that. So proposition. And the claim here is that the symmetric difference is associative. So we're going to prove that it is an associative binary operation on the power set of capital X. So we'll start by looking at A, and we'll take the symmetric difference of that with this. And we're just going to write it down in set builder notation. So we're not taking an element and showing the sets or subsets of each other. No. This is a much nicer proof. So what does it mean for an element to be in the symmetric difference of A with B symmetric difference C? Well, it means it's in exactly one of them. So X is in exactly one of A, and then B symmetric difference C. That's what it means to be in that set. This is the set of all X such that, well, now let's rewrite what it means to be in exactly one of these two sets. That means that X is in A, and X is not in the other set. So X is not in B symmetric difference C. Or it means X is not in A, and x is in the symmetric difference of B with C. So all we did was rewrite what it means to be in exactly one of those sets. Let's keep going. So this is the set of all x such that, well, let's take care of the first line here. Let's rewrite this. So this means x is in A. And, okay, now what does it mean to not be in the symmetric difference of B and C? It means it's in none or it's in both. Let's do the case where it's in none first. So that means x is not in B and x is not in C. Or, again, x is in A. And this time we'll look at the case where it's in both. So it's in B and it's in C. So everything we've written down so far is only for, here I'll circle it, only for this. Right? We rewrote this, and that means everything here. That means all of this stuff. Okay. Now let's look at the second line. So x is not in A. And, well, what does it mean to be in the symmetric difference? It means it's in exactly one of BC. So let's look at the case first where it's in B and it's not in C. Should have an or here, or. And then, again, x not in A. And the case where it's not in B and it is in C. So it's in exactly one of BC. And let's close our set notation here. And here is the really cool part. So this is equal to the set of all x such that, well, in the first case, x is only in A and it's not in the others. In the second case here, it's in all three. In the third case, it's only in B. And in the last case, it's only in C. So x is in exactly 1 or 3 of ABC. Right? We can write it that way. So x is in exactly 1 or 3 of ABC. Now we'll look at A symmetric difference B, symmetric difference C. And we'll show it's equal to exactly the same thing. So this is the set of all x such that. Now what does it mean to be in the symmetric difference of this with this? It means x is in exactly one of A symmetric difference B, C. Let's keep going. Let's rewrite this. So let's write down what it means for x to be in exactly one of these sets. So that means that x is in the symmetric difference of A with B, and x is not in C, or x is not in the symmetric difference of A with B, and x is in C. That's what it means to be in exactly one of those sets. So I hope this makes sense so far. You really have to think carefully, but once you get it, it really is an amazing argument. All right, now again, we're going to focus on this first line here. So what does it mean to be in the symmetric difference of A and B? It means it's in exactly one of them. So x is in A, and x is not in B. That could be one case. And then we still have this x not in C. Or, and the other case would be x is not in A, and x is in B. And then here we still have this piece, x not in C. Or, now we'll go to the third line. So if x is not in the symmetric difference, that means it's in 0 or it's in both. Let's look at the case where it's in 0 of them. So x is not in A, and x is not in B. And then we still have this piece here, and x in C. Or it's in both. So x is in A, and x is in B, and x is in C. Let's think about this carefully. Let's keep going. We're almost done. So this is the set of all x such that, well, let's see. Yep, it looks like in the first case, x is only in A. In the second case, x is only in B. In the third case, x is only in C. And the last case, x is in all of them. So x is in exactly 1 or 3 of ABC. Well, when we started the problem, we showed that if you take this is the set of all x such that x is in exactly 1 or 3 of ABC. Then we looked at it the other way. We did this, and we got the same thing. So x is in exactly 1 or 3 of ABC. So we showed that if you take A, symmetric difference, B, symmetric difference C, you get A, symmetric difference, B, symmetric difference C. Thus, the symmetric difference is associative on the power set of a set. So I hope this video has helped someone out there. I personally think this is a really, really nice argument. Yeah, I hope this helps. If A is congruent to B modulo n, then B is congruent to A modulo n. Proof. We'll start by assuming that A is congruent to B modulo n. So suppose A is congruent to B modulo n. This means A minus B is a multiple of n. So how do you write that? Well, you write A minus B equals K times n, where K is an integer. So this is precisely what it means for A to be congruent to B modulo n. It means A minus B is a multiple of n, or A minus B is equal to an integer, here that's K, times n. All right, we have to show that B is congruent to A modulo n. That means we need to show that B minus A is a multiple of n. So we somehow need to get B minus A from here. That's pretty easy because if we factor out e-1, we get B minus A. And that's equal to K times n. Now you just divide by -1, so B minus A is equal to negative K times n, where negative K is indeed an integer. So we've shown that B minus A is equal to an integer times n. That's exactly what it means for B minus A to be a multiple of n. In other words, B is congruent to A modulo n. Prove A is congruent to A modulo n. Proof. So all we have to show is that A minus A is a multiple of n. So we start by writing it down. So A minus A, that's equal to 0. Okay, we're almost done. So A minus A, well, we want to show it's a number times n. Well, we have 0, so we're kind of stuck with it. So let's write it as 0 times n. And here 0 is an integer. So we've shown that A minus A is equal to an integer times n. That's exactly what it means for A to be congruent to A modulo n. Alright, this is a really nice problem. If A is congruent to B modulo n, and B is congruent to C modulo n, then A must also be congruent to C modulo n. Let's prove this. So proof. We'll start by assuming that A is congruent to B modulo n, and B is congruent to C modulo n. So suppose A is congruent to B modulo n, and B is congruent to C modulo n. This means a couple things. This means that A minus B is a multiple of n. It means that B minus A is a multiple of n. It means that n divides A minus B. It means that n divides B minus A. Let's just stick with A minus B is a multiple of n. So then A minus B is a multiple of n. So we can write it as K times n. And likewise, B minus C is a multiple of n, so we can write it as R times n, where K and R are integers. So now we have to prove that A is congruent to C modulo n. So we have to show that A minus C is a multiple of n. So the natural way to start is by writing, so then, we write a minus c, and we have to show it's a number, an integer, times n. Well, here we have a, and here we have b, and here we have c, and here we have b. You'll notice that b appears twice. So let's write this as a minus b. We somehow have to use this, so might as well write it down, plus b minus c. And you'll notice that these equal 0. And that's the beautiful thing, because this is equal to kn plus this, which is equal to rn. And then we'll factor out the n. So this is k plus r times n, where k plus r is indeed an integer. So we showed that a minus c is equal to an integer times n. In other words, a minus c is a multiple of n. So this means a is indeed congruent to c modulo n. It's not a hard problem, but I think it's worth doing. Okay, so we're going to prove this property of exponents for all positive integers. So here a and b are fixed constants. We're going to do this via mathematical induction, so proof. So the statement we're proving is this one. This is our S sub n. And so we'll start with the base case. Now, we're starting at 1, and the reason is we're showing this is true for all positive integers, and the smallest positive integer is 1. So we start the base case at 1. So on the left-hand side, we just get ab to the first power, so that's ab. On the right-hand side, we just get a to the 1, b to the 1, which is also ab. Well, sure enough, the left-hand side is equal to the right-hand side, so S sub 1 is true. So we have shown that the base case is true. The next step is the induction hypothesis. In this step, we assume that our statement is true for some arbitrary positive integer k. So now what we'll do is we'll write down S sub k. Well, S sub k, all you do to figure out what that is just plug in k. And we'll assume this is true for some arbitrary, I won't write that down, I'll just put k, which is a positive integer. The last step is the induction step. We have to show that our statement is true when n is equal to k plus 1, so the induction step. So it's really, really helpful to write down what we need to show. So we need to show ab to the k plus 1 is equal to a to the k plus 1, b to the k plus 1. Now, if you just write this down without writing, we need to show, someone can read your proof and think that you don't know what you're doing. So we need to actually prove this, right? So it's important that if you write it down, maybe you go to the side. That's why I put it in parentheses. This is not part of the proof. This is just for our own benefit, so we can prove it. Okay, so not part of the proof. All right, so to prove this, we'll start by writing this side down. So let's look at ab to the k plus 1. And we have to show it's equal to this. All right, well, we can do this. ab to the k, ab to the 1. And this right here, well, we know what this is, right? It's up here. And it's equal to this. So in this step, we use the induction hypothesis. So we get a to the k, b to the k, times ab. Multiplication of real numbers is commutative, so we end up with a to the k plus 1, b to the k plus 1. So we started with this, and we showed that it's equal to this. That was precisely what we needed to show, so S sub k plus 1 is true. And when you finish, you just write something down, so maybe, therefore, by PMI, S sub n is true for all positive integers, and that's it. Pretty easy problem. Okay, we're going to show that the sum of the first n integers is equal to n times m plus 1, all divided by 2 for every positive integer. We'll do this via induction, so proof. There's lots of ways to write an induction proof. Let's just show all the steps. So we'll start with the base case. Alright, so in this case, the base case starts at 1. Why? Well, we're proving this is true for all positive integers, and the smallest positive integer is 1. So we have to check our statement when n is equal to 1. Now what is our statement? We have to prove this. So in all of this, this is our S sub n. Alright, so let's look. So the left-hand side is equal to 1. Right, there it is, 1. The right-hand side is 1 times 1 plus 1 over 2. So this is 2 over 2, which is 1. So all we did was plug in 1 into the right-hand side. So the left-hand side is equal to the right-hand side, so S sub 1 is true. All right, now we'll write down what's called the induction hypothesis. So induction hypothesis. The induction hypothesis basically says that we get to assume that S sub n is true for some arbitrary positive integer k. So suppose, now what we'll do is we'll write down S sub k. That's just basically 1 plus 2 plus dot 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 plus k is equal to k times k plus 1 all over 2. And this is for some arbitrary, I won't write it, k, which is a positive integer. All right, the next step is the induction step, okay? The induction step, so I'll write it down, induction step. We need to show that our statement S sub n is true when n is equal to k plus 1. So let's write down what we need to show. We need to show that 1 plus 2 plus dot 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 plus k plus 1 is equal to k plus 1. K plus 1 plus 1 is k plus 2 over 2. So this is what we need to show. This is not part of the proof. This is just a note that I wrote down just to help us do it. So in order to show that this equality is true, we'll start by writing down the left-hand side. So note 1 plus 2 plus dot 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 plus k plus 1. Well, we somehow need to involve our hypothesis. That's super important. You always have to use the induction hypothesis. What we can do is we can think, what's the number right before k plus 1? Well, that's k. So you can write this as k plus k plus 1. And then right here, this is right here. And it's equal to this. So here we use the induction hypothesis. This is k plus 1 over 2 plus, and this hangs out, so we still have k plus 1. So this is the key step in the proof. This is where we use the induction hypothesis. It's always really good to be aware of that. All right, let's keep going. We can add these, so this is k plus 1 over 2 plus 2k plus 1 over 2, right? Find a common denominator. And now it's just a little bit of algebra and we should be done. So let's see, this is k squared plus k distributing, and then plus 2k plus 2 all over 2. This ends up being k squared plus 3k plus 2 all over 2. This should factor. It's k plus 1, k plus 2 all over 2. Yep. So S sub k plus 1 is true. So therefore, by the principle of mathematical induction, PMI, S sub n is true for all positive integers. This was probably the easiest induction proof we could do. This is like the hello world of programming. Being asked to prove this inequality is true for all real numbers a greater than or equal to -1 and for all positive integers n. This is called Bernoulli's inequality. Let's go ahead and prove it. To prove this, we'll use induction. So this has to hold for all a greater than or equal to -1. So we'll start by supposing a is greater than or equal to -1. And now we'll use induction on this. We'll think of this as our statement S sub n. Let's start with the base case. So base case. So for the base case, we're proving it's true for all positive integers. So we have to start with the smallest one, which is n equals 1. So on the left-hand side, if we replace n with 1, we get 1 plus a to the 1, which is simply 1 plus a. And on the right-hand side, we get 1 plus 1 times a, which is simply 1 plus a. So the left-hand side is 1 plus a, the right-hand side is 1 plus a. 1 plus a is certainly greater than or equal to 1 plus a. In particular, it's equal to. So our statement is true for n equals 1. So S sub 1 is true. So the base case is taken care of. Now let's go ahead and write down the induction hypothesis. So induction hypothesis. So for the induction hypothesis, we'll suppose our statement is true for some positive integer k. So suppose that 1 plus a to the k is greater than or equal to 1 plus ka for some positive integer k. So for some k in the set of positive integers. This here is the set of positive integers. Now let's do the induction step. So induction step. This is the meat of the proof. So induction step. So I'm going to go ahead and write down what we need to show before we show it. It helps to know where you're going. Otherwise, it's very hard to get there. So we need to show that our statement is true when n is equal to k plus 1. So we need to show that 1 plus a to the k plus 1 is greater than or equal to 1 plus k plus 1 a. That's what we have to show. Now let's go ahead and show it. So note, we'll start with the left-hand side and show that it's greater than or equal to the right-hand side over there than this. So 1 plus a to the k plus 1, well, that's equal to 1 plus a to the k times 1 plus a to the 1, right? Just using properties of exponents. Now, we know something about 1 plus a to the k. 1 plus a to the k is greater than or equal to 1 plus ka. So what we can do is we can insert a greater than or equal to sign here and replace this piece here with 1 plus ka. And this piece here just hangs out. So here we have 1 plus a. Now it's important to notice that 1 plus a is greater than or equal to 0. That's because a is greater than or equal to -1. So that means we don't have to switch the inequality or anything like that. Because if this was negative, it could be problematic possibly. All right, so 1 plus a to the k is greater than or equal to 1 plus ka. At this point, there's not much we can do except maybe distribute everything. So let's see, 1 times 1 is 1. 1 times a is a. And then the inside terms, that's ka. And then the last terms, that gives us ka squared. And let's see if we can write this in a way that's beneficial to us. I probably should have written something down, but this was by the induction hypothesis. Okay, so we want 1 plus k plus 1a. Let's see, we have the 1 here, and then here we have k plus 1a. And then we have this straggler here, ka squared. Well, we know that a is greater than or equal to -1. That means a squared is greater than or equal to 1. So this is greater than or equal to, well, it's greater than or equal to 0. Right? A could be 0 in all of this, and if it is, then this is 0. So we can certainly say this is greater than or equal to 0. So this is greater than or equal to 1 plus k plus 1a. And that's it. So we showed that 1 plus a to the k plus 1 is greater than or equal to this. So s sub k plus 1 is true. Therefore, by the principle of mathematical induction, s sub n is true for all positive integers n. So that's it. Prove 2 to the n is greater than 2 times n for all n greater than or equal to 3. Let's go ahead and prove this using mathematical induction. So proof. So in our proof, this inequality here will denote s sub n. So in the base case, we have to make sure that s sub n is true when n is equal to 3. So this induction proof actually starts at 3 because n is greater than or equal to 3. So let's see. When n is 3, the left-hand side is 2 cubed, which is 8. And the right-hand side is 2 times 3, which is equal to 6. So the left-hand side is greater than the right-hand side. So 8 is bigger than 6. That's obvious. So s sub 3 is true. So that takes care of the base case. The next step is the induction hypothesis. Induction hypothesis. In this step, we assume that s sub n is true for some k. So we suppose that s sub k is true. Well, what is s sub k? We just replace all of the n's with k's. So we suppose that 2 to the k is greater than 2 times k for some k greater than or equal to 3. So that's the induction hypothesis. The third step is really the meat of an induction proof. It's the induction step. So the induction step, here we need to show that s sub n is true when n is equal to k plus 1. So we claim that 2 to the k plus 1 is greater than 2 times k plus 1. So this is what we actually have to prove. And that's why I wrote claim, to let the reader know that we're not just writing this down. This is what we have to prove. We can distribute the 2. So this is 2k plus 2. So if we show that 2 to the k plus 1 is greater than 2k plus 2, we're done. So let's go ahead and do it. So note, we'll start by writing down the left-hand side. So 2 to the k plus 1. And this is equal to 2 to the k times 2 to the 1, because you add the exponents when the bases are the same. Why did we do that? Well, we want to use the induction hypothesis, and now we're in a position to do that. We know that 2 to the k is greater than 2k, so this is greater than 2k times 2. Now we want 2k plus 2, so we need to have a sum. So the natural thing to do is write this as 2k plus 2k. Right, we have two 2k's, right? Two of them, so that's just 2k plus 2k. Now we're going to use the fact that k is greater than or equal to 3. So this is greater than or equal to 2k. I'm going to keep this one because that's what we want. And I want to replace this with a number. So plus 2 times 3, because k is bigger than 3. So we can do that. We can just replace the k with the 3 and insert the appropriate inequality there. So this is equal to 2k plus 6. Now we want it to be greater than 2k plus 2. Well, we know that 6 is greater than 2, so this is greater than 2k plus 2. So we've shown that 2 to the k plus 1 is greater than 2k plus 2. So s sub k plus 1 is true. So by the principle of mathematical induction, our statement s sub n is true for every positive integer n greater than or equal to 3. And that completes the proof. A lot of times people have a hard time with this right here, with all of the inequalities. When I do this on my own and no one's looking, uh, I do it in a straight line. So let me show you another way. This is probably even more confusing, but why not? The way I would do it, if I wasn't making a video, I would write it like this. 2 to the k plus 1, well, that's 2 to the k times 2. And we know that that's greater than 2k times 2, because 2 to the k is greater than 2k. And we want to write this as a sum because we have a sum over here. So we can write this as 2k plus 2k. And this is greater than or equal to 2k plus 2 times 3. And this is greater than 2k plus 2. So that's how I would do it if I was rushing through it. I hope this helps. Just keep in mind that because 2 to the k is bigger than 2k, when we're going from here to here, we can just replace this with this and insert the appropriate inequality. Likewise, when we're going from here to here, because k is bigger than 3, we can replace 2k with 2 times 3 and insert the appropriate inequality. I hope this helps. So in this problem, we're going to prove that every subset of a linearly independent set is also linearly independent. So here's the setup. We have V, it's a vector space over a field F, and S is a linearly independent subset of our vector space. And we're going to prove that every subset of S, every single one, is also linearly independent. So proof. Now, since we have to prove that this is true for every single subset, we have to start by taking an arbitrary subset. So suppose S prime is a subset of S. Now we need to show that S prime is linearly independent. That means that whenever we have a linear combination of vectors in S prime equal to the 0 vector, all of the scalars must be equal to 0. So suppose that we have such a linear combination. So let's write that as C sub 1 times V sub 1 plus dot 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 plus C sub n times V sub n equal to 0. Now we have to show that all of the C sub i's are 0. Now we should say something about these v's, so it's usually better to write something like for some V sub 1, V sub 2, dot dot dot, V sub n in S prime, and C sub 1, dot dot dot, C sub n in capital F. So again, we have to show that all of the C sub i's are 0. Now here's the trick. S prime is a subset of capital S. So all of the V sub i's, since they're in S prime, they're also in capital S. But capital S is independent, so all of the C sub i's must be 0 by definition of independence. Let's just write all that down. So since S prime is a subset of S, and these guys, these little v's, are in S prime, then our little guys here, they're also in S. So now we have a linear combination of vectors in S. So this is actually a linear combo of vectors in S, and it's equal to the 0 vector. So by definition of linear independence, we have that all of the C sub i's are 0. So let's write that down. So since S is linearly independent, C sub 1 is 0, C sub 2 is 0, dot dot dot, C sub n is 0. Therefore, S prime is linearly independent. Let's go over it one more time. So you start by taking a subset of S. We call that S prime. And you start by writing down a linear combination of vectors in S prime, and you set it equal to the 0 vector. Now you have to show that all of these guys are 0. That's what it means for S prime to be independent. Whenever you have a linear combination of vectors in S prime equal to the 0 vector, then all of the scalars should be 0. Since S prime is a subset of S, all of the vectors are also in S. So you really have a linear combination of vectors in S, but S is independent, so all of the scalars are 0, and we're done. I hope this helps. Hi YouTube. In this video we're going to continue our discussion of what we're calling the standard topology on the set of real numbers. Recall that a subset of the real numbers U is said to be open in this topology if for every x in the set U we can find some epsilon greater than 0 such that we have a neighborhood of x that is entirely contained in U. That's what it means for a set U to be open in what we're calling the standard topology on R. So in this video we're going to just prove a lemma. So I'm calling it a lemma because we're going to use this to prove at some point that the standard topology on R is in fact a topology. So this is one of the criteria required for something to be a topology. So the lemma states that the union of any family of open sets is open. So we're going to prove that the union of any family of open sets that satisfy this criteria is also open. So proof. So we'll start by considering a family of open sets. So let V sub I, as I runs through some index set, be a family of open sets. And now we're going to consider the union of this family. So set, let's call it W. Set W equal to the union of the VIs. And the claim is that W is an open set. So claim W is open. So we'll take some x in W, and then we have to show that there is an epsilon neighborhood about x that's completely contained in W, and that will complete the proof. So take any x in W. Well, that means that x is in the union of the v's. So then x must be in at least one of these. So x is in v sub j, let's say, for some j. Now, since x is in v sub j, and v sub j is open, it's an open set, there exists some epsilon greater than 0, such that there is an epsilon neighborhood about x that's entirely contained in v sub j. But v sub j is entirely contained in the union of the VIs, which is equal to W. So that means that this epsilon neighborhood is entirely contained in W. So given any x in W, we found an epsilon greater than 0, such that we found a neighborhood of x contained entirely in W. This is precisely what it means for W to be open. So this is precisely what it means for W to be open. And the proof is complete. Thanks for visiting my channel. I hope this video has been helpful. Hi YouTube. In this video we're going to continue our discussion of what we are calling the standard topology on the set of real numbers. So to define a topology you have to define what an open set is. So we are saying that an open set U, so U, a subset of the real numbers, is open if for all x in U, we can find some epsilon greater than 0, such that we have a neighborhood about x that's contained entirely in U. And we're calling this a topology, but we haven't quite proved it's a topology. So in this video, we're going to prove the last piece, and after this last piece, we'll officially be able to call it a topology. So we have another lemma. And this lemma is that the intersection of any finite family, so of any finite family of open sets is open in this topology. So proof. So to start the proof, we'll start by considering a finite family of open sets. So suppose that we have V sub 1 through V sub n. Suppose these are open sets. And now we have to consider the intersection of these sets. So let W be equal to the intersection of this finite family as I runs from 1 to n. So to show W is open, we have to take an x in W and show there is an epsilon neighborhood about x entirely contained in W. So our claim is W is open. And so we'll start again by taking an x. So take any x in W. So the natural thing to do now is write down what it means to be in W. So if x is in W, x is in this intersection. If it's in the intersection, that means it's in each of these V sub i's. Then x is in V sub I for I equals 1 to all the way to n. It's in each one of these, right? It's in V sub 1, and V sub 2, and V sub 3, and so on. It's in all of them. Since x is in V sub I, and V sub I is open, just reiterating it for clarity, so we have x in V sub I, and V sub I is open. So using the definition of open, there exists some, say, epsilon I, such that we have a neighborhood about x contained in V sub I. And this is true for each I, so from 1 and so on. So this statement is true for each I. So for each I, this is true. So we have a finite number of epsilons. We have epsilon sub 1, epsilon sub 2, all the way to epsilon sub n. And we want to find an epsilon that's small enough so that we can create a neighborhood around x that's contained in all of these V sub i's. So the key idea here is, a key idea in all of mathematics, is that whenever you have a finite set, you can take the minimum. Okay, so we're going to set epsilon equal to the minimum of epsilon sub 1, epsilon sub 2, ... epsilon sub n. So our epsilon will be the minimum of these. Then, for each I, so 1, 2, all the way to n, x minus epsilon, x plus epsilon, this set is contained in all of these other ones. It's contained in each one of these. And each one of these is contained in V sub I. So for each I, this set, this epsilon neighborhood, is contained in this set, which is contained in V sub I. So for each I, our epsilon neighborhood is contained in V sub I. Hence, our epsilon neighborhood is contained in the intersection of the V sub i's. Right? It's contained in each one, so it's therefore contained in the intersection, which is what we said was W. So given an X and W, we found an epsilon greater than 0 such that there was a neighborhood of X entirely contained in the intersection. I forgot to put the subset symbol there, so I'm glad I went over it again. That's it. That completes the proof. So now we've essentially proven that this is a topology, right? So recall the definition of a topology was that the entire set and the empty set were open. So I think in the first video we proved that the real numbers and the empty set were open, so are open, using this definition of open sets. 2, we proved that the union of any family of open sets is open. I believe that was the previous video. And then 3, in this video, we proved that the intersection of any finite family of open sets is open. So we proved all 3 of these things, and that means that our topology is indeed a topology. So therefore, we have a topology. We have a topology on the set of real numbers. And our topology is defined, again, by the way we define open sets. So when you're dealing with topology, you define what it means for a set to be open, and then if you satisfy these 3 conditions, then you have what's called a topology on your set. So I hope this video has been helpful. That's it. Let X be a topological space and Y a subset of X. We're going to define open sets as follows. We're going to say a subset A of Y is open in Y if there is an open set O in X such that this is true. So we're defining what it means for a set to be open in Y. I said define a topology, but in this problem we're actually going to prove that with this definition of open sets, we do have a topology on Y. So proof. This is called the subspace topology. So the first condition we have to show is that both the empty set and Y are open in Y. So we just have to carefully use the definition of what it means for a set to be open in Y. So to show that the empty set is open, we obviously have to write down empty set, and we have to write down an equal sign, and we have to write down Y. And we want to intersect this with an open set in X. Well, the natural choice is to use the empty set. Why? Well, because it's true, and because the empty set is open. The empty set is open in X. And this is true because X is a topological space. So this shows that the empty set is open in Y. And we can do something similar to show that Y is open in Y. We can write Y equals Y intersection X. And X is open in X. Right? This is open in X because X is a topological space. So Y is open in Y. So that shows the first condition, that both the empty set and Y are both open in Y. The second condition is to show that the union of any family of open subsets of Y is also an open subset of Y. So take any collection. So take any collection of open sets in Y. Let's call this collection A, and then let's index it with an alpha, where alpha runs through some index set. And then for each alpha in I, because each of these guys is open, there exists some open subset of X, say O sub alpha, where O sub alpha is open, such that we can do the following, right? What does it mean for each of these A's to be open? It means that A sub alpha is equal to Y intersected with O sub alpha. And this is true for each alpha, right? Now we'll just look at the union of the A sub alphas and hopefully show that it's open in Y. So if we just write it down, we take the union of our A's, a lot of notation here. This is equal to the union of these guys. So Y intersected with our little open guys here, O sub alpha. And again, alpha is running through some index set. And we can use basic set properties and write this as Y intersected with the union of the O sub alphas. I don't know why I put that in parentheses. And just to avoid some writing here, this is open in X. Right? This is open in X because the union of any number of open subsets of X is also open in X because X is a topological space. So we have Y intersected with an open set in X. So this shows that the union of the A's is open in Y. And the last condition is to show that any finite intersection of open sets of Y is also in Y. So suppose A sub 1 through A sub n are open in Y. And what does this mean? This means there exists open sets O sub 1 through O sub n subsets of X. O sub I are all open, such that we can write each of the A sub i's, a lot of notation, as Y intersected with O sub I. Right? Now what we do is we simply look at the intersection of the A sub i's. So it's pretty easy. It's pretty easy. It's not too bad. So we take this intersection. Now, if you're just getting used to working with topological spaces and stuff, the notation is a little bit, it takes some getting used to. So each of these A sub i's is this. So this is the intersection. And this is Y intersected with our little O sub i's. I used O for open, just to make it a little more clear. So this is Y, right, intersected with the, I'll put this in parentheses, with the intersection of the O sub i's. Didn't really have to put it in parentheses there. And this is a finite intersection of open subsets of X. So this is open in X. So we have Y intersected with an open subset of X. So this term here, this whole set here, this is actually open in Y. But what is this? This is the finite intersection of our A sub i's. So this shows that this finite intersection of open sets of Y is open in Y. And that's it, right? We've shown it's a topological space. So when you have these three conditions, again, you say that Y is a subspace of X. This is called the subspace topology or the induced topology on Y. So this Y is a subspace of X. So worth seeing it once. I hope that made sense. Hey, what's up, YouTube? In this video, we're going to show that these two spans are equal. And the way we're going to do it is we're going to use properties of spans. So here are the properties. So first of all, you're allowed to multiply any of these vectors by any non-zero number. If you have zero, the zero vector, you can drop it. And you're allowed to add a multiple of one vector to another. So I can multiply the first vector by 3 and then add it to the second vector if I want to. All right, let's go ahead and do it. Let's prove this. And we're just going to prove it using those things. So we'll start by writing down the left-hand side. So we have span. And I'll write it down again. So we have bracket 6, -2, 0, 0. I'll explain everything I just said again. multiple times as we go through it. So -2, -2, 0, 0. And this is 1, 1, 0, -1. And then we have 0, 0, 0, 2. Okay, so the goal is to make this, what we have here, look like what's over here on the right-hand side. So the way to do this is to work from the right first. You want to aim for this triangular shape. So let's focus on this last vector here, 0, 0, 0, 1. Well, here we have 0, 0, 0, 2 here. It's our last vector. So we can multiply this vector by 1/2, and that'll get us what we want. So let's go ahead and do that. So we're allowed to multiply any vector by any non-zero number. So we keep the first one. So 6, -2, 0, 0. Okay, we keep the second one. So -2, -2, 0, 0. And then we keep the third one, 1, 1, 0, -1. And we're multiplying this last vector by 1/2, right? Why? Because we want it to be that. So when we do that, we get exactly that, right? We get 0, 0, 0, 1. So we're in very, very good shape. Okay, so all we've done so far is we've multiplied the last vector by 1/2, and we have this vector here. Okay, so that vector is going to stay. We want that one, so success. So what about these other three? Well, you see this -1 down here. This is a problem, right? It should go away. So I'm thinking we can add the last vector to the third, right? Add the last vector to the third. So let's go ahead and do that and see if that helps. So this is equal to the span of, let's see, we have bracket 6, -2, 0, 0. Then we have -2, -2, 0, 0. Gotta be really careful here I don't mess up. So we're adding this last one to this one. So when we do that, they'll cancel. So we just get 1, 1, 0, 0. Right, you're allowed to add vectors together, and you can multiply them by numbers. And then we have the last vector here, 0, 0, 0, 1. Okay. So now we're in a much better place. It's starting to look better. We're starting to get some ones here, right? I think what I'm going to do next is reorder these. I'm going to put this vector first. I'm just going to flip it with, well, actually, I think at this point, we can actually eliminate a vector, right? I can multiply this vector here by 2 and add it to the second vector. So we're going to multiply third vector, let me write that down, by 2, add to second vector. Let's go ahead and do that because that's clear. You can eliminate a vector completely. So this is the span. Let's keep that first vector. So 6, -2, 0, 0. And again, we're multiplying the third vector by 2 and adding it to the second vector. So it's going to become 0, 0, 0, 0, right? Because this is 2 plus -2, and that's 0. Beautiful stuff. And then we keep the other 2. This method is extremely powerful. Like, the other way to do this problem, I have a video on it, is using what's called double inclusion. Like you take an element in one span, you show what's in the other span, and then vice versa. You take an element in the other span, and you show what's in the other span. So you show the spans are subsets of each other. But that is a lot of work, my friends. This is the way pros do it. So now you have the 0 vector. You can always drop the 0 vector, right? Always. It's always what's called a redundant vector. It's always a linear combination of the others. So you can just drop the 0 vector. So we have 6, -2, 0, 0. Then here we have 1, 1, 0, 0. And then here we have 0, 0, 0, 1. Okay, 0, 0, 0, 1. All right, good stuff. We're almost there. Maybe what we can do now is get rid of this ugly 6 and -2. Maybe we can multiply the second one by -6 and add it to the first. So let's do that. So mult second by -6, add to first. So let's do that. Let me change colors here. The yellow is getting out of control. This is equal to the span. All right, so multiplying this by -6, so -6 plus 6 is 0. -6 plus -2 is -8, and the rest of them are zeros. Okay, and then here we have 1, 1, 0, 0. And then here we have 0, 0, 0, 1. So we've rewritten our span. Okay, we've rewritten our span. Now maybe we can make this one a 1. Right, we can do that by multiplying it by negative 1/8. So this is equal to the span. This is going to be 0, 1, 0, 0. Okay, 1, 1, 0, 0. Again, we can multiply any vector by any non-zero number, and we can add vectors to each other, and we can remove 0. And let's go ahead and maybe now multiply this one by negative 1 and add it to this one. So that'll become the span. So adding negative 1 times the first to the second. So the first is the same. And then negative 1 times this vector plus this vector, it's just going to cancel the second component, right? So it'll be 1, 0, 0, 0. And then we have 0, 0, 0, 1. Okay, and then let's go ahead and rearrange it so we have what we want. So this is equal to the span. Kind of rushing through this. Let me give myself some more room. I think this is the last step, so let me make it look cooler. Span. It's a big span. We have the set. Let's rewrite the ordering here. Reorder this. So we're here, and then we are here, 0, 1, 0, 0. And then the last one would be 0, 0, 0, 1. And that's it, my friends. That's how you simplify spans using theorems, right? So basically, you're allowed to multiply any vector by any non-zero number, and you're allowed to add vectors to each other, and you can drop 0. So I hope this video has made sense. That's it. Let x be a non-empty set. Define little d as follows. We'll say that the distance between x and y is equal to 1 if x is not equal to y, and that it's equal to 0 if x is equal to y. In this problem, we have to prove that d is a metric on x. So over here on the right, I've written down the definition of a metric on x. So as we go through the proof, we'll carefully go through each of these conditions and verify that little d is actually a metric. Oh, and little d is called the discrete metric. So this is the discrete metric. All right, the first condition. We have to show that it's non-negative for all x, y, and that equality holds. In other words, the distance is equal to 0 if and only if x is equal to y. It's pretty obvious from the definition, but let's write some stuff down. So note, for all xy in capital X, the distance between x and y, well, it's either 0 or 1 according to the definition, so is 0 or 1. So in particular, in any case, it's greater than or equal to 0. Right? If it's 0, it's equal to 0, so this holds. And if it's 1, it's greater than 0, so this holds as well. And equality holds. Well, let's see. If this is equal to 0, what does that mean? Well, that means that x is equal to y. And if x is equal to y, then it means that the distance is 0 by definition. So this is an if and only if statement. So the first condition is trivially satisfied. The second condition is to show that the distance between x and y is equal to the distance between y and x. So note, and again, this is pretty clear by definition, but let's write some stuff down just to make it a little bit more clear. Let's look at the distance between x and y. Well, by definition, this is 1 if x is not equal to y, and 0 if x is equal to y. And what we can do is we can reverse the roles of y and x. So this is 1 if y is not equal to x. That's the same thing as saying x is not equal to y. And 0 if, well, x is equal to y, or y is equal to x. Same thing. And by definition, this is the distance between y and x. So that takes care of the third condition. The last condition is probably the most challenging. It's called the triangle inequality. Oops, and I forgot to say something here. This has to be true for all x, y, z in capital X. So this last condition, let's take cases. So take any x, y, z in capital X, And let's first look at the case where x is equal to y. So if x is equal to y, then the distance between x and y, well, that's going to be 0. And that's certainly less than or equal to all this stuff over here. You might say, well, why? Well, the reason is that these guys are either 0 or 1. So this right-hand side is either 0, 1, or 2. And in any case, 0 is less than or equal to any of these numbers. So that condition holds. If x is not equal to y, well, that's going to mean that z is not equal to x, or z is not equal to y. And if that's not clear, well, suppose not. So otherwise, that means z is equal to x, and z is equal to y. So x is equal to y, a contradiction. So if x is not equal to y, then z is not equal to x, or z is not equal to y. And when that happens, we can look at this piece here. Then the distance between x and z plus the distance between z and y. Well, we're saying z is not equal to x or z is not equal to y. That means one of these conditions is true or both of them are true. Worst case scenario, only one of them is true, in which case this is equal to 1. So this is at least 1, right? This is going to be either 1 or 2. And so it's definitely at least 1. So then we have this, and the distance between x and y. Well, we said x is not equal to y, so this is equal to 1, which is less than or equal to what's over here. And so that takes care of the triangle inequality. So why did we choose to take cases in this way? Well, because this is over here. So the natural thing to do is say, okay, what happens if x is equal to y? And then what happens if x is not equal to y? So that takes care of all three conditions, and therefore little d is a metric on capital X. So we have to prove this statement for harmonic numbers. So here h sub m is called the mth harmonic number. So it's equal to this sum here. So for example, h sub 1 would be equal to 1, h sub 2 would be equal to 1 plus 1/2, etc. So to prove this, we'll use mathematical induction, so proof. Before we start the proof, let's identify what our statement is. This entire thing here, this will be s sub n. And we have to show that this is true for every positive integer n. So the first step is the base case. And since we're proving this is true for every positive integer, we'll start with the smallest one, which is 1. So we're going to replace all of the n's with 1's and see if our statement is true. So the left-hand side, when n is equal to 1, is the sum as j runs from 1 to 1 of h sub j. This means we plug in 1, so we get h sub 1, and h sub 1 is equal to 1. The right-hand side, well, we just replace all of the n's with 1's on the right-hand side. So this is 1 plus 1 times h sub 1 minus 1. So 1 plus 1 is 2. The first harmonic number we know is 1. Then minus 1. So 2 minus 1 is 1. So the left-hand side is the same as the right-hand side. So our statement is true when n is equal to 1. So s sub 1 is in fact true. The next step is the induction hypothesis. Induction hypothesis. This is the step where we suppose that our statement is true for some positive integer k. So suppose our statement is true when n is equal to k. So we're just going to replace all of the n's in our original formula with k. So we have the sum as j runs from 1 to k, h sub j equals k plus 1 h sub k minus k. And we're assuming that this is true for some positive integer k. In the induction step, we have to prove that this is true when n is equal to k plus 1. So we replace all of the n's with k plus 1's, and we have to show that that statement is actually true. So let's go ahead and do the induction step now. Induction step. In order to do the induction step, it helps to write down what you're trying to prove so that we can kind of figure it out. So claim that the statement is true when n is equal to k plus 1. So we claim that if we replace all of the n's with k plus 1's, that our statement is in fact true. So replacing all of these k's, since we can't see the n's, I'll just replace the k's. K plus 1, h sub k plus 1 minus k plus 1. This is what we have to prove. Now, 1 plus 1 is 2, so let's go ahead and rewrite this as k plus 2 h sub k plus 1 minus k plus 1. So this is what we have to show. We just replaced all of these k's with k plus 1. So we got k plus 1, k plus 1, k plus 1, k plus 1. And then 1 plus 1 was 2, so we combine them. All right, here's where it gets tricky. So we'll start by writing down the left-hand side, and we'll show it's equal to the right-hand side. So note, well, we have the sum as j runs from 1 to k plus 1 of h sub j. Now we somehow have to use our induction hypothesis up here. So let's write this as a sum from 1 to k. So this is the sum from 1 to k of h sub j, but then we're missing the last term, so plus h sub k plus 1. Right, these are exactly the same thing. Here we just added them all up from 1 to k plus 1 in a single step. Here we add them up from 1 to k and then add the last term, the k plus 1th term. Now we can use the induction hypothesis because we know that this is equal to this via the induction hypothesis. So this is equal to k plus 1 h sub k minus k plus, we still have this piece here, the k plus 1th harmonic number. Now we have to think about where we're going. We're trying to get to this over here. And you notice that here we have an h sub k, but we don't have an h sub k over here. So let's go to the side and see if we can figure out maybe how we can write h sub k in terms of h sub k plus 1. So note, h sub k is 1 plus 1/2 plus dot 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 plus 1 over k. And h sub k plus 1 is 1 plus 1/2 plus dot 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 plus 1 over k plus 1 over k plus 1. So we can write h sub k plus 1 as, well, all of this is h sub k plus 1 over k plus 1. So h sub k is equal to h sub k plus 1 minus 1 over k plus 1. Let's go over that again. So I wrote down h sub k, I wrote down h sub k plus 1, and the goal is to somehow combine them and write them together so that we can eliminate this h sub k. Well, you'll notice that h sub k plus 1 is really all of these guys plus 1 over k plus 1. But all of these guys, this is just h sub k. Then you subtract 1 over k plus 1 from both sides, and you get this equation here. So let's go ahead and rewrite what we have using that equation. So continuing, this is equal to k plus 1. And we know something about h sub k. It's h sub k plus 1 minus 1 over k plus 1. So it's h sub k plus 1 minus 1 over k plus 1. and this is minus k, and this is plus h sub k plus 1. Here we have k plus 1 distributing h sub k plus 1. And then k plus 1 times this, that's just minus 1. Then we have minus k, and then here we still have this plus h sub k plus 1. This is equal to, well, we have k plus 1 h sub k plus 1 plus 1 h sub k plus 1. That gives us k plus 2 h sub k plus 1s. And this is minus k plus 1, factoring out the minus sign. And that's exactly what we want. Now, if this step of getting this was too much, you can go to the side and grind it out. K plus 1, h sub k plus 1, and we combine that with this one here, so plus h sub k plus 1. This is k, and then the h, and then the h. It's being multiplied by 1, and then the other h. It's a lot of h sub k plus 1s. This is k h sub k plus 1. And you have two of these, so plus 2 h sub k plus 1. And then you can factor out the h sub k plus 1. I said, did I do all this in my head? Absolutely not. I thought of it this way. You have k plus 1 of these, and then you have one of them. So k plus 1 is k plus 2. This is exactly what we had to show, so s sub k plus 1 is true. So therefore, by PMI, the principle of mathematical induction, s sub n is true for every positive integer n. I hope this helps someone out there. In this video, we're going to prove that these two spans are equal, so proof. So what is a span? Well, the span here on the left-hand side is the set of all linear combinations of these vectors. And the span here is the set of all linear combinations of these vectors. So we have to prove here that these sets are actually equal. So we're going to use the method of double inclusion. We'll show that they're both subsets of each other. So we'll avoid using any theorems or anything. We'll just give a direct proof. So first, let's show this direction. So we'll take any x in the span on the left-hand side. So the span of the vectors 1, negative 2, 3, and 0, 1, negative 1. Then we're going to write down what it means for a vector to be in the span, and then we have to show it's here. So this means there exist some scalars, in this case real numbers, alpha and beta, in R, such that our vector x is a linear combination of these vectors. So the vector x can be written as alpha times the first vector, so 1, negative 2, 3, plus beta times 0, 1, negative 1. And we somehow have to show that x is a linear combination of the vectors in this span. So we already have the first one and the second one. Well, we can simply do this. We can add 0 times this vector. And we haven't changed anything, and now we have x written as a linear combination of these vectors here. And so that's exactly what it means for x to be in the span of the vectors 1, negative 2, 3, 0, 1, negative 1, and 1, 0, 1. So again, we started with the vector x in this set. We wrote down what it meant for it to be in this set. It means this. Then we realized that we wanted to write it as a linear combination of the vectors over here. And we did that simply by adding 0 times the missing vector. And then we have x written as a linear combination of the vectors in this set here. And so x belongs to the span. So we took any x in this set and we showed it belonged to this one. So the first inclusion is shown. So I'll go ahead and write it one more time. So the span of this A lot of writing, but it's not too hard. It's actually pretty easy. Is contained in this span here. So 0, 1, negative 1, and 1, 0, 1. So I think that was the easy direction. So I said it's kind of easy, but I think the other direction is going to be a little bit harder. So let's try it. So now we'll show the other inclusion. So we'll take any vector x in the set on the right-hand side. So in the span of, should have abbreviated this stuff, 1, negative 2, 3, 0, 1. Oh yeah, this is going to be a little bit trickier. 1, 0, 1. Okay. And so what does this mean? So this means we can write x as a linear combination of those vectors. This means there exists alpha, beta, and gamma in R. No idea why I'm using Greek letters. Such that x is a linear combination of these guys. So x is equal to alpha times 1, negative 2, 3 plus beta times 0, 1, negative 1 plus gamma times 1, 0, 1. Ah, indeed, this is the hard direction. So we have to show that x is a linear combination of only these two vectors here. Let me circle them, right? We have to show x is in this set. So x has to be a linear combination of just these guys. Well, we've already got this taken care of, because here, this is one of the vectors in this span. And this one's also in the span, so there's no issues there. We just have to deal with 1, 0, 1. So this is where we actually have to think a little bit harder. So we go to the side. This is not part of the proof. And we have to figure out a way to write 1, 0, 1 as a linear combination of 1, negative 2, 3. So I'll go ahead and write it here. 1, negative 2, 3. And 0, 1, negative 1. Okay. So it looks like, let's see, 1 plus 0. So this has to be multiplied by 1, I think, because we need to have this component being 1. So we can't change that. And so how can we make the second component 0? We have a negative 2 here. So if I multiply this by 2, let's see. 2 plus negative 2 is 0. 3 minus 2 is 1. Yep, this works. You can check and verify. So again, how did I do that? I knew this had to be a 1 because 1 plus 0 is 1. And then I had to put a 2 here because we wanted to make this 0. So negative 2 plus 2 is 0. So it's a little bit tricky and it requires some thought. So now we're going to go back to the proof. I'll stick with yellow. This is equal to alpha 1, negative 2, 3 plus beta 0, 1, negative 1 plus gamma, and now we're going to rewrite our vector like we did over here. This is 1 times 1, negative 2, 3 plus 2 times 0, 1, negative 1. Right? Just replacing this vector here with this stuff here. And now let's condense this. So this is the vector x. It's equal to, let's see, we have 1, negative 2, 3 here, and we have it here. So this is going to be, let's factor out the vector. So it'll be alpha plus gamma times 1, negative 2, 3. So what I did was I factored out this vector from these two terms here. And then here we have the other vector, here and here. So it'll be beta plus, and then there's a gamma here. Let me use a different color. There's a gamma here, and there's a 2 here. So 2 gamma times our vector, which is 0, 1, negative 1. That's a gamma, and that's a 2. All right, so just very, very careful rearranging. Again, let me go over that one more time. So here we have this vector here and this vector here. And so that was alpha plus gamma. That's that piece there. And over here, we have this vector here and this vector here. So that's 2 gamma plus beta. And that's what we have down here. And this is certainly in the span of 1, negative 2, 3, 0, 1, negative 1. So we took any vector x in this set and we showed it was contained in this one. So this means that the span of 1, negative 2, 3, 0, 1, negative 1, and 1, 0, 1 is contained in the other span here. So kind of rushed and kind of messy there, but hopefully it made some sense. So we showed both inclusions, and so by the method of double inclusion, the spans are equal. So the proof is done. So again, I hope that made sense. It got a little bit messy here with the colors, but the idea is pretty simple. The first direction was trivial. This direction here, though, required a bit more work. And again, it's when you get here, right? This is taken care of because that's certainly in the span. This is taken care of. The only thing you really have to deal with is this. You just got to write this as a linear combination of these two guys here. I hope that made sense. Find x and two topologies on x whose union is not a topology on x. Let's go ahead and work this out. Solution. So the way I did it was I just picked x to be ABC. So ABC. And then we have to define two topologies on this set where the union will not be a topology. So one easy case maybe is to take tau sub 1. Now we have to include x in the empty set no matter what, because that's one of the conditions for tau sub 1 to be a topology on x. And then maybe just include this open set here. And that should be good. This is certainly a topology on x. It contains the whole space and the empty set. The intersection of any of these guys is also here, and so is the union, so there's no problems. Then we can take tau sub 2, and we can do the same thing. We can take capital X, the empty set, except this time let's take a different element. Let's take B. This is also a topology on X. The intersection and union is also in tau 2, and it contains the whole space and the empty set, so no problems there. The interesting thing happens when we take the union. Well, the union is going to be X, the empty set, the set containing A, and now we also get the set containing B. And this is not a topology on capital X. And it's pretty easy to see why. So note the singleton set containing A, the singleton set containing B. These are both open sets in tau 1 union tau 2. But the union is not there. If you take the union of these two singletons, you get the set containing A and B, and this is not in the union. So we found two open sets in tau 1 union tau 2, whose union is not in tau 1 union tau 2. So this guy is not a topology on capital X. So not a topology. Right? The union of any number of open sets must also be an open set. In other words, the union of any number of these guys also has to be in this set. So we found two sets whose union is not in here. So I hope that made sense. Let tau sub 1 and tau sub 2 be topologies on capital X. We have to prove that the intersection, tau sub 1 intersected with tau sub 2, is also a topology on X. So proof. To do this, we'll just go through the definition of a topology. So the first thing we have to show is that X and the empty set are both in this set. So since the empty set is in tau 1, and this is true because tau 1 is a topology on X, and the empty set is in tau 2, and this is likewise true because tau 2 is a topology on X, we have that the empty set is in the intersection. So that condition checks. Likewise, we can do the same thing with capital X. We know that capital X, well, this is in tau 1 because tau 1 is a topology on X. And capital X is in tau sub 2 because tau sub 2 is a topology on capital X. So as before, capital X is in the intersection. So the first condition was pretty easy to show. For the second condition, we have to show that the union of any number of open sets in the intersection is also in the intersection. So take any collection of sets or open sets in tau 1 intersected tau 2. So we're taking any collection of sets in this intersection, and we have to show that the union is in the intersection. Well then, for each alpha in our index set I, we have O sub alpha. Well, if it's in the intersection, O sub alpha is in tau 1, and O sub alpha is in tau 2. So these are actually open sets in tau sub 1 and in tau sub 2. So then, the union of these open sets, well, the union lies in tau sub 1 because these are open sets in the first topology, tau sub 1, and so the union of any number of open sets should also live inside tau sub 1. And the union of these open sets, well, as before, these are open sets in tau sub 2, and so the union of these open sets should also be inside tau sub 2 because, again, it's a topology on X. So that this means that the union is actually in the intersection. So the union of the O sub alphas is actually in the intersection. So that takes care of the second condition. And the third condition is pretty much exactly the same. The proof is almost identical. The third condition, we have to show that any finite number of open sets in the intersection is also in the intersection. So take any O1 dot 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 O sub n in the intersection, open sets, then all of these guys are in tau sub 1, and all of these guys are also in tau sub 2. Okay, so we have a finite number of open sets in tau sub 1. That means that their intersection is also in tau sub 1 because tau sub 1 is a topology on X. And here we have a finite number of open sets in tau sub 2, so their intersection also lies in tau sub 2 because tau sub 2 is a topology. So the intersection is in tau sub 1, the intersection is in tau sub 2, so the intersection, crazy notation or fun notation, so the intersection is in tau sub 1 intersected tau sub 2. It's always fun to have like these big intersection symbols. All right, so that was pretty easy, and that completes the proof. So we showed that X and the empty set are in the intersection. We showed that the union of any number of open sets is also in the intersection. And we showed that any finite intersection of open sets is in our intersection. So tau sub 1 intersected with tau sub 2 is a topology on capital X. So we have a set which we're calling V. V is the set of all of the vectors in R cubed such that the third component is equal to the sum of the first two components. And we want to prove that this is a subspace of this vector space here. And all of this, our field, will be the set of real numbers. So what do we need to show? We need to show three things. One, we have to show that V is non-empty. That's pretty easy to do. Two, we have to show that if we have two vectors, say X and Y, in V, then the sum of those vectors is also inside V. And lastly, we have to show that if we have, say, a scalar alpha in our field, which is the set of real numbers, and another vector in V, that the scalar product, so alpha x, is also in V. So we have to show it's closed under vector addition, and this here is saying it's closed under scalar multiplication. Let's go ahead and prove this. It's a pretty easy proof. So proof. So we'll start by showing condition 1. We have to show it's not empty. We'll note that 0 is equal to 0 plus 0. Right? So 0 is equal to 0 plus 0. So this means that the vector 0, 0, 0 is in V. So it does contain the 0 vector, so it is in fact non-empty. So condition 1 is done. Pretty easy. 2. we have to take two vectors in V and show that their sum is also in V. So suppose that we have two vectors which live inside V. Then that means we can write these vectors as follows. That means that the first vector x is x1, x2, x3. And the other vector, let's call it y1, y2, y3. For sum, and then we know that all of these little components, x1, x2, x3, these are all real numbers, y1, y2, y3. These guys are all in the set of real numbers. And moreover, we know something else. This is a special set, right? If you're in this set, your third component is the sum of the first two. So, and we know that x sub 3 is equal to x sub 1 plus x sub 2, and y sub 3 is equal to y sub 1 plus y sub 2. So we know that's what it means for a vector to be in V. It means the third component is the sum of the first two. Now we have to show that the sum is in this set. So note, let's look at what the sum looks like. If you take x, the vector x, and add it to the vector y, well, the addition is the normal component-wise addition. So you just add the corresponding components. So x sub 1 plus y sub 1, x sub 2 plus y sub 2, and x sub 3 plus y sub 3. So that's what the sum of the vectors looks like. And we have to show that this is in V. So we have to show that the third component, and the third component, x3 plus y3, we have to show it's the sum of the first two. Well, x3 is right here. It's x1 plus x2. And y3 is right here. It's y1 plus y2. And I'm being a little abusive here. You should have parentheses, but these are real numbers, so addition is associative, and moreover, it's commutative. So we can write this as x sub 1 plus y sub 1 plus x sub 2 plus y sub 2. So we've shown that the third entry, the third component of our vector, is the sum of the first two, right? The first two. That's precisely what it means for the vector x plus y to be in V. So x plus y is in V. So this shows that V is closed under vector addition. The third step is to show it's closed under scalar multiplication. Again, pretty easy. So take any vector in V and some scalar alpha in the field of real numbers. Then we know that x is equal to the vector whose components are x1, x2, x3 for sum x1, x2, x3 in the field of real numbers. And we know that the third component is the sum of the first two. So x3 is equal to x1 plus x2. So then we have to look at the vector alpha times the vector x, right? The vector alpha x, so this is equal to x sub 1, alpha x sub 1, alpha x sub 2, alpha x sub 3. And, well, what is the third component? Alpha x sub 3, well, using this equation, that's alpha times x sub 1 plus x sub 2. And these are real numbers, so alpha distributes. So alpha x sub 1 plus alpha x sub 2. So the third component is the sum of the first two. So the vector alpha x is in V. So this shows that V is closed under scalar multiplication. So therefore, V is a subspace. So I hope this helps. Prove that this set W is a subspace of R squared. So proof. Before we start the proof, let me really quickly remind you what it means for W to be a subspace of R squared. So in general, a subset W of a vector space V, so V here is our vector space, is a subspace of V if the following three conditions hold. So the first condition is that W must be a non-empty subset. So it cannot be the empty set. 2, The second condition is that W should be closed under vector addition. In other words, given any two vectors x and y in W, their sum must also reside inside W. So x plus y also needs to be an element of W. And 3, given any alpha in our field F, usually the field is taken to be the real numbers. In this example, we'll use the real numbers. Usually you use the complex of the real numbers. So any alpha, so any real number, and any vector x in our subset, if you have these two things, then the product, alpha times the vector x, should also reside inside the subset W. So this is called closure under scalar multiplication. So it's non-empty, it's closed under vector addition, and it's closed under scalar multiplication. All right, so let's go ahead and do this proof. And as we do it, I'll number the steps. So step 1, we have to show it's non-empty. So we have to explain why there is a vector in W. Well, the easiest choice is 0, because note, 0 is equal to minus 0. So that's this condition here with a equal to 0 and b equal to 0. So this is precisely what it means for the vector 0, 0 to be inside W. So this shows that W is not the empty set. So it's a non-empty subset. So condition 1 is satisfied, and we're done with that part of the proof. 2. Here we have to show it's closed under vector addition. So to show condition 2, we have to start by supposing we have two vectors x, y, and w. So suppose x, y are in W. And then all we do is write down what that means. So this means x. Well, how do I know what to write down here? Well, you just look up here. All of the vectors in W have this form, AB. So x can be written as AB. And likewise, y, it also has that form. So we'll use different letters, CD. With, and what does it mean for x to be in W? Well, it means that a is equal to negative b. And what does it mean for y to be in W? Well, it means that c is equal to negative d. And so now we just simply have to show that the sum, x plus y, is also in W. So then, x plus y, well, x is simply AB, and y is CD. And how do you add vectors? Well, we just use regular component-wise addition. So this is a plus c, and here we have b plus d. And now in the case of x, we had to show that x was equal to negative b. Here we have to show that a plus c is equal to negative the quantity b plus d. So with, and it should work out, a plus c, well, we'll use this condition here, a is equal to negative b, so this is negative b. And now we'll use this condition here, c is equal to negative d, so this is negative d. Then you can factor out negative 1 and write this as b plus d. So a plus c is equal to the opposite of b plus d. That's precisely what it means for this guy to be inside W. So x plus y is in W. So this shows that W is closed under vector addition. The last thing we have to do is explain why it's closed under scalar multiplication. So 3. We'll start by taking some alpha. So suppose alpha is a real number. So in this problem, our field is R, and x is a vector in W. So as before, we usually write down what this means. So this means that we can write x equal to a, b, with a equal to negative b. Now we have to explain why the vector alpha x is also in W. So then, alpha x, well, this is simply alpha times ab. And we can perform the scalar multiplication. So this is alpha a, alpha b. And now we just have to show that alpha a is equal to the opposite of alpha b. So with, let's write it down and see if it works, alpha a, we can replace a with negative b. So that worked out nicely. So alpha negative b. And then we can write it this way as negative alpha b, skipping some steps there. So negative alpha b. So alpha a is equal to the opposite of alpha b. Right, these are numbers, so we can do that. So this is precisely what it means for the vector alpha x to be in W. So alpha x is in W. So since W is non-empty, closed under vector addition, and closed under scalar multiplication. Let's finish the right way. Under scalar multiplication, W is a subspace of V. W is a subspace of V. So kind of rushed that, but I think I already have another video on this. I just wanted to make one more because you need to practice these to get good at them. I hope that made sense. So we have a set W. This is actually a subset of Rn, and we're asked to prove it's a subspace of Rn. So recall that W is a subspace of a vector space V if we have three conditions. The first condition is that W is non-empty. So there has to be something in there. There has to be a vector in W. 2, W is closed under what's called vector addition. So symbolically that means given any two vectors in W, the sum also has to reside inside W. Again, this is called closure under vector addition. And then 3, given any vector in W and given any scalar C in a field. Now, in this case, our field is going to be the real numbers, so I'll go ahead and put the real numbers here. Whenever this happens, we have a new vector. It's called the scalar product. So it's the scalar C times the vector x. And this new vector is in W. So we have non-empty, closed under vector addition, and then closed under scalar products. If all three conditions hold, then W is a subspace of V. So let's carefully go through this and show that this set here, W, is actually a subspace. So proof. So I'll number the steps. So 1, we have to show that W is non-empty. So you have to think of a vector that's in this set. So what does it mean to be in this set? It means that when you add up the components of your vector, you get 0. So the easiest choice is this one. So 0, dot, 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 0. This guy is in W, right? Because if you add up all of the components of this vector, you get 0 plus 0 plus 0, dot, 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 etc. And there's n copies of 0. But 0 plus 0 is simply 0. So no problems there. So this shows that W is non-empty. For the second condition, we have to take two vectors in W and show that the sum is also in W. That's this one here. So take any, and I'll go ahead and just write them like this. So I guess we could use x and y. So take x1 dot 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 x sub n and y1 dot 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 y sub n in W. Then let's go ahead and write down what this means. This means that the sum of the components of the first vector is 0, and the sum of the components of the second vector is also 0. And so now we have to look at the new vector. What happens when we add these? So then x1 dot 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 xn. Let's examine what this is. And how do you add these vectors? Well, you just add the components, right? The addition is just the regular addition that takes place in Rn. So this is going to be x1 plus y1, comma, dot, 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 x sub n plus y sub n. And in order to show this is in W, we have to show that if we add the components of this vector, it's also 0. Well, this will be in W. Since, let's go ahead and verify it here. Let's see, it should work. If not, we're in trouble. So this is xi plus yi. Right, we're adding up all the components. And you can break the sum up as the sum from 1 to n of x sub I plus the sum from 1 to n of y sub I. And the first sum here, this is 0, right? So this is 0, and this sum here, it's also 0. So 0 plus 0 equals 0. So that vector is indeed in W, and so W is closed under vector addition, right? This here, let me use a different color. This was our x, and this was our y. So we took any x and y, and then we looked at x plus y, and we showed it was in W because the sum of the components was 0. That's exactly what it means to be in W, right? A vector is in W if the sum of the components is 0. And the third one is to show that it's closed under scalar multiplication. So I guess I'll use x again. So take any x1. You can do these two steps here at the same time pretty much, but I figured let me just really do them individually so you see that there are two different criteria that we have to check. So take any vector in W and scalar C in R. And as before, we're going to write down what it means for this vector to be in W. Well, it means that the sum of the components is 0. Then we have to look at the new vector, C times the vector. Right, this is a new vector. That's 3 dots, really important. And how do you multiply a number times a vector in Rn? Well, you multiply the number, right, the scalar, by each of the components. So it's Cx sub 1 dot 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 Cx sub n. And we have to show that this is a vector in W. Well, it is. So let's go ahead and say it is, and then verify it later. This is since if we take the sum of the components of this vector, it's Cx sub I runs from 1 to n, and we can factor out the c from the sum. This is c times the sum, as I runs from 1 to n of x sub I. But this piece here, this is 0. So this is c times 0, which is 0. That's exactly what it means for this vector to be in W. So we've shown all three conditions. So W is a subspace of Rn. And again, went pretty fast through this, but trying to keep the video length short. I hope that made sense. So we have a set W. This consists of all the functions that are bounded. So what does it mean for a function to be bounded? It means that there is a number m such that the absolute value of the function is less than or equal to m for all x and r. And we want to prove that this is a subspace of all functions. So recall that W is a subspace of V if we have three conditions. The first condition is that W is non-empty. 2, W is closed under vector addition. So is closed under vector addition. That means given any two vectors in W, the sum of the vectors is also in W. So in this problem, our vectors are actually functions, so it's a little bit different. And 3, W is closed under scalar multiplication. And what this means is that given any vector x in W and any scalar c in a field, here our field will be the real numbers, that we have a new vector, which is the scalar c times the vector. This is the scalar product, and that's also in W. So in order to do this problem, we carefully have to go through and just check all of these conditions. So proof. We first have to show W is non-empty. We have to think of a function that's definitely bounded. Well, the 0 function. So note, let's call it 0 hat. From R to R, given by, so this is the 0 function. It takes every x and sends it to 0. Is in W. So the claim is that the 0 function is in W, and the reason is if you take 0 of x, well, you just get 0. So if you take the absolute value of that, that's less than or equal to, say, I don't know, 2 for all x and r. Why did I pick 2? it doesn't really matter what number you pick as long as it's non-negative, right? To satisfy this definition, you could have picked any number bigger than 0. So here this is 0, so there's no issues there. So this shows that this guy is inside W, so the first condition is actually satisfied. Let me put a little 1 here to indicate that we've just done the first condition. 2, we have to show that W is closed under vector addition. So we have to take any two vectors in W, and we have to show the sum is also in W. So take any f and g in W. And now we have to show f plus g is in W. Well, before we do that, maybe let's go ahead and write down what it means for f and g to be in W. So then, there exists, well, we're going to have two different m's because we have two functions. So I'm going to use m1 and m2 in R such that, well, the absolute value of f of x is less than or equal to m1 for all x in R, and the absolute value of g of x is less than or equal to m2 for all x in R. So now we have to show that f plus g is there. So we have to look at the absolute value of f plus g. So then, the absolute value of f plus g of x, right? This is a new function. It's called f plus g. Well, this is equal to, by definition of function addition, f of x plus g of x. Then we have to use something from other math areas. It's called the triangle inequality. This is less than or equal to the absolute value of f of x plus the absolute value of g of x. And we know something about the absolute value of f of x. It's less than or equal to m1. So this is less than or equal to m1 plus m2. And so all we do is we call this m, and we have it. And this is true for all x in R. So we have f plus g of x less than or equal to some constant. So f plus g is in W. So that shows closure under vector addition. Now we just have to show closure under scalar multiplication. So let's go ahead and do that, and then we're done. So 3, take any. Let's use f again. In W, I could have used the same one, but I didn't. And scalar c in the field of real numbers. Then as before, we go through the same game. We write down what it means for f to be in W. It means there is a constant m in R such that the absolute value of f of x is less than or equal to m for all x in R. Then, and now we have to look at the scalar product, Cf of x. And we have to show that this is bounded. So this is equal to the absolute value of C times f of x. Well, the absolute value of a product is the product of the absolute values. This is C times the absolute value of f of x. And this is less than or equal to the absolute value of C times m. And this is for all x in R. So here we have our new m. This is our new constant, say m tilde. So we have Cf of x less than or equal to some constant for all x in R. So the vector Cf is in W. So I kind of rushed through that really quickly, but hopefully it makes sense. And then, so therefore it's a subspace. Let me go ahead and write that down. So therefore W is a subspace. But hopefully it made some sense. I wanted to keep the video short. Basically, you just check all three conditions very carefully. And we did have to use the triangle inequality right here. Right? This was the triangle inequality. The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. But other than that, wasn't too bad. That's it. So we have a subset of R cubed, and we have to determine if it's a subspace. So recall that a subset W of a vector space V is a subspace of V if the following three conditions hold. So the first condition is that W is non-empty. The second condition is that W is closed under vector addition. So if you take two vectors, x and y in W, then whenever this happens, the sum x plus y must also be in W. So this is called closure under vector addition. And three, given any scalar in a field, usually this is the set of real numbers, so given any real number, and any vector x in W, if we look at the new vector, alpha x, this is also in W. This is called scalar multiplication. This is called vector addition. So non-empty, closed under vector addition, and closed under scalar multiplication. So solution, let's work this out, see what's going on. So we have this subset, and we have to determine if it's a subspace. So maybe let's start by just checking the conditions. Let's start with the first one and see what happens. So is 0 here? Well, I'm looking at this and I'm thinking no. So let's suppose it was a subspace. So suppose W is a subspace. Let's actually prove it's not. Then what does that mean? Well, if it's a subspace, it's non-empty. So then by 1, there exists some x in W. Right? It's non-empty. By 3, oh, this is kind of cool. By 3, well, note 0 is a real number. X is in W. So condition 3 tells us that the new vector, 0x, which is equal to 0. Now over here, I'm using 0 as a real number. Here, I'm going to put a little arrow. This is the 0 vector. So because of condition 3, this is in W. In particular, that means that 0, 0, 0 is in W. And what does that mean? Well, that means we can write 0, 0, 0 equal to x1, x2, 0, right? Because that's what vectors in here look like, right? They're all x1, x2, 0. So 0, 0, 0 is a vector just like that with x1 equals x2 plus 1. Okay, let's go over that again. So we're actually proving it's not a subspace. So suppose it is, and we're going to reach a contradiction. So by 1, it's non-empty, so we can find some x. By 3, since 0 is a real number and x is in W, the 0 vector is actually in W. So what does that mean? Well, it means that, let me write it one more time, it means that 0, 0, 0, so let's write it bigger, is equal to x1, x2, 0, and we have this condition here. So that means that x1 is equal to 0 and x2 is equal to 0. But at the same time, x1 is equal to x2 plus 1. So this is x2 plus 1 equals 0, x2 equals 0. Oh, look at that. So x2 is 0. So 0 plus 1 equals 0. That's a contradiction, right? That means contradiction. So I didn't intend to prove this problem, prove it wasn't a subspace. I just kind of looked at it and thought, okay, let's check to see if it's a subspace. But when you see this right here, you know it's suspect. For it to be a subspace of R cubed, it has to contain 0, 0, 0. So we basically just proved here that every subspace, right, we supposed it was a subspace, actually contains the 0 vector. So it has to pass through 0, 0, 0. So this one is not a subspace. Because if it was, it would contain the 0 vector, and it does not. That's a contradiction. We have a set W, and we're being asked if it is a subspace of R cubed. So over here, I've written down what it means for a set W to be a subspace of a vector space V. So there's three conditions. The first one says that our set W is non-empty. The second one says that for all vectors x and y in W, the sum is also in W. This is called closure under vector addition. And the third condition says that for any vector x in W and any scalar in our field, here our field is the real numbers, the vector cx is in W. This is called closure under scalar multiplication. So if all three conditions are satisfied, then we say that W is a subspace of V. Now, I haven't done this problem yet, but I really think this is not going to be a subspace because of this here. This is very, very suspect. So what we'll do is we'll carefully go through the three conditions and try to violate one of them. So let's start with condition 1. So is W non-empty? Well, I think there's a vector there, so I don't think condition 1 is going to help us because 0, 0, 0 is in W, and this is because 0 is equal to 0 squared. So here, this is our A, and this is our B, and this is our C. So what does it mean to be in W? It means that A is equal to B squared. But that means 0 is equal to 0 squared. So that's true. So this guy here is certainly in W. So we can't use the first condition to show it's not a subspace. I think that the second condition should work. So to violate the second condition, all we have to do is carefully come up with two vectors that are actually in W whose sum is not in W. So I'm going to have to think here because I haven't done this. So let's come up with two vectors that are in W. So what does it mean to be in W? It means that A is equal to B squared. So if I write a number here down, rather if I write a B here, I have to square it to get A. So let's say I put a 2 here for the second component. So that's our B. So A has to be the square of that. So 4, and then I'll put a 1 here. So this guy is in W because, again, this is A, B, C. So 4, that's our A, is equal to B squared. So that's our B is 2. So 4 is equal to 2 squared. So that guy is there. Let's do it again. So let me put a 3 here this time. And again, I'll put a 1 here. And how do I get this guy? Well, this is B, C. So A goes here, and it's equal to B squared. So 9. And that's in W. And this is because A, well, what's A? A is 9. And that's equal to 3 squared. And B is 3. So both of these guys are in W. And now the question is the sum in W? Well, I certainly hope not. I don't think it will be. So then 4, 2, 1 plus, let's see, 9, 3, 1. Well, how do we add these vectors? Just in the usual way. We add the corresponding components. So 4 plus 9, that's going to be 13. 2 plus 3, that's going to be 5. And then 1 plus 1 is 2, right? And the question is this in W? Well, if this is in W, then we have to have A equal to B squared, right? So let's see, this is A, this is B, and this is C. So is it true that 13 is equal to 5 squared? No, it's not. So this is not in W because A, which is 13, is not equal to B squared. So it's not equal to 5 squared. So we have two vectors in W whose sum is not in W. So this is not closed under vector addition. So there is no way this can be a subspace. So it's not a subspace. So I hope that made sense. I thought this was a pretty good example. We had to think here a little bit to get it to work. I hope that made sense. So we have a set W. This set consists of all polynomials with integral coefficients. That basically means all of the polynomials whose coefficients are integers. And we're being asked if this is a subspace of the vector space of all polynomials with real coefficients. So solution. Over here, I've gone ahead and written down the criteria for W to be a subspace of V. So in this problem, this is our V, and this should not be a subspace. So what we have to do is we have to violate one of these conditions, either W being non-empty, W being what's so-called closed under vector addition, and W being closed under scalar multiplication. So the condition that we're going to violate is condition 3. So to violate this condition, the closure under scalar multiplication, we have to find a polynomial, and we have to find a real number such that the product will not be in W. So we'll simply take, say, f of t equals 2t squared plus 3t minus 1. That's certainly in W because all of the coefficients are integers. And then let's take the number 1/2. That's a real number. And if W were to be a subspace, then the scalar product 1/2 times f of t should also be inside W. But if we look at 1/2 times f of t, this is 1/2 times 2t squared plus 3t minus 1. And we can distribute the 1/2, so 1/2 times 2 is 1, so we get t squared. 1/2 times 3 is 3/2. And then 1/2 times -1 is -1/2. And this is not in W, and the reason being is that this here and this guy here are not integers. So we violated condition 3, and so this is not a subspace of V, which was in this case P of T. So the answer is no, it is not a subspace. So when you're determining if something is a subspace, you just kind of think about it a little bit and go through these three conditions. I knew immediately to use this one because when I saw that all of the coefficients had to be integers, I thought, well, what if you take a fraction or something and you multiply it by your polynomial? That could ruin this, and then so you'll end up with something that is not in W. In this video, we have a set W. This is the set of all functions such that f of -x is equal to -f of x. So this is the set of all odd functions. And we're asked to prove that this is actually a subspace of all functions from the real numbers into the real numbers. So this guy here is a vector space over the real numbers. Over here on the right, I went ahead and wrote down what it means for W to be a subspace of V. So we have three conditions, and all we have to do to prove this is carefully satisfy these three conditions. The first condition is that W is non-empty. The second is that given any two vectors, the sum is also in W. This is called closure under vector addition. And the third condition is called closure under scalar multiplication. And it basically says that given a vector x and W and a scalar c, in this case our field is the real numbers, that the scalar product c times the vector x is also in W. So before we start the proof, also let me show you how you add vectors in this vector space. So given f and g in this vector space V, the sum is f plus g. That's the sum of the vectors, and it's f plus g of x, and that's defined as f of x plus g of x for all x in R. And likewise, if you take a scalar times f, this is defined to be c times f of x, and again for all x in R. So let's go ahead and carefully go through the proof. So first we have to show that W is non-empty. So we have to show it's non-empty. So there is a function that is odd that is in W. That's the 0 function. So note, or the 0 vector, I'm going to call it that, put a little hat on it. This guy, given by, let's see, 0 of x, we're going to say that's equal to 0 for all x in R, right? The claim is that this is odd, since, and let's check, if we take 0 of minus x, well, what does the 0 function do? It just sends it to 0. And if we take the 0 of x, well, what does it do to x? It just sends it to 0. So this 0 vector, it's actually a vector, but it's a function, is this. So this is true for all x in R. And so this guy is certainly an odd function, so it is inside W. So the 0 vector is a function, it's the 0 function. So that takes care of condition 1. We've shown it's non-empty. Now we have to show that the sum of any two vectors in W is also a vector in W. So take any fg in W. Then what does that mean? That means that f of negative x, is equal to negative f of x, and g of negative x is equal to negative g of x. And both of these conditions hold for all x in R. And now we have to look at the sum. So then f plus g, we have to show that f plus g is in W. Well, what does it mean for f plus g to be in W? It means it's an odd function. So we have to check that it's odd. So f plus g of minus x, well, by definition of the addition, this is f of negative x plus g of negative x. And now we can use the fact that both f and g are odd. So f of negative x is negative f of x. So this is negative f of x. And then here, this is going to be negative g of x. I'm going to skip a step and write it like this. Then you can factor out a negative sign. So this is negative, I'll use a bracket, f of x plus g of x. Right? But this is equal to negative f plus g of x, by definition of the addition of functions. So we have f plus g of negative x equal to negative f plus g of x. That means that f plus g is an odd function, so f plus g, oh, and this is true for all x and r. So this means f plus g is an odd function, so f plus g is in fact in W. So this shows that W is closed under vector addition. So to recap, to do this step, you start by taking any two vectors. In this case, the vectors are actually functions. And then you just write down what that means. What does it mean for f to be in W? It means this is true for all x and r. I can squeeze it in here. And what does it mean for g to be in W? It means this is true for all x and r. Then you have to show that f plus g is in W. Well, what does that mean? That means f plus g is an odd function. So you just write down f plus g, and you look at what happens when you plug in negative x. And you got to be really careful here, right? And we showed that f plus g of negative x is equal to negative f plus g of x. So that means that f plus g is in W. 3. We have to show it's closed under scalar multiplication. So take any f in W and c in the real numbers. Okay. Then what does this mean? This means that f of negative x is equal to negative f of x for all x and r. Then we have to show that CF is in W, right? So we have to look at CF of x, of negative x. So what does this mean? Well, this is C times f of negative x by definition of scalar multiplication. And so this is C times negative f of x because f is odd. And then we can factor out the negative, so we get negative C times f of x. And I'll put this in brackets. And so this is negative, and what is this in brackets? This is CF of x. So we have CF of negative x equal to negative CF of x. So that means that the vector CF is in W. So W is closed under scalar multiplication. So all three conditions are satisfied. So W is a subspace of V. Kind of rushed that, but I hope it makes sense. I think the hardest part is just this notation here, right? This notation. Keep in mind, you really have to know this. F plus G of x, that's defined to be f of x plus g of x, and then CF of x, that's the scalar product, that's C times f of x. So you really have to use these carefully in the proof. Suppose A is an invertible matrix. We want to prove the following equation involving determinants. So this should be pretty easy proof. The natural thing to look at is the determinant of the identity matrix, because we can write 1 as the determinant of the identity matrix. And we know that this is equal to the determinant of A times A inverse, right? Because A times A inverse is equal to the identity matrix. And this is equal to the determinant of A times the determinant of A inverse. And dividing both sides by the determinant of A, and we can do that because it's not 0, A is invertible, we end up with 1 over the determinant of A is equal to the determinant of A inverse. Rewriting this another way, we have the determinant of A inverse equals, and if we think of this as being raised to the first power, when we bring it upstairs, it becomes that A to the -1. Pretty easy proof. I hope that made sense. In this video, we have a set W, and we're being asked to determine if it's a subspace of R cubed. So recall that a set W is a subspace of a vector space V if the following three conditions are satisfied. So the first one is that W is not the empty set. So there is a vector inside W. The second condition is that for any two vectors in W, the sum is also in W. This is called closure under vector addition. And the third condition says that for every vector x and every scalar c in our field, here our field is the real numbers, that the vector cx is in W. So this is called closure under scalar multiplication. So we have W is not empty, we have closure under vector addition, and then we have closure under scalar multiplication. So if we wanted to prove that W was a subspace, we would carefully have to go through these conditions and verify. If we wanted to show that W was not a subspace, all we have to do is violate one of these conditions. So I suspect that this will not be a subspace. In the first condition, we have W non-empty. So is that true in this case? Unfortunately, it is. The vector 0, 0, 0 is in W, and this is because, well, this is our B here. B is equal to 0, which is greater than or equal to 0. And that's precisely what it means for this vector to be inside W. So the first condition of actually being a subspace is satisfied, so we can't use this to violate that condition. Also, it seems that the second condition is also going to be true, because if we take ABC and DEF in W, then what does the sum look like? Well, that would be ABC plus DEF, and then you would just add the components. So it would be A plus D, B plus E, C plus F. And the question becomes, is this a vector in W? Well, let's think about it. ABC is in W. What does that mean? That means that B is greater than or equal to 0. Right? That's exactly what it means for ABC to be in W. DEF is also in W. What does that mean? That means that the second component, which in this case is E, is greater than or equal to 0. Well, that means that B plus E is greater than or equal to 0. That means the second component of the sum of the vectors is greater than or equal to 0, and so this vector is actually in W. So W is actually closed under vector addition, so the first two conditions are actually working. Where it's going to fail is in the third condition. W should not be closed under scalar multiplication. So to violate this condition, all we have to do is come up with just one vector, just one where it fails, right? This has to hold for all x and all c and f. So if we find one vector where it fails, we're good. So let's just make one up. Let's try 1, 2, 3. That's certainly in W. And this is because, well, the second component is 2, and that's greater than or equal to 0. And let's take a negative number. Let's take -1. That's a real number. So when we multiply this vector by this number, we should get a vector in W, but we won't. Watch this. Then, -1 times the vector 1, 2, 3. Well, how do you multiply a scalar times a vector in R cubed? You just multiply -1 by each of the components. So this would be -1, -2, -3. And this is not in W because -2 is not greater than or equal to 0. So the third condition is violated. W is not closed under scalar multiplication. So the answer is no, not a subspace. In this video, we have a set W. This is actually the unit sphere. And we're being asked to determine if it's a subspace of R cubed. So recall that W is a subspace of a vector space V if we have three conditions. So the first condition is that W is non-empty. The second condition is that W is closed under vector addition. So what does that mean? That basically means given any two vectors in W, their sum has to also be a vector inside W. So for all vectors x and y in W, we have that the sum, x plus y, is also a vector in W. And the third condition is that W is closed under what's called scalar multiplication. So scalar multiplication. And this basically says that for all vectors x in W and for all scalars c in our field, here our field is just a set of real numbers, that the vector cx is also in W. So if these three conditions are satisfied, then we know that W is a subspace of V. So here in this problem, our V is R cubed, and then this is obviously our W. So solution. So let's go down the list and see if we can violate any of these conditions. Let's start with the first one. So let's see, W non-empty, is that true in this case? No, it's not true, right? Note 0 squared plus 0 squared plus 0 squared, that's equal to 0. So that's less than or equal to 1. And that's this condition here, with x, y, and z all being 0. So this is precisely what it means for the vector 0, 0, 0 to be in W. So W is non-empty, so this condition is satisfied, so that's no good. All right, we're going to show it's not a subspace. What about this one? W is closed under vector addition. So given any two vectors, is it true that the sum is also in W? Well, I think we can pretty easily come up with two vectors. Let's see. Note 1, 0, 0 is in W. And this is because 1 squared plus 0 squared plus 0 squared, this is 1. That's less than or equal to 1. Likewise, let's try 0, 1, 0. And the same thing will happen here. 0 squared plus 1 squared plus 0 squared. That's 1, so it's less than or equal to 1. So if W were a subspace, the sum should also be in W. So let's look at 1, 0, 0 plus 0, 1, 0. If we add these, we get 1, 1, 0. But what's 1 squared plus 1 squared plus 0 squared? Well, that's 2. That's bigger than 1. So the sum is not in W. So we violated the second condition, right? This has to hold for all vectors x and y and W. So all you have to do to violate this is just come up with two vectors where it fails and then just explain why it fails. So the answer is no, and the reason is W is not closed under vector addition. In this video, we have a set W, and we're being asked if it's a subspace of R cubed. So over here on the right, I've written down what it means for a set W to be a subspace of a vector space V. So there's three conditions, and if all three conditions are satisfied, then we say that W is a subspace of V. The first condition is that W is not equal to the empty set. In other words, it's non-empty. It contains a vector. The second condition says that for all, that's what this symbol means, x and y in W, the sum of the vectors, x plus y, is also in W. This is called closure under vector addition. And the third condition says that for every vector x in W and every scalar c in our field F, here our field is the real numbers, the vector cx is also in W. This is called closure under scalar multiplication. So if all three conditions are satisfied, then W is a subspace of V. So in this problem, we have to determine if W is a subspace of R cubed. That's our V. If you think about it, condition 1 is satisfied. the vector 0, 0, 0 is in W because, well, what does it mean to be in W? The first component is less than or equal to the second, which is less than or equal to the third. So in this case, this is A, this is B, this is C, and we certainly have 0 less than or equal to 0, less than or equal to 0. So that means that W is non-empty. So condition 1 checks. So I suspect that this will not be a vector space because of these inequality signs. So that kind of leads us to jump to condition 3. Because if we take a vector and we multiply it by a negative number, that's going to mess this up. So let's try to violate condition 3 by just making up a vector. So note, now we have to come up with just one vector, right? One vector in W and one real number such that the scalar product is not in W. If we can violate this condition just for one vector, we're done, right? So let's try something in W. How about 1, 2, 3? This is in W, and this is because 1 is less than or equal to 2, which is less than or equal to 3. And let's just take negative 1. Negative 1 is a real number. So if this was a subspace, it should be closed under scalar multiplication. So now we're going to look at the scalar product, negative 1 times the vector 1, 2, 3. Well, how do you multiply negative 1 by a vector? You multiply each of the components of the vector by negative 1. So this is negative 1, negative 2, negative 3. And the question is this in W? Well, let's see. But let's see, is it true that negative 1 is less than or equal to negative 2, which is less than or equal to negative 3? Is that condition true? Well, let's think about it. Where's negative 1? Here's negative 1, here's negative 2, and here's negative 3. So this is not true. So this is not in W, because but this is false. Right? So if this was true, then it would be in W. It's not true. So this vector is not in W. So this is not closed under scalar multiplication. So the answer is no, right? It is not a subspace. I hope that made sense. So we have a function and we have to prove it's a surjection. Before we go into the proof, let's go over the notation. So this is called the general linear group of order 2. This is basically all 2 by 2 matrices with complex entries and the determinant non-zero. So it's all of the invertible 2 by 2 matrices with complex entries. And then this set here, the C with the star, this is all of the complex numbers minus the complex number 0. So it's all of the non-zero complex numbers. And so what does a matrix look like in this set? Well, if you have an A in the general linear group of order 2, then A looks like A, B, C, D. And A, B, C, and D are complex numbers. And the determinant of A is given by the formula, well, you just multiply AD minus BC. So this is AD minus BC. Okay, so we have to prove that this function is surjective, right? So given a non-zero complex number, we have to find a matrix whose determinant is equal to that complex number. So recall, let me give you the definition quickly. F from capital X to capital Y is surjective if for all of the y's in capital Y is called the codomain, there is a value of x in the domain such that f of x is equal to y. So we have to use this definition to prove that this function is surjective. Let's go ahead and do it. So proof. I use a different color for the proof. Let's use yellow. Oh, yellow. There we go. So we'll start by taking, keep in mind F, it maps this group into this set. Okay, so we have to take a Y in our codomain, right? That's our y here. Our y is the non-zero complex numbers. We have to show it's true for all y and y. So let's call it z because it's a complex number. It's usually better to call it z. It's what people usually call it. So let's take a non-zero complex number. And then we need to produce a matrix such that the determinant of that matrix is equal to z. So then let's look at the matrix A equals, how about z0, 0, 1? So then this guy is in this set because its determinant is z times 1 minus 0 times 0, right? Using the formula we have up here for determinant. So that's going to be z. And z is not 0 because it's in this set. So that's why A is here. So we showed this part. Then f of A, well, that's the determinant of A, is equal to z. So we started with a z in our codomain. We found an A in our domain such that f of A is equal to z. So we're done. This shows f is surjective. Kind of a super rushed video because I had to go over all the notation, but I hope that helps. In this video, I'm going to show you how to show a set is closed under vector addition. So here we have a set S, and S is going to be all of the vectors of the form x, y, such that 2x is equal to y. And we're going to show that this set is closed under vector addition. So first, let's see what a vector looks like here. So if we have a vector x in S, that means that x is equal to xy, and 2x is equal to y. Right? So let's use this to rewrite stuff. So I'm going to put a biconditional arrow here. So x is in S is the same as saying this, which is the same as saying, well, y is 2x, right? So this is the same as saying that x is equal to the vector x, 2x. And the reason I'm doing this is because I'm using x and y here, and I want to simplify this to make it a little more clear when we do the proof. So we can think of a vector here as being of the form, you can call the x whatever you want. You can call it alpha 2 alpha, okay? So whenever we take a vector x and s, we can say it's of the form, you know, alpha 2 alpha or beta 2 beta, right, for alpha, a real number. All right, so let's prove this set is closed. So to prove it's closed, what we have to do is we have to take any two vectors in this set and show the sum is in the set. So take any x, y, and s. And the claim is that if we add these vectors, they're also in S. So claim that x plus y is in S. That's what it means to be closed under vector addition, right? So we have to show. So now what you do in these problems, always, no matter what, is you write down what this means. So let's clarify that. So since x, y are in S, then, well, we talked about it before we did the problem, right up here, right? We talked about it. We said that if x is in S, then x is of this form here. So then x is of the form alpha 2 alpha, and y is of the form beta 2 beta, okay, for some alpha beta real numbers, right? So that's what it means for x, y to be in S. Now we have to look at the sum and show that that is in S. So then x plus y, let's just write down what that means. Well, you just add the components, right? So it'll be alpha plus beta, 2 alpha plus 2 beta, right? Just adding the components. You could do something with the second component, right? You can pull out a 2, so alpha plus beta. And now it meets the form, right? It's alpha 2 alpha. You can think of this as like gamma or something, right? So it's gamma 2 gamma. You can think of this as gamma 2 gamma. where gamma is equal to alpha plus beta, which is a real number because the sum of real numbers is a real number. This is precisely what it means for these two vectors to be in S. So x plus y is in S. And this shows it's closed under vector addition. What is this set, by the way? This is the set. This is the graph of all the vectors on this line. So if you take two vectors on this line, y equals 2x, and you add them, you get another vector on the line. So the line is closed under vector addition. So kind of a cool example. I hope this video has been helpful to someone out there in the world. That's it. Okay, so we have to prove this statement. So what is the statement in this problem? This right here, this is the statement. This is our S sub n. And we're going to prove this via mathematical induction. So we'll start with the base case. So base case. Now, I haven't done this problem before, but it shouldn't be too hard. Now, the base case starts at 1. We know that because we have to show that it is true for every positive integer, and the smallest one is n. So when n equals 1, let's look at S sub 1. Let's look at the left-hand side. So the left-hand side, well, we just basically plug in 1 for our n. So we get 1 over I plus 1. Well, the sum starts at 1 and it ends at 1. So this is just 1 over 1 times 1 plus 1, which is 1/2. So the left-hand side is equal to 1/2. On the right-hand side, again, we just plug in 1, so we get 1 over 1 plus 1, which is 1/2. And sure enough, the left-hand side is equal to the right-hand side. So S sub 1 is true. In other words, our statement is true for n equals 1. Now we have to write down the induction hypothesis. I'll just call it IH. Here is the step where we suppose that our statement is true for some arbitrary positive integer k. So we just have to write down our statement when n is equal to k. So all you do is replace all the n's with k's. So we'll go from 1 to k, 1 over I plus 1, and then here we get k over k plus 1. And this should be true for some arbitrary positive integer k. All right, so we get to assume this. Now we need to show our statement is true for k plus 1. So I'm going to go ahead and write down what we need to show just to help us. So we need to show that the sum as I runs from 1 to k plus 1 is equal to 1 over I plus 1, and then here we need to have k plus 1, and on the bottom it would be k plus 1, so k plus 2. So this is the statement we need to show. This is not part of the proof, right? So generally when you do write this down, you want to write it down on the side, and you don't want to mix it with your proof. Because if you just write this down and you don't write we need to show, whoever is reading your proof will think that you don't know what you're doing because this is what you actually have to prove. So technically you're not supposed to write it down. All right, so now to prove this, we'll start by writing down the left-hand side, and we'll show it's equal to the right-hand side. So the sum, as I runs from 1 to k plus 1, of 1 over I plus 1, well, let's see, we need to break this up, and we need to somehow involve the induction hypothesis. So the induction hypothesis had a k here. So what we'll do is we'll write it as follows. We'll write down the first k terms. So we'll go from 1 to k. And then we'll add the last term. So the last term, well, how do you get the last term? Well, you just plug in k plus 1 into all the i's here. So you get 1 over k plus 1, k plus 2, right? 1 plus 1 is 2. We have k plus 1 here, and then you add another 1 and you get 2. All right, at this point, we're going to use the induction hypothesis, IH. The induction hypothesis said that this was equal to k over k plus 1, right? And then we have plus 1 over k plus 1, k plus 2. All right, now if we add these, hopefully we get this. If not, then we did it wrong. Let's find out. We need to find the LCD. So it looks like it's going to be k plus 1, k plus 2. So this, I'm going to write this over here as k plus 2, right? And then here we have k plus 1, k plus 2, and then here we just have 1 plus 1. All right, cross your fingers. I still don't see how it's going to work out. Again, we need to get k plus 1, k plus 2. So let's see. So this is equal to, let's see, k squared plus 2k. Oh, I see it. Plus 1. On the bottom, you get k plus 1, k plus 2. The numerator is a perfect square trinomial. It factors as k plus 1 squared. Then here we have k plus 1 and k plus 2. So we lose a copy of k plus 1. So we end up with k plus 1 over k plus 2. That's exactly what we wanted to show. So this means that our statement is true when n is equal to k plus 1. So s sub k plus 1 is true. Exclamation mark, exclamation mark. I didn't think it would work out. It wasn't obvious to me at first. Therefore, by the principle of mathematical induction, s sub n is true for all positive integers. So that was a nice problem, and it wasn't really too hard. Hey, what's up, YouTube? In this video, we're going to prove via mathematical induction that n factorial is greater than 2 to the n for n greater than or equal to 4. Let's do it. Proof. So the first step in induction proof, if you're writing out the steps, is called the base case. So I'll write out all the steps. So base case. So in the base case, you have to verify it's true for whatever number you're starting at. In this case, we're starting at n equals 4. So on the left-hand side, we get 4 factorial. So 4 factorial is 24. So piece of cake. On the right-hand side, we have 2 to the 4th. That's equal to 16. So all you do is you plug in the numbers. So 24 is bigger than 16. So check. So the base case is satisfied, right? So our statement is true for n equals 4. By the way, this here is our statement. We can call it s sub n. So if you want to add some rigor to the proof, you could say, so s sub 4 is true. That takes care of the base case. The next step is super important. It's called the induction hypothesis. So induction hypothesis. And there's different ways to write induction proofs. You don't have to name the steps. You can do it in paragraph form. But when you're first learning, I find it's really helpful to label all 3 steps. So we can abbreviate the induction hypothesis by using IH. For the induction hypothesis, you typically write suppose, and then you just copy-paste your statement, and you replace all of your n's with k's. So k factorial greater than 2 to the k. And this is true for some arbitrary, we don't know what it is, could be any number, k greater than or equal to 4. It's worth writing this down just to add another layer of rigor to your proof. Also, the fact that k is greater than or equal to 4 might be useful, right? It probably is going to be useful. Okay, now here's the hard part. The hard part is the induction step. This is where the work takes place. So the induction step. Okay, the induction step. So in this step, we have to show our statement is true for k plus 1. So I'm going to write it down in red over here and put it in parentheses. This is not part of the proof. This is what we have to show. So we need to show, so what you do is you put k plus 1s everywhere you see an n. Okay, so instead of n factorial, I'm going to put k plus 1 factorial. We want to show that's greater than 2 to the k plus 1. This is what we have to show, okay? So on the right-hand side here, you can write this as 2 to the k times 2 to the 1, right, using properties of exponents. You might be wondering, why am I doing that? Well, this is what we have to show. This is our goal, right? So maybe we can rewrite our goal in a more familiar way, right, in a way that we'll be able to reach that goal. So maybe write it like this, and then you could be clever. You can write this as 2 to the k plus 2 to the k, right? That's the same thing as 2 to the k, right? Think about it. If you have 2 to the k plus 2 to the k plus 2 to the k, you have 3 of them, so it's 3 2 to the k. So if you have 2 to the k plus 2 to the k, you have 2 to the k. Good stuff. So that's what we have to show. So if we can show this, we can rewrite everything and get to where we want. All right, so to start this part, we start by writing down this piece here. So k plus 1 factorial. So k plus 1 factorial is k plus 1, k minus 1, k minus 2, etc. So it's k plus 1. And the next one is k minus 1, k minus 2. So the rest of it is just k factorial. Okay. The next thing you could do naturally is maybe just distribute the k factorial. So this is k times k factorial plus 1 times k factorial. So just k factorial. Right, that's all it is there. And now we can use our induction hypothesis. This is super key, right? So k factorial is greater than 2 to the k, right? So what we're going to do in this case is we're going to replace all of our k factorials with 2 to the k, and we're going to put a greater than here. So the k hangs out, and then you just replace the k factorial with 2 to the k. You're using this, right? K factorial is bigger than 2 to the k. So you can just put a greater than there and just replace all the k factorials with 2 to the k. And then same thing here, plus 2 to the k. You're allowed to do that, right? So like if you knew k factorial was greater than w, and you had 3k factorial, that's greater than 3w. You can do that all day long in mathematics. It's something that people aren't used to doing. And so when they first see these proofs, they're like, whoa, what's going on? So again, you can do that. You can just put a greater than there and then drop the k factorial and put a 2 to the k there. All right, so what do we got going on? We've already got a 2 to the k here. Boom, look at that. So one of them is good. What about the other one? Well, this here has a k in front of it. We need to get rid of the k. Well, we know that k is greater than or equal to 4, right? We said it here. So same thing. We know k is greater than or equal to 4, so we can drop the k, insert that symbol, and then just put a 4 there. Boom. 4 2 to the k plus 2 to the k. But we don't need 4 2 to the k, right? We just need 2 to the k. Well, 4 is greater than or equal to 1. In particular, it's greater than 1, right? 4 is bigger than 1. So you can drop the 4 and just put a 1 there. So you get 1 times 2 to the k plus 2 to the k. So that's the same thing as 2 2 to the k, right? You have 2 of them, which is the same thing as 2 to the k plus 1, right? Because you're multiplying things with like bases, so you add the exponents. Would you look at that? K plus 1 factorial, take the strongest inequality, is greater than 2 to the k plus 1. So this shows that our statement is true for k plus 1 by, it's called the principle of mathematical induction by PMI. S sub n is true, just as a formality, for all integers n greater than or equal to 4. We fit the entire proof without me, having to scroll down. I could have scrolled down and created more room, but I thought, you know what? Let's see if I can fit the entire proof in one screen. So I hope that this video was helpful. Thanks for watching. Be sure to check out the rest of my videos. That's it. All right, we have T. It's a linear transformation from one vector space to another, and we have to show that the kernel of T is a subspace of V. Proof. So recall the kernel of T. It is the set of all the vectors inside V such that T of x is equal to the 0 vector in W. So in order to show that the kernel is a subspace of V, we have to show 3 things. 1, we have to show that the 0 vector in V is actually inside the kernel of T. Pretty easy to do. 2, we have to show that the kernel of T is closed under vector addition. And 3, we have to show that the kernel of T is closed under scalar multiplication. So we have to show these 3 things. If we show all 3 things, then we're done, and the kernel of T is a subspace of V. So I guess we'll start with the first one. Pretty easy to do. Note, if you take T and apply it to the 0 vector in V, that is just the 0 vector in W. So this is easy to show. This is actually a proof. So you can show this. So you should prove this. And it's very easy. Okay, that's exactly what it means for 0 to be in the kernel of T. Right, so this right here is what it means for a vector to be inside the kernel of T. So T of x equals 0 means x is in this set. So here we have T of 0 equals 0, so 0 is in this set. All right, so the first condition is done. Now we have to show it's closed under vector addition. So suppose we have two vectors, x and y, in the kernel of T. This means that T of x is equal to the 0 vector in W, and T of y is equal to the 0 vector in W. Right? That's what it means for a vector to be inside the kernel of T. We have to show that the sum of the vectors x plus y is also in the kernel. So we look at T of x plus y, and we have to show that this is equal to the 0 vector in W. Well, T is linear, so we can write T of x plus T of y, and T of x is the 0 vector in W. T of y is the 0 vector in W. When you add those 0 vectors, you just get the 0 vector. So that means that x plus y is in the kernel of T. Why does it mean that? Well, we have T of x plus y equal to the 0 vector. That means x plus y is in the kernel of T. The last thing to show is that it is closed under scalar multiplication. And it's very similar to what we just did. So suppose we have a vector x in the kernel of T, and some scalar c in our field f. Then T of x is the 0 vector in W. So, let me not write so. So then T of cx, we have to look at this term here, and we have to show this is equal to the 0 vector. So T is linear, so we can actually write it like this, c times T of x. But T of x is the 0 vector, so this is c times the 0 vector, which is the 0 vector. So cx is in the kernel of T. So we're done. We've shown all three things. We showed that it contains the 0 vector, it is closed under vector addition, and it is closed under scalar multiplication. So therefore, the kernel of T is a subspace of V. This is a really, really easy proof. That's it. Okay, so here's the setup. We have T. T is a linear transformation. Okay. We have V and W. These are vector spaces over some field which we'll call capital F. So we're going to show that every single linear transformation is one-to-one if the kernel is equal to the set containing the 0 vector. Okay, so proof. So we'll start by supposing that the kernel is just the set containing the 0 vector. So suppose that the kernel of T is just the set containing the 0 vector. So it's just the 0 vector. Now we need to show that T is one-to-one. So suppose, again, so I'll just write suppose, that T of x is equal to T of y for some arbitrary xy in V. Now we need to show that x is equal to y. So we can subtract T of y from both sides. So we end up with T of x minus T of y equal to the 0 vector in W. Now we can use linearity of T. Right? The fact that T is linear means we can do this. Right? So we have T of x minus y equal to the 0 vector. This is precisely what it means for x minus y to be in the kernel of T. But the kernel of T is just the 0 vector. So x minus y is equal to the 0 vector in V. So x is equal to y. Really, really incredible. All right, now we have to go the other way. We have to assume that the kernel of T, rather, we have to assume that T is one-to-one, and we have to show the kernel is just the 0 vector. So suppose that T from V into W is one-to-one. And we need to show that the kernel contains only the 0 vector. So take any x in the kernel. If we show x is 0, then the only element in the kernel is 0. All right, so here's the trick. So then T of x is equal to 0. By definition, it's in the kernel. But 0 is equal to T of 0. Now, it's worth emphasizing here. This is the 0 vector in V. This is the 0 vector in W. But wait a minute. We have T of x equal to t of 0. So x must be 0 because t is 1 to 1. So that means that the kernel of t is the set containing just the 0 vector. So that's it. That's the proof. It's worth knowing how to do this one on your own for sure. Okay, we have to show that H union K is a subspace of a vector space V if and only if H is contained in K or K is contained in H. And all of this will assume that K and H themselves are also subspaces of a vector space V, but I forgot to write it, so proof. All right, let's prove this direction first. So we'll start by assuming, so suppose, that H is contained in K or K is contained in H. So this means either H is contained in K or K is contained in H, or both. Now, if both are true, then H is just K, and it's a subspace because H union K is K, and we're done. So let's just start by saying if H is contained in K. Then let's look at H union K. What is this? Well, if it's not obvious, draw a picture. So let's see. Here's a little H, and here's K, right? Because H is contained in K. Well, the union in this case is just K. So this is K. And this is a subspace of V. So the union is a subspace. So that part is done. Now, if instead K is contained in H, then again, let's look at the union and see what we come up with. And if it's not obvious, draw a picture. So here is K, and it's contained in H. Looks like if you union K and H, you just get H. Well, sure enough, this is a subspace of our vector space V. Easy enough. All right, the other direction, let me see if I can erase this. Oh, look, it erases very badly. All right, so here we go. Okay, so the other direction looks a little better. That's a nicer arrow. We're going to prove by showing the contrapositive. So we're going to suppose that H is not contained in K, and K is not contained in H. Okay, and we are going to show that H union K is not a subspace. Okay, so to do this, we're going to prove this by contradiction. So suppose to the contrary that H union K is a subspace. So if we reach a contradiction, we are done. Okay, we are completely done. So at this point, we should probably use our hypothesis, right? So H is not contained in K, and K is not contained in H. So the first one means, so since H is not contained in K, there exists an element which we'll call little h, which lives inside H, but not K. And just for clarity, I'll write it right below. Now, since K is not contained in H, there exists an element, or a vector, actually, these are vectors, these are vector spaces, which lives in K, but not H. Okay. So now we need to somehow involve the fact that H union K is a subspace, right? It is a subspace. So the natural thing to do is to notice that the sum of H and K is in the union. So note, H and K are both in the union. So is the sum of the vectors. Why? I won't write it this time. It's because H union K is a subspace. Right? Okay. Now, to finish, we need to reach a contradiction, which we've been trying to do. At this point, I think we've exhausted almost everything. So we need to somehow involve little h, which we know is in H but not in K, and little k, which we know is in K but not in H. To do that, we need to know where H plus K is. So let's use the definition of union. So then, little h plus little k is in H, or little h plus little k is in capital K. So let's take cases. So if little h plus little k is in H, so we have a vector in H. So what other vector do we have in H? Let's see. We have little h, that's in H. So let's see if we can write k in a funny way. So then, little k, well, let's try to write it as h plus k. So you just write it down. Let's see, h plus k. Sure enough, looks like we can subtract h. And then this here is in H. This here is in H. So the difference is in H because H is a subspace. But we said that little k is not in H. If you look right here, it says that little k is not in H. So this is a contradiction. Likewise, if h plus k is in k, then let's see if we can do the same thing with little h. Little h is h plus k minus k. So this is in k. This is in k. So little h is in k. But again, we said that little h was not in k. If you look right here, you see that little h is not in k. But now we're saying it's in k. That's a contradiction. So in any case, we have a contradiction. So we're done. That's it. Prove that if lambda is an eigenvalue of a, then lambda squared is an eigenvalue of a squared. Proof. We'll start by supposing that we have lambda and it's an eigenvalue of a. So suppose lambda is an eigenvalue of a. And what does this mean? This means there is an eigenvector. So then we have some x, which is an eigenvector. So it's not equal to the 0 vector, such that a times the vector x is simply lambda x. And we have to show that lambda squared is an eigenvalue of a squared. So the natural choice to use for our eigenvector is x. So then we'll apply a squared to the vector x. And we can write this as a times the vector x using associativity. And now we know something about ax. It's equal to lambda x. So this is a lambda x. And now we can use associativity once again. And or rather, lambda is a scalar, so it commutes with a. So we can write this as lambda ax. And this is simply lambda, and then we can do it again. Ax is equal to lambda x. So this is lambda x. And this is simply lambda squared x. So we have a squared x equal to lambda squared x. So that's precisely what it means for lambda squared to be an eigenvalue. So it is an eigenvalue of a squared. And that's it. In this video, we're going to show that a set is not closed under vector addition. So our set is going to be capital T, and it is the set of all vectors x, y, such that y is equal to the square root of x. So first, what does it mean for T to be closed? So T is closed if for all x, y, and T, we have x plus y in T. That's what it means for T to be closed. So to violate this definition, we have to show the existence of two vectors in T such that the sum is not in T. So we have to come up with one example, right, in order to violate this. Because this is what it means for T to be closed. And this has to be true for all x, y. So if it's not true, even for just one pair, we got this. So let's find out. Let's just think of two simple vectors that are in T. The first one that comes to mind is 0, 0, but that feels like it's not going to work. So let's try something else. What's an easy number we can take the square root of? How about 4? So if x is 4, y is the square root of 4, that's 2. So the vector 4, 2, right, x is 4, y is 2, is in T. Let's see, what's another number that's easy to take the square root of? How about 9, right? If x is 9, right, that's a 4, it's an ugly 4. Y is the square root of 9, which is 3. So the vector 9, 3 is in T. So these two vectors are in T, right? X, Y, yeah, 4, 2, 9, 3. So all we have to do is look at the sum and ask ourselves, is that in T? If that's not in T, then we've disproven closure and T is not closed. So let's look at the sum. So 4, 2 plus 9, 3. So this is going to be 4 plus 9 is 13. 2 plus 3 is 5. So the question is this in T? Right? Is this in T? Well, let's see. Is it? So x here is 13. And y here is 5. So if this is in T, y is equal to the square root of x. Right? So that would mean that 5 is equal to the square root of 13. That's not true. That's not true. So this cannot be in T. Right? So this is not in T. So because 5 is not equal to the square root of 13. So that's how you show a set is not closed under vector addition. So you come up with two vectors in the set, and then you just show that it can't be in the set. I hope this video has made sense. That's it. We have to prove that this function is linear. In other words, it's a linear transformation. So recall that a map T from a vector space V into a vector space W is called linear, or is a linear transformation, if the following two conditions hold. So the first condition is that T of x plus y is equal to T of x plus T of y. And this condition has to be true for all vectors x and y in our vector space V. And the second condition is that if you take a scalar, let's call it c, and you multiply it by T of x, this is simply equal to T of c times the vector x. And this has to be true for all scalars c in our field and for all vectors x in our vector space V. So here our field will be the real numbers. So our scalar c will be in the set of real numbers. So let's go ahead and carefully prove this. So we'll start by taking some vectors in V. So take any, and let's use this notation here. Let's say x sub 1, y sub 1, and x sub 2, y sub 2. And our v here is r squared, and our w here is r squared. So this is what the vectors look like. They're ordered pairs, they're vectors, and these will be in r squared. And our scalar will be a real number. And we'll start by checking the first condition very carefully. This is really an exercise in notation. So we have T of the sum of the vectors. So x1, y1, plus x2, y2. Right, this is our x right here. This is our x, and this is our y. And now we'll actually perform the addition. So how do you add two vectors? Well, you add the components. So this is simply x1 plus x2, comma, it's a little 2, y1 plus y2. And now we'll go ahead and apply t to this new vector. So this is equal to parentheses. Let's see, so this is our x coordinate. So that's going to go here. So it's going to be 2 times x1 plus x2, and then plus y. Well, this is our y, so it'll be plus y1 plus y2. We have a comma, and then we have x minus y. So our x is x1 plus x2 minus, and now I really should put the y in parentheses, so y1 plus y2. Parentheses, parentheses. And now let's go ahead and distribute and see if we can make sense of this. So this is parentheses, let's see, 2x1 plus 2x2 plus y1 plus y2, comma, and then we have x1 plus x2, and then we'll distribute the minus. So minus y1 minus y2. And we somehow have to show that this is equal to t of the first vector plus t of the second vector. So this is equal to, let's look at t. T of xy is 2x plus y. So we can group these in a special way to make it more clear. Let's see. So 2x1 plus y1. So 2x1 plus y1 plus, and then here we have 2x2 plus y2. So 2x2 plus y2. Be really careful. And then here we have x minus y. So let's group them in a similar fashion. So this is x1 minus y1 plus x2 minus y2. Let me switch colors here, maybe add to the clarity. So this is equal to, okay, so our first vector is going to be 2x1 plus y1. That's the x-coordinate of our first vector. And the y-coordinate of our first vector is x1 minus y1. Right? We want it to be equal to the actual t of the vector. And then plus, and we have this piece, this is our second x-coordinate. So 2x2 plus y2. And then here we have this piece here, x2 minus y2. And now we're pretty much done, right? This is equal to t of x1, y1, plus, and this is t of x2, y2. And that shows the first condition, that t of x plus y is t of x plus t of y. Let me go ahead and write down t down here again for clarity. So t of xy was parentheses 2x plus y, comma, x minus y. That's how we were able to make this step here. So the next condition is to check, we have to check, I'll write it again, we have to check that t of c times a vector is equal to c times t of the vector. I wrote it backwards from the original definition, but that's no big deal. We'll actually prove it this way. So using the same vectors we have t of c of x1, y1. And how do you multiply a scalar times a vector? You just multiply each of the components by the scalar. So this is cx1, cy1. And now we'll apply t to this vector. So this is equal to, well, here's the formula for t. So it's 2x, so it's parentheses 2, and then our x is cx1. And then it's plus y, so that's cy1. Right, this is our x, this is our y. And then we have x minus y, so it'll be cx1 minus cy1. Right, this is our x, this is our y. Again, it's just a very careful exercise in notation. Well, these are all numbers, so we can actually factor out the c. This is equal to parentheses c, and then here we have 2x1 plus y1, comma, and then factor out the c here. This is cx1 minus y1. And now we can factor out the c completely. This is c, parentheses 2x1 plus y1, comma, x1 minus y1. And at last, this is c, and this is t of x1, y1. So we've shown both conditions, so therefore t is linear. Kind of rushed through that, but it still took a while. I hope that made sense. Prove p dp inverse to the nth power is equal to p d to the n p inverse for every positive integer n. So here p and d are square matrices and p is invertible. So proof. Let's go ahead and try this by induction. So our statement in all of this will be this one right here. And this will be our s sub n. So first we'll start with the base case. And since we're showing this is true for every positive integer, We'll start by showing it's true when n is equal to 1. So the left-hand side, when n is equal to 1, is simply p d p inverse to the first power, which is p d p inverse. And the right-hand side is p d to the 1 p inverse, which is just p d p inverse. So the left-hand side is equal to the right-hand side when n is equal to 1. So S sub 1 is true. Our statement is true when n is equal to 1. The second step will be the induction hypothesis. So induction hypothesis. So in this step, we suppose our statement is true for some positive integer k. So suppose p d p inverse to the k is equal to p d to the k p inverse for some positive integer k. So this here, this is actually s sub k. So we're supposing that s sub k is true for some positive integer. So now for the induction step, we need to show that our statement is true when n is equal to k plus 1. So I'm going to write that down in blue. So we need to show our statement is true when n is equal to k plus 1. So we need to show that p d p inverse, that's a funny looking p, to the k plus 1 is equal to p d to the k plus 1 p inverse. So that's what we have to show. So we'll start with the left-hand side, and we'll show it's equal to the right-hand side. So note, p d p inverse to the k plus 1. We can write this as p d p inverse to the k times p d p inverse to the 1, because laws of exponents let us just add the k and the 1. That works with matrices as well, with powers of matrices, right? If you have a squared times a cubed, that's just a to the 5th, where a is a matrix. Okay, now we know something about p d p inverse to the k. We know it's equal to this, right, by the induction hypothesis. So this is p d to the k p inverse, and over here we just have p d p inverse to the first power, so it's just itself. Now matrix multiplication is associative, so we can drop the parentheses, and p inverse times p, that's the identity matrix. So this is p d to the k times the identity matrix. I'll put a dot there, not really necessary, and then d p to the negative 1. So this is equal to, well, d to the k times I is just d to the k. So this is p d to the k d p inverse, because I is the identity matrix. And this is equal to p, well, there's a 1 here, so this is d to the k plus 1 p inverse. So that's the right-hand side. So we did it. So s sub k plus 1 is true, right? This statement here is s sub k plus 1. So in the induction hypothesis, we assume it's true for some k. So we suppose s sub k is true. And in the induction step, we prove it's true for k plus 1. So we prove that s sub k plus 1 is true. So that completes the proof. So by the principle of mathematical induction, our statement s sub n is true for every positive integer n. And I hope this helps. We're asked to prove that a complex number times its conjugate is the modulus of that complex number squared. So before we get started, Let's just write some stuff down just in case you've never seen this before. So a complex number can be written as a plus bi, and here a is called the real part of the complex number. That's the notation we use. And b is called the imaginary part of the complex number, and that's the notation we use. Z conjugate is just a minus bi. This is the conjugate of z. So how do you get the conjugate? You just switch the signs. Really easy. And the bars here, they don't mean absolute value. They mean modulus. Now, if z is a real number, then it's the same as absolute value. So this is the square root of a squared plus b squared. And this is called the modulus of z. All right, so now that that's out of the way, let's prove this. So proof. So we have to show that the statement holds for all complex numbers. So we have to start the proof by writing down, suppose we have some arbitrary complex number. So suppose z is a complex number and it is arbitrary. Now in order to prove this, we probably need to write down z. So then z is equal to a plus bi, where a and b are real numbers. So the conjugate of z is just a minus bi. Right? You just switch the signs. So then, to finish, what we'll do is we'll just work out the left-hand side, then we'll work out the right-hand side, and we'll show that they are actually just the same. So then, z times z conjugate, well, z is a plus bi, and z conjugate is a minus bi. There's a formula, but let's just distribute. So a times a is a squared. A times negative bi is negative abi. A times bi is plus abi. And bi times negative bi is negative b squared I squared. These cancel. And recall that I squared is equal to negative 1. So a negative and a negative is going to give us a positive. So z times its conjugate is just equal to a squared plus b squared. To finish, we'll work out the right-hand side of what we had to show. So let's look at the modulus of z. So note, the modulus of z, by definition, is the square root of the real part squared plus the imaginary part squared. So all we have to do now is square both sides. So if you take the modulus and you square it, well, when you square this, the square root goes away. So you just end up with a squared plus b squared. So we have a complex number times its conjugate is equal to a squared plus b squared. And we have that the modulus of a complex number squared is equal to a squared plus b squared. Hence, a complex number times its conjugate is equal to the modulus of that complex number squared. Since z in the set of complex numbers was arbitrary, this holds for all complex numbers out there. And that is how you prove it. Prove p dp inverse to the nth power is equal to p d to the n p inverse for every positive integer n. So here p and d are square matrices and p is invertible. So proof. Let's go ahead and try this by induction. So our statement in all of this will be this one right here. And this will be our s sub n. So first we'll start with the base case. And since we're showing this is true for every positive integer, we'll start by showing it's true when n is equal to 1. So the left-hand side, when n is equal to 1, is simply p d p inverse to the first power, which is p d p inverse. And the right-hand side is p d to the 1 p inverse, which is just p d p inverse. So the left-hand side is equal to the right-hand side. when n is equal to 1. So S sub 1 is true. Our statement is true when n is equal to 1. The second step will be the induction hypothesis. So induction hypothesis. So in this step, we suppose our statement is true for some positive integer k. So suppose p d p inverse to the k is equal to p d to the k p inverse for some positive integer k. So this here, this is actually S sub k. So we're supposing that S sub k is true for some positive integer. So now for the induction step, we need to show that our statement is true when n is equal to k plus 1. So I'm going to write that down in blue. So we need to show our statement is true when n is equal to k plus 1. So we need to show that p d p inverse, that's a funny looking p, to the k plus 1 is equal to p d to the k plus 1 p inverse. So that's what we have to show. So we'll start with the left-hand side, and we'll show it's equal to the right-hand side. So note p d p inverse to the k plus 1. We can write this as p d p inverse to the k times p d p inverse to the 1, because laws of exponents let us just add the k and the 1. That works with matrices as well, with powers of matrices, right? If you have a squared times a cubed, that's just a to the 5th, where a is a matrix. Okay, now we know something about p d p inverse to the k. We know it's equal to this, right, by the induction hypothesis. So this is p d to the k p inverse, and over here we just have p d p inverse to the first power, so it's just itself. Now matrix multiplication is associative, so we can drop the parentheses, and p inverse times p, that's the identity matrix. So this is p d to the k times the identity matrix. I'll put a dot there, not really necessary, and then d p to the negative 1. So this is equal to, well, d to the k times I is just d to the k. So this is p d to the k d p inverse, because I is the identity matrix. And this is equal to p, well, there's a 1 here, so this is d to the k plus 1 p inverse. So that's the right-hand side. So we did it. So S sub k plus 1 is true, right? This statement here is S sub k plus 1. So in the induction hypothesis, we assume it's true for some k. So we suppose S sub k is true. And in the induction step, we prove it's true for k plus 1. So we prove that S sub k plus 1 is true. So that completes the proof. So by the principle of mathematical induction, our statement S sub n is true for every positive integer n. And I hope this helps. We're being asked to prove that this function is differentiable on the coordinate axes, but is nowhere analytic. Let's go ahead and try to prove this. So proof. So we'll start by looking at the real part and the imaginary part of f and try to see when the Cauchy-Riemann equations hold. So set u of xy equal to the real part of f, so that will be x cubed plus 3x y squared minus 3x. And we'll set v of xy equal to the imaginary part of f, so that's y cubed plus 3x squared y minus 3y. And now let's go ahead and compute the first partial derivatives of u and v. So del u, del x, let's see, we're treating y as constant, so here x cubed is going to give us 3x squared. And treating y as constant, this is just going to give us 3y squared. And then the derivative of minus 3x is minus 3. Likewise, del v, del y, that's going to be 3y squared. And the derivative, I copied this down wrong. And the derivative of 3x squared y is simply 3x squared. And here, this derivative here is minus 3. Now we'll compute del u, del y. Let's see, del u, del y, well, this derivative is going to be 0. This one is 0, so we're going to get 6xy. And then del v, del x, well, let's see, that's simply going to be 6xy also. So this function is differentiable if and only if all of the first partial derivatives are continuous and the Cauchy-Riemann equations hold. So then f is differentiable at, say, z equals x plus iy if and only if all of these guys are continuous. I won't write that part down, but they have to be, and they are, if and only if they're continuous and the Cauchy-Riemann equations hold. So what does that mean? That means that del u, del x is equal to del v, del y, and that's clearly true. These are exactly the same, and del u, del y is equal to negative del v, del x. Now, these aren't exactly equal, right? Here we have 6xy, and here we have 6xy, but when you put a negative sign here, things change. So this happens if and only if 6xy is equal to the opposite of 6xy. So 6xy is equal to minus 6xy. And this happens if and only if 12xy is equal to 0, which happens if and only if x is equal to 0 or x is equal to y. So the Cauchy-Riemann equations hold and the partials are continuous if and only if x is equal to 0 or y is equal to 0. In other words, the function is differentiable on the coordinate axes, right? When x is 0, we're looking at this line here, and when y is 0, we're looking at this line here. So therefore, f is differentiable on the coordinate axes. Now we still have to show that it's nowhere analytic. That's kind of just like a remark. It should be clear that it's nowhere analytic because open straight lines are not open sets in the complex plane. So note, f is nowhere analytic because lines are not open sets. Right, are not open sets in the complex plane. Right? We know it's differentiable only on these lines, and for a function to be analytic, it has to be differentiable on an open set. So if I pick a point here, yeah, this is not an open set. In fact, there's no open set around this point on which it's analytic either. So I hope that helps. Let phi from G to K be a group homomorphism. We're going to prove that phi is 1 to 1 if and only if the kernel of phi is equal to the set containing the identity element of G. So, proof. Before we start the proof, let me remind you what the kernel of phi is. So the kernel of phi, it is the set of all of the x's in G such that phi takes x and maps it to the identity element in K. So to start the proof, let's go ahead and assume phi is 1 to 1. So suppose phi is 1 to 1. And the claim is that the kernel of phi is equal to this set here. So take any x in the kernel of phi. Then, well, what does it mean to be in the kernel? That means phi takes x to the identity in K. However, phi also takes the identity in G to the identity in K. Right? That equation is also true. But phi is 1-to-1. Whence x is equal to the identity element in G. So we took an x in the kernel and we showed that it was equal to the identity. So every single x is the identity. Thus, the kernel of phi, well, it's contained in this set, so it must be equal to that set. Now let's suppose that the kernel of phi is equal to the set containing the identity. So suppose that the kernel of phi is equal to the set containing the identity. And the claim is that it's 1-to-1. So assume that phi of x is equal to phi of y for some x, y, and g. And we have to show that x is equal to y. So the natural thing to do is to rewrite this equation. You can multiply this on the right by phi y inverse. So you could write it as follows. So then you can write this as phi x, phi y inverse equals the identity element in K. Phi is a group homomorphism, so we can rewrite this as follows. So phi of x, y inverse is equal to the identity element in K. Well, this is precisely what it means for x, y inverse to be in the kernel. So x, y inverse is in the kernel of phi, which is equal to the set containing the identity element in G. So this forces x, y inverse to be equal to the identity element in G. Hence, x is equal to y. Right? Just multiply both sides of this equation by y on the right, and you have x is equal to y. So we started with phi of x equal to phi of y, and we showed that x was equal to y. That's precisely what it means for phi to be 1-to-1. So this shows phi is 1-to-1. And that's it. So I ran into this problem in a pretty strange place. It says, give an example of a group G and a proper subgroup H of G such that H is isomorphic to G. So when I first saw this, I thought, wow, how can that be? If it's a proper subgroup, then it has to have less elements, right? Because, so what's the deal? And I thought, wait a minute, it can't be finite, right? So the example we come up with has to be infinite. That's the only way that this is going to work, because, see, if two groups are isomorphic, that means their cardinality is the same. So if you have finite groups and you do this, it's not going to work, right? Because if H is finite and G is finite, and you take H and you take a proper subgroup, let's use that notation, then H has less elements than G, so the cardinality of H is strictly less than the cardinality of G, so it fails horribly. So the only way this is going to work is if H and G are infinite. So I thought of this example, which is probably the simplest one. Take the set of integers under addition, and then take any set of multiples of z. Let's take 2z. So this is all of the even integers, and let's define phi from z into 2z by, say, phi of x equals 2x. And this works, right? This is a homomorphism. It's 1-to-1, and it's surjective. I won't prove it, but I'll give you like a quick sketch. So for any x, y, and z, maybe we will prove it. So for any x, y, and z, if you look at 5x plus y, that's 2 times x plus y. And that's just 2x plus 2y. Pretty easy stuff. And that's equal to 5x plus 5y. So that shows that, phi is a homomorphism. What about 1 to 1? A couple ways to do this. Let's be fancy and show that the kernel is the identity element. So suppose x is in the kernel of phi. And so this means, what does this mean? This means that phi takes x and sends it to the identity in 2z. Well, the identity in 2z is just 0, with the number 0. And so this means that 2x is equal to 0, and so x is equal to 0. So this shows that the kernel of phi is just the identity element. So 0 in this case, and so phi is 1 to 1. What about onto? Onto is pretty easy. Take any y in 2z. So this means that y is a multiple of 2, so you can write it as 2x, where x is in z. Going pretty fast. I wasn't planning on proving it. And then take 5x, that's an integer, so you can do that, and that's equal to 2x by definition of phi. But we said that's equal to y, so 5x is equal to y, so it's onto. So we've got that it's a homomorphism, it's 1 to 1, and it's onto. So what does that mean? We have an isomorphism, right? So z is isomorphic to 2z. So the fact we use 2 is pretty arbitrary, right? We could have used any integer, right? We could have used nz, as long as it's not 1 or -1, because then we get back the same thing, I guess. I hope that helps. Pretty cool example, I thought, so I figured I would make a video. Okay, we have a group G, and H is a finite non-empty subset, which is closed under the group operation, and we have to prove that H is a subgroup of G. So proof. Now, I won't bother writing down the hypothesis, it's just so much to write. So suppose it's a group, and suppose H is a finite non-empty subset, which is closed under the group operation. So we have to prove that H is a subgroup of G. So the first thing we have to show is that H is non-empty. But that's one of our assumptions, right? It's a non-empty subset, so that part is done. So done. 2. H is closed under the group operation. But again, that's one of our hypotheses, right? So it's closed under the group operation, so that part is done. The last thing we have to show is that H is closed under inverses. So suppose we have an element x in H, and we want to show that the inverse of x also lies in H. So the only thing we haven't used is the fact that H is finite. So we somehow have to use the fact that H is finite to show that x inverse also lives inside H. So note x squared, x cubed, x to the fourth, etc. are all in H, right? Because H is closed under the group operation. But H is finite. But H is finite. That means at least 2 of these must be the same. So there exists distinct positive integers, mn, that are positive integers, m not equal to n, such that x to the m is equal to x to the n. Now, if m is not equal to n, then either m is bigger than n or m is less than n. So let's assume, without loss of generality, that m is bigger than n. So we somehow need to incorporate the inverse into all of this. So let's do it in steps. First, let's take this and rewrite it. So note, we can rewrite that as x to the m minus n equals e. Now to involve the inverse, maybe just multiply both sides by the inverse. So x to the m minus n minus 1 is equal to x inverse. Okay, now the last step is to justify why this is an h. We have to explain why this is an h. So this is where we have to be really careful. So since m is bigger than n, that tells us m minus n is bigger than 0. So we can do it from here, but it might be easier if we think of it this way. So since it's bigger than 0, that means m minus n, well, the smallest number it can be is 1, so it's greater than or equal to 1. Okay, it's greater than or equal to 1. So let's take cases. So if m minus n is equal to 1, right? If it's greater than or equal to 1, it's either equal to 1 or greater than 1. So if it's equal to 1, then x inverse is equal to x. Well, then this is 1, right? So we just get 1 minus 1. So we get x to the 0, which is equal to the identity. Now, if x inverse is the identity, then x is the identity, because the inverse of the identity is the identity. So this is an h, right? Because then this is x, right? If x inverse is e, then x is e, so it's an h. If m minus n is bigger than 1, then x inverse, well, that's x to the, let me write it like this, m minus n minus 1. So that means that this term here is positive, right? It's positive. That's what it means if it's bigger than 1, because m minus n is bigger than 1. You're subtracting 1, so it's positive. So if it's 1, then it's x, and x is already an h, so we're done. If it's bigger than 1, then it's among these. And we said those are an h, so there's no problem there. So this is an h. So in any case, the inverse is an h. So this shows that, so h is closed under inverses. So that's the last thing we had to show. And so therefore, H is a subgroup of G. Kind of a delicate argument here at the end, so I hope that helps. Prove that the formula for the difference of squares holds for all a, b in a ring if and only if the ring is commutative. So let's go ahead and prove this. So proof. So we'll start by supposing that this formula holds for all of a, b, and r. So suppose that a squared minus b squared is equal to a minus b times a plus b for all a, b, and r. So then, for all a, b, and r, let's write it again. We've got a squared minus b squared. And now we'll use the distributive property. So this can be written as a times a plus b minus b times a plus b. And using the distributive property once again, we have a times a is a squared. A times b is simply ab. And here we end up with minus ba minus b squared. And then we have a squared minus b squared equals all of this. So we subtract a squared, subtract and add b squared. So we end up with 0. See, these go away and these go away. So we get 0 equals ab minus ba. And so ba is equal to ab. And this holds for all ab in the ring. So this shows r is commutative. So this shows r is commutative. On the other hand, we'll suppose that r is commutative, and we'll show that the formula holds. So suppose r is commutative, and now we have to show that the formula holds for all a, b, and r. So then, for all a, b in our ring R, let's look at a minus b times a plus b. And we'll show that this is equal to a squared minus b squared. So using the distributive property, this can be written as a times a plus b minus b times a plus b. And using the distributive property two more times, a times a is a squared, and then a times b is a times b. Then here we end up with minus ba, and then minus b squared. But we supposed that our ring R was commutative, so this is a squared plus ba minus ba minus b squared, right? AB is equal to BA because R is commutative. And so this is equal to 0. So we end up with a squared minus b squared. So we have a minus b times a plus b is equal to a squared minus b squared for all AB in the ring R. And that's precisely what we had to prove. So I hope this video made sense. Let R be a commutative ring with 1. And the claim is that R is a field if and only if R has no proper non-zero ideals. Let's go ahead and do this proof. So proof. Let's start by proving that if R is a field, then R has no proper non-zero ideals. So suppose R is a field. And let's go ahead and try this by contradiction. So suppose, to the contrary, that I is a proper non-zero ideal. Well, if it's a proper ideal and it's not 0, then that means that I is not equal to the entire ring. And it also means that I is not equal to the ideal containing 0 and 0 alone, the ideal generated by 0. So this means there exists an element which we'll call, say, A in I, such that A is not equal to 0. Right? It's a non-zero ideal. And since R is a field, A inverse exists. Right? That's what it means to be a field. Every non-zero element is a unit. In other words, every non-zero element has an inverse. And so then what we can do is we can write 1 in a clever way. 1 can be written as the inverse of A times A. This is an element in our ring or in our field R. And this is A. So therefore, because I is an ideal, the product also lives in I. So I contains 1. So for all R and R, we can write R equals R times 1. This is an element in R. This is an element in I. And so because I is an ideal again, the product is in I. So every single R in capital R is also in capital I. So I must be the whole ring. And that's a contradiction. So that takes care of the first direction. So now we'll prove the other direction. Let me use a different color. So there's my funny arrow. So we'll start by supposing R has no proper non-zero ideals. So suppose R has no proper non-zero ideals. And the claim is that R is a field. So claim R is a field. So to show it's a field, we have to show that every non-zero element is a unit. So take any A in R A not equal to 0. And we're going to look at the following set. So set, let's call it I. Set I equal to the set of RA, R, and R. In other words, this is the ideal generated by A. Now, I just said it was an ideal, but we're going to go ahead and prove it in this problem. So claim I is an ideal. So to show it's an ideal, use a different color. What do we need to show? We need to show two things. We need to show that, one, for all A, B, and I, we have A minus B, also in I. And two, we need to show that for all R and R, for all A and I, we have RA, also in I. So those are the two things we are going to prove here. Probably shouldn't have used A in this definition here. It's kind of sloppy because we have an A here as well. Okay, so take any x, y, and I. So then x can be written as R1A, and y can be written as R2A for some R1 and R2 in capital R. And now we'll start by looking at this difference here, A minus B. So in our case, x minus y. So then, x minus y, well, x is R1A, so this is R1A, minus, and y is R2A, so this is R2A. And this can be written as R1 minus R2 times A. And this is in I. And the reason is R1 is in R. R2 is in R. So R1 minus R2 must also be in R because R is an additive group under addition. It's a ring. So therefore this is in R and this is A. And so by definition of I, this element is in I. So that takes care of the first part. For the next part, so then, for all R in R, we'll look at Rx. Well, Rx is R, R1A. And this is, using associativity, R, R1 parentheses A. Both of these guys are in R. R is a ring. It's closed under multiplication. So the product is in R. And this is A. So by definition of I again, simply by the definition, this is also in I. So we showed that Rx is in I. So this shows that I is an ideal. So this shows I is an ideal. Okay, so we've shown that I is an ideal. So because I is an ideal, or rather before that, note something. Note A can be written as 1 times A. So A is certainly an I. And so then we can do the following. 1 can be written as 1 times A. We know that 1 is an R. We know that A is an I. And we've shown that I is an ideal, right? So that this means that this product is an I. And this is because, just to be really clear, this is because 1 is an R, A is an I, and I is an ideal. That's the key step. And since 1 is an I, there exists some R in R such that 1 can be written as RA. So 1 is equal to RA. And so this shows that A is a unit. So this shows A is a unit. And so therefore R must be a field. Thus, R is a field. So we did that in excruciating detail, but hopefully that helped. Suppose that the limit of f of x as x approaches a is equal to L, and the limit of g of x as x approaches a is equal to k. Then we have to prove that the limit of f plus g as x approaches a is equal to L plus k. Before we start the proof, let me just refresh your memory on what a limit is. So recall the limit as x approaches a of f of x is equal to L. This means for all epsilon greater than 0, there exists a delta greater than 0 such that for all x and r with the distance between x and a smaller than delta, we have the distance between f of x and L smaller than epsilon. So when you first see this definition, it can be intimidating. So proof. So in order to prove that this limit is equal to L plus k, we have to start by letting epsilon be greater than 0. So let epsilon be greater than 0. And I won't write it, but suppose that we have this limit and this limit both existing, the first one equal to L and the second one equal to k. So since the limit of f of x as x approaches a is equal to L, that means we can find a delta. Let's call it delta 1. So delta 1 greater than 0 such that for all x in R with the distance between x and a smaller than delta 1, we have the distance between f of x and L smaller than, well, we can use epsilon, but at some point we're going to have to add, and we have to use two limits. So let's use epsilon over 2. And if it's not clear, you'll see why at the end. What's going to happen is we're going to have epsilon over 2 plus epsilon over 2, and that's going to give us the epsilon. Since the limit as x approaches a of g of x is equal to k, we can find another delta, let's call it delta 2, such that for all x and r with the distance between x and a smaller than delta 2, that should have been delta 1, we have g of x minus k less than epsilon over 2. Okay, so now we need to find a delta for our problem, right? We need to find a single delta. So the natural choice is to take the minimum of the two. So let delta equal the minimum of delta 1 and delta 2. Then for all x and r with the distance between x and a smaller than delta, we have, well, we're going to look at f plus g minus L plus k. We want to show that that is less than epsilon. So f of x plus g of x minus L plus k, that should be f of x minus L. So what we're doing here is rewriting it in a clever way so that we can use both conditions, right? We have this and we have this, and we want to use them both. So what we've done is we've rewritten it in a way where we can do that. Now we'll use the triangle inequality. So this is the triangle inequality. And we know that the first absolute value is less than epsilon over 2. So epsilon over 2. plus, and then the second absolute value is less than epsilon over 2. So you add them and you get epsilon. And so the proof is done. So we started with some epsilon greater than 0. We found a delta, which was also positive. And we showed that the distance between f plus g and L plus k was smaller than epsilon. And that completes the proof. We have to show that the function f of z equal to the real part of z is nowhere differentiable, so proof. So we'll use the Cauchy-Riemann equations. So first, so let z equal, let's say, x plus iy. So then we can write f of z, well, that's just the real part of z, which is just x. Now, we need to identify u and v to use the Cauchy-Riemann equations. So I'm going to write this as x plus 0i. Okay, so now it's pretty easy to see what u is. So set u of xy equal to x, and v of xy equal to 0. So now we'll check. We'll take the partial derivatives, and we'll check the Cauchy-Riemann equations. If they don't hold, then we're done, and the function is nowhere differentiable. So del u del x, that's equal to 1. Del u del y is equal to 0. Let's see, del v del y, that's equal to 0, and negative del v del x, that's also equal to 0. So these are the same, but that's not enough. These have to be the same, and they're not. So del u del x is not equal to del v del y. So the Cauchy-Riemann equations do not hold. And they don't hold at any point. 1 is never equal to 0. So this always works. This works for every complex number. So since the Cauchy-Riemann equations do not hold at any complex number, f is nowhere differentiable. So to prove a function is nowhere differentiable, one way to do it is to show that the Cauchy-Riemann equations do not hold. What's up, YouTube? In this video, we're going to do a delta epsilon proof for a function of two variables. So first, let's recall what the definition of a limit is for a function of two variables. So here L is a real number, so L is real, and what follows. And so when we write limit of f of xy as xy approaches x naught y naught, if we say this is equal to L, this means that for every epsilon greater than 0, we can find some delta greater than 0 such that, well, whenever the distance between xy and the pair x naught y naught is small, the distance between f of xy and L is also small. So for all pairs xy in the plane with the distance between xy and x naught y naught being small. So we can write that as follows. I'm going to put a double bar here. This is called the Euclidean distance. So the Euclidean distance, the distance between xy and x naught y naught, whenever that's small, note here this has to be greater than 0. We have the distance between f of xy and L, this is just the regular absolute value, less than epsilon. So this up here is called the Euclidean distance. You could rewrite it as follows. You could write this by subtracting the components. So you can write it as x minus x naught, comma, y minus y naught. And then by definition, this is equal to the square root of x minus x naught squared plus y minus y naught squared. So a lot of the books will write the condition like this. I just figured I'd do it this way in the video since this generalizes to points in Rn, right? You can have n tuples and this will work. Okay, so let's go ahead and try to figure out the proof. So proof. So I think we should be able to figure it out fairly easily. So I'm just going to go ahead and just try to do the proof all at once. Instead of just trying to figure it out first, let's go for it. So let epsilon be greater than 0. And then choose delta equals, and I'm going to pause here because I don't know what delta is. So at some point, we're going to come back and fill this in. Okay, so choose delta equals some magical number. Then for all pairs x, y in the plane with, I'm going to go ahead and write it like this. With this condition here, square root x minus, in this case it's 0 squared, right, plus y minus 0 squared less than delta, right? X naught and y naught are 0 in this problem. We have, and so now we have to look at the distance between f of x, y, and L. So f of x, y is this piece here. So it's x cubed over x squared plus y squared. And that's minus 0. And we want this to be less than epsilon. So this is equal to the absolute value of x cubed over x squared plus y squared. So we want to make this small. So one thing we can do here is we can say this is equal to the absolute value of x times the absolute value of x squared over x squared plus y squared. This is a reoccurring idea in these types of problems. So when I saw the x cubed, I thought, oh, I can borrow an x and do this, you know. And this number here is less than or equal to 1. So this is less than or equal to the absolute value of x times 1. Now, if you're not convinced by that, it's pretty easy to see that it's true. Just let me do it on here on the side. So if x is 0, then it's 0 and we're done because everything is less than epsilon. If x is not 0, then you can write this x squared over x squared plus y squared. You can drop the y squared, and so you just get x squared over x squared, and so it's less than or equal to 1. So in any case, it's less than or equal to 1. So what do we do next? Well, now there's a little trick, another little trick. So this is equal to the absolute value of x. And the absolute value of x, you can write this as the square root of x squared, right? And that's the same thing as saying the square root of x minus 0 squared, right? Which is what we have here. And so this expression should be less than or equal to the square root of x minus 0 squared plus y minus 0 squared. Haha, and that's less than delta, right? So now we know what our delta has to be. It has to be epsilon, right? And so all of this is equal to epsilon. So I hope that made sense. I kind of rushed through it. That's it. So we're asked to show that a function is nowhere differentiable. So the natural thing to try first is to check the Cauchy-Riemann equations. If they do not hold, then we're done and the function is nowhere differentiable. So in this problem, we're going to set u of xy to 2y. And v of xy, this is actually negative x. You have to be careful here, negative x. So now we'll compute the partial derivatives and check the Cauchy-Riemann equations. So del u del x, that's equal to 0. Del u del y, that's equal to 2. Del v del y, that's equal to 0. So these are the same. So far so good. And let's see, negative del v del x. Well, negative del v del x is negative 1. But here you have another negative, so we're just going to get 1. So right away you see that these guys are not the same. So since del u del y is not equal to negative del v del x, the Cauchy-Riemann equations do not hold. And this is true for every complex number, so the Cauchy-Riemann equations never hold at any point. So the function is nowhere differentiable. So f is nowhere differentiable. You have to be really careful. Sometimes there's functions